In 1989, a spacecraft no larger than a small car began a journey that would take 14 years and nearly 5 billion kilometers, carrying with it a probe destined to fall into the crushing atmosphere of the largest planet in our solar system, the only human-made object ever to descend into a gas giant. The Galileo mission unfolded slowly, patiently, across the better part of 2 decades, gathering secrets from Jupiter's swirling storms and the hidden oceans of its moons, sending back whispers of discovery from a distance so vast that each signal took nearly an hour to reach Earth. If these quiet explorations of science and distance help the mind settle, subscribing might bring more evenings like this one. Now, with the stars overhead and the outer planets waiting in the dark, the story of Galileo can begin. In the early 1970s, when the Voyager spacecraft were still being assembled in cleanrooms and the Pioneer probes had only just begun their lonely journeys toward the outer solar system, a small group of scientists and engineers at the Jet Propulsion Laboratory in Pasadena, California, began to dream of something more ambitious, something that would not merely fly past Jupiter in a matter of days but would instead settle into orbit around that distant giant and study it for years on end, watching the slow dance of its moons and the swirling patterns of its atmosphere as they changed with the seasons. If one could speak of seasons on a world so far from the warming influence of our sun. These early conversations were quiet and unhurried, taking place in conference rooms and over cups of coffee in the JPL cafeteria, where engineers would sketch orbital trajectories on napkins and planetary scientists would list the mysteries they most wished to solve, the questions that a brief flyby could never hope to answer. Questions about the composition of Jupiter's deep atmosphere and the nature of its powerful magnetic field and the geological processes that might be reshaping the surfaces of its many moons even as we watched from our comfortable distance of several 100 million miles. The Pioneer missions, launched in 1972 and 1973, had provided humanity's first close-up glimpses of Jupiter, revealing a world far more complex and dynamic than anyone had imagined from telescopic observations alone. And these tantalizing images and measurements only deepened the scientific community's desire to return with more sophisticated instruments and, crucially, with the ability to remain in the Jovian system long enough to observe changes over time, to witness the rise and fall of storms, the orbital mechanics of the Galilean moons, and perhaps even volcanic eruptions or other geological activity that might occur during an extended stay. By 1974, this informal dreaming had crystallized into a formal mission concept that NASA officially designated the Jupiter Orbiter Probe, or JOP for short, a name that was admirably straightforward if perhaps lacking in poetry, describing precisely what the spacecraft would do without any flourishes or romantic embellishments, simply a vehicle that would orbit Jupiter while also deploying a probe into the planet's atmosphere. 2 complementary activities that together would reveal the secrets of the solar system's largest world in unprecedented detail. The Jupiter Orbiter Probe concept represented a significant departure from the flyby missions that had characterized planetary exploration up to that point, and the engineers at JPL understood that designing a spacecraft capable of surviving for years in the harsh radiation environment around Jupiter would require innovations in shielding, in power systems, in communications, and in the fundamental architecture of the spacecraft itself, challenges that were daunting but not insurmountable, problems that could be solved with sufficient time and resources and the steady application of human ingenuity. Among those who championed this ambitious undertaking was Bruce Murray, who would become the director of the Jet Propulsion Laboratory in 1976, and who brought to the position both a scientist's passion for exploration and an administrator's understanding of how to navigate the complex political and budgetary waters of Washington. where dreams of distant worlds must always be balanced against more immediate terrestrial concerns, where every dollar spent on planetary exploration must be justified to legislators who represent constituents with pressing needs much closer to home. Murray understood that the Jupiter orbiter probe would require sustained advocacy over many years, that such a complex and expensive mission could not be approved and launched in a single burst of enthusiasm, but would need patient champions who could keep the project alive through changes in presidential administrations, through shifts in congressional priorities, through the inevitable budget crises and competing demands that would arise over the course of a decade or more of development. And he committed himself and his laboratory to this long campaign with the same determination that earlier generations of explorers had brought to expeditions across unmapped oceans and uncharted continents. The decision to name the mission after Galileo Galilei came somewhat later, when the austere technical designation of Jupiter Orbiter Probe was set aside in favor of a name that would connect this modern voyage of discovery to one of the most profound moments in the history of human understanding of the cosmos. That winter of 1609 and 1610, when an Italian mathematician and philosopher turned a newly improved telescope toward the night sky and observed, for the first time in human history, for small points of light moving in orbit around Jupiter, a discovery that would help to overturn the ancient belief that Earth stood motionless at the center of the universe. Galileo Galilei, working in Padua and later in Florence, had watched those 4 tiny moons night after night, carefully recording their positions and eventually recognizing that they were satellites orbiting Jupiter just as our own moon orbits Earth. A finding that provided powerful evidence for the Copernican model of a sun-centered solar system and that earned Galileo both lasting fame and considerable trouble with the religious authorities of his time, who found his conclusions threatening to established doctrine, though history would ultimately vindicate his patient observations and careful reasoning. Those 4 moons that Galileo discovered, now known as Io, Europa, Ganymede, and Callisto, would become primary targets for the spacecraft that bore his name, and there was a pleasing symmetry in this connection across nearly 4 centuries of human curiosity. The same worlds that had captured the attention of a Renaissance scholar with a primitive telescope now drawing a sophisticated robotic emissary from a civilization that had learned to send its instruments across the vast gulfs of interplanetary space, carrying forward a tradition of careful observation and methodical inquiry that Galileo himself would surely have recognized and approved. The original planning for what was now called the Galileo mission envisioned a launch date in 1982, a target that seemed comfortably far in the future when it was first proposed, but that would prove, as such targets often do, to be optimistic in ways that the early planners could not have fully anticipated. For the development of a spacecraft as complex as Galileo would encounter obstacles and setbacks that would push the actual launch date further and further into the future, testing the patience and persistence of everyone involved. These delays arose from multiple sources, some technical and some political and some simply the result of the inherent difficulty of attempting something that had never been done before, of designing systems that would need to function reliably for years in an environment that no human-made object had ever experienced for such an extended period. An environment where the radiation was intense enough to damage electronic components, and where the distance from Earth meant that any malfunction would need to be diagnosed and addressed with communication delays measured in tens of minutes rather than seconds. One significant source of uncertainty and delay centered on the question of how Galileo would reach Jupiter, a debate that reflected the broader changes occurring in American space policy during the late 1970s and early 1980s, specifically the decision to phase out expendable rockets like the reliable Titan and Atlas vehicles that had launched earlier planetary missions in favor of the new space transportation system, more commonly known as the Space Shuttle. which was then being developed as the primary means of American access to space. The original Galileo mission design had assumed the use of a powerful expendable rocket, a vehicle that would be discarded after use, but that would provide the substantial energy needed to send a heavy spacecraft on a direct trajectory toward Jupiter, a journey of several 100 million miles that required significant velocity beyond what was needed merely to reach Earth orbit. And the engineers at JPL had designed their spacecraft accordingly, planning for a relatively straightforward journey that would deliver Galileo to Jupiter in roughly 2 years after launch. However, as NASA's commitment to the space shuttle deepened and political pressure mounted to demonstrate that the shuttle could support all of America's space activities, including deep space exploration, the Galileo mission was redesigned to launch from the shuttle's cargo bay. A change that introduced new complexities and constraints because the shuttle itself could only reach low Earth orbit, requiring an additional upper stage to send Galileo on its way toward the outer solar system. And this upper stage became the subject of considerable debate and multiple redesigns over the following years. The original plan called for using a powerful liquid-fueled upper stage called the Centaur, which would have provided enough energy for a direct trajectory to Jupiter. But the Centaur presented serious safety concerns because it used volatile liquid hydrogen and liquid oxygen propellants that would need to be carried in the shuttle's cargo bay alongside the astronaut crew, a configuration that made many engineers uncomfortable and that would eventually be prohibited entirely in the aftermath of later shuttle safety reviews. Though this prohibition came too late to affect the initial Galileo planning directly. While these debates about launch vehicles and trajectories continued, the estimated cost of the Galileo mission was growing in ways that alarmed both NASA administrators and congressional overseers, as the original figure of approximately $400 million, which had seemed substantial when it was first proposed, proved to be inadequate for a mission of such complexity and ambition, with costs eventually reaching $1.6 billion by the time the spacecraft was finally launched, a fourfold increase that reflected both the inherent difficulty of the undertaking and the additional expenses incurred by years of delays and redesigns. This cost growth was not the result of waste or mismanagement in any simple sense, but rather reflected the genuine challenges of building something unprecedented, of developing new technologies and solving problems that no one had ever faced before, of maintaining a skilled workforce through years of uncertainty about whether the mission would ultimately be approved and funded, costs that accumulated steadily like sediment in a riverbed, each layer representing another month or year of patient work by thousands of dedicated professionals. Throughout these years of planning and replanning, a scientific team was being assembled to define the observations that Galileo would make and the instruments it would carry, a collaboration that extended far beyond the Jet Propulsion Laboratory to include researchers from universities and institutions across America and Europe, experts in atmospheric physics and magnetospheric science and planetary geology and a dozen other specialties, each bringing their unique perspectives and priorities to the collective enterprise of designing a mission that would address the most important scientific questions about Jupiter and its retinue of moons. The role of project scientist for the Galileo mission was entrusted to Torrance Johnson, a planetary scientist at JPL whose expertise in the geology of icy moons and whose ability to communicate complex scientific concepts to non-specialists made him ideally suited for the challenging task of coordinating the efforts of dozens of principal investigators and hundreds of supporting researchers, each of whom had strong opinions about what Galileo should observe and how limited spacecraft resources should be allocated among competing scientific priorities. Johnson brought to this role not only deep scientific knowledge but also the diplomatic skills necessary to build consensus among researchers who might otherwise have spent their energies in unproductive conflicts over instrument selection and observation time, and his patient stewardship of the science team would prove essential in maintaining the collaborative spirit that a mission of this complexity demanded. A spirit that would need to endure through many more years of delays and setbacks before Galileo finally reached its destination. The instruments selected for the Galileo orbiter represented the state-of-the-art in planetary science instrumentation of the 1980s, including cameras that would capture images of Jupiter and its moons in unprecedented detail, spectrometers that would analyze the composition of surfaces and atmospheres, magnetometers that would map the complex magnetic environment of the Jovian system, and particle detectors that would sample the charged particles trapped in Jupiter's powerful radiation belts. Each instrument the product of years of development by teams of specialists who poured their expertise and their hopes into hardware that would need to function flawlessly at enormous distances from any possibility of repair. The atmospheric probe that would descend into Jupiter's clouds represented its own distinct engineering challenge. A compact vehicle that would need to survive the violent deceleration of atmospheric entry at speeds far greater than any object had ever experienced, withstanding temperatures that would briefly exceed those at the surface of the Sun and pressures that would increase steadily as the probe descended through layer after layer of alien atmosphere, transmitting its precious data back to the orbiter above for relay to Earth before finally succumbing to the crushing depths of the Jovian atmosphere. Scientists from European institutions played important roles in the Galileo collaboration, contributing instruments and expertise that enriched the mission's scientific return and that exemplified the increasingly international character of planetary exploration. A recognition that the questions being asked about Jupiter and its moons were of interest to all of humanity, not merely to a single nation, and that the resources and talents needed to answer those questions could most effectively be marshaled through cooperation across national boundaries. The assembly of this scientific team was itself a gradual process that unfolded over years, beginning with informal discussions among researchers who shared an interest in Jupiter and its moons, continuing through formal proposals and selection processes, and eventually coalescing into a community of investigators who would work together through launch preparations and the long cruise to Jupiter and the even longer orbital mission, a community that became something like an extended family, united by a shared commitment to understanding a distant world. As the 1970s gave way to the 1980s, the Galileo mission remained in a state of perpetual preparation, always seeming to be just a few years away from launch, always encountering new obstacles that pushed that launch date further into the future, testing the patience of scientists who had devoted significant portions of their careers to a spacecraft that sometimes seemed more like a dream than a tangible reality. A dream that persisted nevertheless because the scientific rewards of success would be so profound and because those who had committed themselves to this undertaking were not easily discouraged. The original 1982 launch date slipped first to 1984, then to 1985, then to 1986, each postponement accompanied by revised schedules and updated cost estimates and renewed assurances that the delays were necessary and that the mission would ultimately succeed. Assurances that required ever greater reserves of faith as the years accumulated and as younger researchers who had joined the project as graduate students found themselves growing into mid-career scientists while still waiting for their instruments to depart for Jupiter. These delays, frustrating as they were at the time, would ultimately prove to have an unexpected benefit, for the additional years of preparation allowed the science team to refine their understanding of what they hoped to learn from Galileo and allowed the engineering team to address problems that might otherwise have compromised the mission, a silver lining that could only be appreciated in retrospect, when the actual data began flowing back from Jupiter and the quality of those observations vindicated the patient work of the preceding decades. The birth of the Galileo mission was thus a long and difficult labor. extending across more than 15 years from the first conceptual studies to the actual moment of launch. A gestation period that tried the spirits of everyone involved, but that ultimately produced a spacecraft capable of achievements that would have seemed impossible to the dreamers who first imagined a Jupiter orbiter in the early 1970s. Achievements that would reveal wonders beyond anything those early planners had dared to hope for. Worlds of fire and ice and hidden oceans that awaited only the patient gaze of Galileo's electronic eyes to yield their secrets to human understanding. The creation of the Galileo spacecraft represented one of the most ambitious engineering undertakings in the history of planetary exploration. A project that demanded solutions to problems no spacecraft had ever faced before. And the men and women who designed and built this remarkable machine spent more than a decade refining every component, every system, every tiny detail, until they had produced something truly extraordinary. A vessel capable of traveling hundreds of millions of kilometers through the cold darkness of space and then spending years orbiting the largest planet in our solar system, all while enduring conditions that would destroy any ordinary piece of equipment within moments of arrival. When you consider the Galileo spacecraft in its entirety, you might picture something rather graceful despite its considerable size. Standing approximately 5.3 meters tall when fully assembled, which is roughly the height of a modest two-story building. Though of course in the weightlessness of space such comparisons become somewhat abstract, as there is no up or down, no floor upon which to stand and measure, only the silent spinning of mechanisms designed to function far from any human hand that might adjust or repair them. The total mass of the spacecraft at the moment of launch was 2,562 kilograms, a figure that included everything the machine would need for its long journey and its years of operation around Jupiter. From the scientific instruments that would study the giant planet and its moons to the fuel that would allow course corrections and orbital maneuvers. From the power systems that would keep everything running to the communication equipment that would send precious data back across the vast gulf of space to waiting receivers on Earth. One of the most distinctive features of the Galileo spacecraft was its dual-spin design, an elegant engineering solution that allowed two different parts of the spacecraft to behave in two entirely different ways simultaneously, each section doing exactly what it needed to do without interfering with the other. The spacecraft was essentially divided into two main portions, and these portions were connected by a bearing assembly that allowed them to rotate independently of one another. A mechanical arrangement that sounds simple enough in principle but required extraordinary precision in execution. One section of the spacecraft, called the spinning section or rotor, rotated continuously at approximately 3 revolutions per minute, which is to say it completed one full rotation every 20 seconds or so. A gentle and steady spin that served several important purposes and gave the spacecraft a kind of inherent stability, much as a spinning top remains upright while a stationary one would simply fall over. This spinning section carried many of the scientific instruments that benefited from rotation, particularly those designed to measure fields and particles. For as the spacecraft turned, these instruments could sweep through space in all directions, sampling the magnetic fields and charged particles and dust grains that surrounded the spacecraft at any given moment, building up a complete picture of the environment rather than staring fixedly in just one direction. The rotation also helped to keep the spacecraft stable and properly oriented, using the same physical principles that keep a bicycle wheel spinning smoothly or a gyroscope standing upright on its pedestal. And this stability was essential for a mission that would last for many years and could not afford to tumble or drift out of control. The other section of the spacecraft, called the Detour section or stator, did something rather remarkable. It remained essentially stationary even while the rest of the spacecraft spun around it, pointing steadily at whatever target the scientists and engineers wanted to observe. This Despun section carried the instruments that needed to stare at things, the cameras and spectrometers that required a stable platform from which to gaze at Jupiter's swirling clouds or the icy surfaces of distant moons, and the high-gain antenna that needed to remain pointed precisely at Earth in order to send its signals home across the immense distance. The mechanism that allowed this dual behavior, with one section spinning and the other holding still, was a sophisticated bearing and motor assembly that continuously adjusted the Despun section to counteract the rotation of the spinning section, a kind of mechanical magic that happened smoothly and silently throughout the entire mission, requiring very little power and producing no vibrations that might disturb the sensitive instruments. Perhaps the most visually striking element of the Galileo spacecraft was its high-gain antenna, a beautiful piece of engineering designed to enable communications across the vast distances between Jupiter and Earth, distances so great that radio signals, traveling at the speed of light, would take more than half an hour to make the journey in each direction. This antenna was an umbrella-like structure measuring 4.8 meters in diameter when fully deployed, nearly 16 feet across in older measurements, and it was made from a golden mesh of metal that would unfold like a flower opening its petals once the spacecraft was safely in space and on its way to Jupiter. The gold color was not merely decorative but served a practical purpose, as gold is an excellent material for reflecting certain wavelengths of electromagnetic radiation and resisting the degradation that might affect other materials over the long years of a deep space mission. The design of this antenna was ingenious in its mechanical simplicity, consisting of 18 ribs that would swing outward from the central hub, pulling the fine gold mesh into a smooth parabolic shape that would focus radio waves with great precision, allowing the spacecraft to transmit data at rates up to 134,000 bits per second, which may sound modest by the standards of modern internet connections but represented a substantial achievement for a spacecraft operating nearly 800 million kilometers from Earth. The antenna was designed to fold up compactly for launch, tucking against the body of the spacecraft like a closed umbrella, and then to open gradually once in space, the ribs swinging outward one by one until the full dish was revealed, ready to begin its long conversation with the receiving stations back home. The atmospheric probe that Galileo carried was itself a remarkable piece of engineering, a separate spacecraft in miniature that would part company with the main orbiter and plunge directly into Jupiter's atmosphere, sending back information about the conditions it encountered during its brief and violent descent. This probe had a mass of 339 kilograms, which made it a substantial object in its own right, and it was designed to withstand forces and temperatures that would have destroyed virtually any other human-made object in existence. The probe consisted of a descent module, which carried the scientific instruments, and a deceleration module, which was essentially a heat shield designed to protect the descent module during the initial entry into Jupiter's atmosphere, when friction with the thickening gases would produce temperatures exceeding 15,000 degrees Celsius, hotter than the surface of the Sun. The heat shield was made from a material called carbon phenolic, a type of ablative material that would char and vaporize as it heated, carrying the heat away from the probe rather than allowing it to penetrate to the delicate instruments within. Behind this heat shield, the descent module waited in relative safety, insulated from the inferno outside, and once the probe had slowed sufficiently, the heat shield would be jettisoned and a parachute would deploy, allowing the descent module to drift down through Jupiter's clouds while its instruments measured temperature and pressure and chemical composition and wind speed and all the other properties that scientists back on Earth were so eager to learn about. The orbiter portion of the Galileo spacecraft carried an impressive array of scientific instruments, 10 different devices designed to study Jupiter and its moons and the space environment around them, each instrument contributing a different piece to the puzzle of understanding this miniature solar system so far from our own. The solid-state imaging camera, which the scientists referred to as SSI, was perhaps the most famous of these instruments. The device that would capture the stunning photographs of Jupiter's storms and its moon's alien landscapes that would eventually grace the covers of magazines and textbooks around the world. This camera used a charged coupled device, a type of electronic sensor that converted light into electrical signals, rather than traditional photographic film, and it could capture images in various wavelengths of light, from violet through red and into the near-infrared, allowing scientists to learn different things depending on which colors they chose to examine. The near-infrared mapping spectrometer, known as NIMS, was designed to analyze the composition of surfaces and atmospheres by studying how they absorbed and reflected infrared light, which is to say light just beyond the red end of the visible spectrum. Light that our eyes cannot see but that carries rich information about the chemical makeup of whatever it touches. By examining the specific wavelengths of infrared light that were absorbed or reflected, scientists could identify particular molecules and minerals, determining whether a moon's surface contained ice or rock or some combination thereof, or what kinds of gases swirled in Jupiter's turbulent atmosphere. The ultraviolet spectrometer, abbreviated as UVS, performed a similar function but at the opposite end of the spectrum, studying light with wavelengths shorter than violet, light that is absorbed by Earth's atmosphere and therefore difficult to study from the ground, but that reveals important information about the upper atmospheres of Jupiter and its moons, where energetic processes break apart molecules and create glowing auroras. The photopolarimeter radiometer, which the team called PPR, was a versatile instrument that measured both the brightness of light and its polarization, which is a property relating to the direction in which light waves vibrate. And this information helped scientists understand the sizes and compositions of particles in atmospheres and on surfaces. The magnetometer was one of the most important instruments aboard Galileo, a sensitive device mounted at the end of a long boom that extended outward from the main body of the spacecraft, and its purpose was to measure the magnetic field in the space around Jupiter, a magnetic field far more powerful than Earth's and extending far out into space, creating a vast magnetic bubble called a magnetosphere that traps charged particles and creates intense radiation belts. The boom that held the magnetometer was necessary to place the instrument far from the spacecraft's own electronic systems, which generated their own small magnetic fields that might otherwise interfere with the delicate measurements. The plasma detector was designed to study those charged particles directly, counting them and measuring their energies and determining what kinds of particles they were, whether electrons or protons or heavier ions. And this information helped scientists understand how Jupiter's magnetosphere worked and how it interacted with the solar wind, the stream of charged particles flowing outward from the Sun. Additional instruments included the energetic particle detector, which measured higher energy particles than the plasma detector, particles accelerated to tremendous speeds by the electromagnetic forces in Jupiter's magnetosphere, and the dust detector, a German-built instrument designed to sense the tiny grains of cosmic dust that permeate our solar system and to measure their sizes and speeds and compositions. The heavy ion counter was added specifically to monitor the radiation environment around Jupiter, helping scientists understand the threats posed to the spacecraft's electronics and to future spacecraft that might venture into this hostile region. Powering all of these instruments and the spacecraft's essential systems required a reliable source of electricity that could function for years without maintenance, far from the Sun and its warming light. in the cold darkness of the outer solar system. Solar panels, which work so well for spacecraft operating near Earth or even Mars, would have been impractical at Jupiter, where the Sun appears much smaller and dimmer than it does from Earth, providing less than 4% as much light and therefore less than 4% as much power for any solar panels that might be deployed. Instead, Galileo carried two radioisotope thermoelectric generators, which the engineers and scientists called RTGs, devices that converted heat from the natural decay of radioactive plutonium-238 into electrical power. Each RTG contained a quantity of plutonium dioxide fuel, and as the plutonium atoms naturally broke apart, they released energy in the form of heat, and this heat was converted into electricity using a principle called the thermoelectric effect, which generates a small electrical voltage whenever there is a temperature difference between two different types of material. The RTGs produced no moving parts, no wear, no noise, just a steady and reliable flow of electricity year after year, and together the two units provided approximately 570 watts of electrical power at the beginning of the mission, enough to light a handful of household light bulbs but more than enough to operate the spacecraft's carefully designed low-power electronics. One of the greatest challenges facing the engineers who designed Galileo was the radiation environment around Jupiter, which is far more intense than anything encountered elsewhere in the solar system. Intense enough to kill an unprotected human within minutes and to damage ordinary electronics within hours or days. The radiation consists primarily of electrons and protons trapped in Jupiter's powerful magnetic field, particles accelerated to tremendous energies and forming belts of radiation that make Earth's Van Allen belts seem gentle by comparison. Electronic components exposed to this radiation can suffer various forms of damage, from temporary glitches caused by individual energetic particles striking sensitive circuits to permanent degradation of the semiconductor materials from which modern electronics are made. The engineers addressed this challenge in several ways, beginning with careful selection of components that were inherently more resistant to radiation than typical commercial electronics, and continuing with physical shielding, placing sensitive components inside boxes made of dense materials like tantalum that could absorb some of the incoming particles before they reached the delicate circuits within. Software was also designed to detect and correct errors caused by radiation, and some systems were made redundant so that if one component failed, a backup could take over. Despite all these precautions, the radiation would gradually degrade the spacecraft systems over time, and the mission planners knew that Galileo would not last forever, but they designed it to last long enough, and in the end it exceeded all their expectations, continuing to function in that hostile environment for more than 3 times as long as originally planned. The construction of the Galileo spacecraft was a vast collaborative effort involving numerous companies and institutions, with the Hughes Aircraft Company playing a central role in the spacecraft's development, providing expertise in spacecraft systems and integration that had been developed over decades of building satellites and space probes for various customers including NASA and the military. Hughes was responsible for much of the overall spacecraft design and assembly, bringing together the work of dozens of subcontractors and ensuring that all the different pieces fit together properly and functioned as a unified whole. The German Aerospace Agency, known by its German initials as DLR, contributed significantly to the mission as well, providing the atmospheric probe's release mechanism and the dust detector instrument, and German scientists were deeply involved in the analysis of data from these systems throughout the mission. This international cooperation was characteristic of many large space missions, which often benefit from the diverse expertise and resources that different nations can bring to bear on problems that no single country might be able to solve alone. And it also helped to spread both the costs and the benefits of space exploration across a wider community of humanity. As you consider all these details, the spinning and despun sections, the delicate instruments, the plutonium power sources, the radiation-hardened electronics, you might find your thoughts growing quieter and your breathing growing slower, for there is something rather peaceful about contemplating machinery so carefully designed, systems so thoughtfully assembled, each part doing its job without fuss or hurry. And in the darkness of space, the Galileo spacecraft carried all of this engineering excellence outward toward Jupiter, spinning gently, instruments ready, prepared to reveal the secrets of a world that had been nothing more than a bright point of light in ancient skies for all the thousands of years that humans had looked upward and wondered what might be out there. So far away, so patient, waiting to be explored. In the quiet months of late 1985, as winter approached and the holiday season drew near, the Galileo spacecraft sat within the vast processing facilities of the Kennedy Space Center in Florida, surrounded by technicians and engineers who were carefully attending to the final stages of its preparation for launch. The spacecraft had been years in the making, a product of countless hours of design work and fabrication and testing, and it was now entering that final delicate period when a machine built for the depths of space must be ready to leave the only planet it has ever known. The launch date had been set for January of 1986, and there was a sense among the team that their long labors were finally approaching fruition, that the spacecraft they had nurtured through so many challenges was about to begin its journey toward the distant giant planet and its family of remarkable moons. The Kennedy Space Center in those days was a place of considerable activity, with multiple missions being prepared simultaneously and the Space Shuttle program operating at what seemed to be a regular and confident pace. The shuttle had been flying for several years by that point, and while there had been difficulties and delays as with any complex endeavor, there was also a growing sense of routine about the whole enterprise. A feeling that humanity had perhaps settled into a comfortable rhythm of traveling to and from low Earth orbit. Galileo was scheduled to ride aboard one of these shuttles, tucked within the cargo bay along with a powerful upper stage rocket that would send it on its way to Jupiter once the shuttle had carried it safely above the atmosphere. The particular upper stage that had been selected for this mission was called the Centaur, a rocket stage that used liquid hydrogen and liquid oxygen as its propellants, a combination that provides exceptional performance but requires careful handling due to the extremely low temperatures involved and the energetic nature of the fuels themselves. The Centaur had been chosen because Galileo needed a great deal of energy to reach Jupiter in a reasonable amount of time, and the Centaur could provide that energy in a way that few other available upper stages could match. The mission profile called for the shuttle to carry Galileo and its Centaur stage into orbit, after which the payload would be deployed and the Centaur would ignite, sending Galileo on a direct trajectory toward Jupiter with no need for the complex gravitational maneuvers that are sometimes employed to boost spacecraft to the outer solar system. January of 1986 arrived, and the Kennedy Space Center continued its preparations for the various missions on its schedule. On the 28th of that month, the Space Shuttle Challenger lifted off from Launch Complex 39B on what was designated Mission 51L, carrying a crew of 7 astronauts including Krista McAuliffe, who had been selected to be the first teacher in space as part of a program to inspire students across the nation. The weather that morning was cold, colder than it had been for any previous shuttle launch, and there had been discussions among engineers about whether the conditions might affect certain components of the solid rocket boosters that helped lift the shuttle during the first minutes of flight. 73 seconds after launch, the Space Shuttle Challenger broke apart over the Atlantic Ocean, and all 7 crew members lost their lives. The cause was later determined to be a failure in the joint seals of the right solid rocket booster, seals that had been compromised by the cold temperatures and that allowed hot combustion gases to escape and impinge upon the external fuel tank, ultimately leading to its structural failure. The nation watched in horror as the events unfolded on live television, and the tragedy marked a profound turning point in the American space program, forcing a comprehensive re-examination of the shuttle system and the institutional cultures that had allowed the launch to proceed despite the warnings of some engineers. At the Kennedy Space Center, the Galileo spacecraft sat in its processing facility as the news of the disaster spread through the workforce. The technicians and engineers who had been preparing the spacecraft for its January launch found themselves in the peculiar and somber position of having been so close to their own launch date while witnessing the loss of a sister mission and its crew. The entire shuttle fleet was immediately grounded pending investigation, and it became clear very quickly that Galileo would not be launching anytime soon. The spacecraft that had been so carefully prepared, so meticulously tested, so close to beginning its journey across the solar system, would instead be returning to the Jet Propulsion Laboratory in California to wait out an uncertain period of delay. The process of returning Galileo to the Jet Propulsion Laboratory was itself a significant undertaking, requiring the spacecraft to be carefully disassembled from its launch configuration, packed into protective containers, and transported across the country to the facilities where it had been built. At the Jet Propulsion Laboratory, the spacecraft would be placed in storage and its systems would be maintained in a state of readiness, though no one knew at that point how long the wait would be or what changes might be required before the mission could proceed. The engineers who had worked so hard to prepare Galileo for launch now faced the task of preserving their spacecraft through an indefinite delay while also addressing whatever modifications might emerge from the post-Challenger review of shuttle safety procedures. The investigation into the Challenger disaster was thorough and far-reaching, examining not only the technical causes of the failure but also the decision-making processes and communication patterns that had led to the launch going forward despite concerns. The Rogers Commission, as the investigative body was known, produced a detailed report that made recommendations for numerous changes to both the shuttle hardware and the management practices of the National Aeronautics and Space Administration. Among the many consequences of the disaster and the subsequent review was a fundamental reconsideration of what payloads could safely be carried in the shuttle cargo bay. And this reconsideration would have profound implications for Galileo. The Centaur upper stage that had been planned for Galileo was examined with fresh eyes in the wake of the Challenger accident, and the examination raised concerns that had perhaps not been given sufficient weight before. The Centaur used liquid hydrogen and liquid oxygen, propellants that, while highly efficient, are also highly energetic and potentially hazardous. The idea of carrying such a rocket stage within the enclosed cargo bay of a crewed spacecraft, with astronauts working just meters away from thousands of kilograms of cryogenic propellants, now seemed more concerning than it had before. If something were to go wrong with the Centaur while the shuttle was in orbit, the consequences could be catastrophic, and after Challenger, the space agency was understandably reluctant to accept risks that might once have seemed acceptable. The decision was eventually made to prohibit the use of the Centaur upper stage on future shuttle missions, a decision that was prudent from a safety standpoint but that created a significant problem for Galileo. Without the Centaur, the mission would need to use a different upper stage, and the available alternatives were considerably less powerful. The most suitable replacement was the inertial upper stage, a solid-fueled rocket that had been designed by the military and that had already flown on several shuttle missions. The inertial upper stage was reliable and well understood, but it simply could not provide the same amount of energy as the Centaur, and this limitation would fundamentally change how Galileo would reach its destination. With the Centaur, Galileo could have been sent on a direct trajectory to Jupiter, crossing the vast distance in a relatively straightforward manner and arriving at the giant planet in roughly 2 years. With the less powerful inertial upper stage, a direct trajectory was simply not possible, as the spacecraft would not have sufficient velocity to complete the journey in any reasonable time frame. The mission designers were therefore forced to develop an entirely new trajectory, one that would use the gravity of other planets to gradually boost Galileo's speed through a technique known as gravity assist. Gravity assist is a method by which a spacecraft can gain or lose velocity by flying close to a planet and using the planet's gravitational field to alter its trajectory. The physics of the maneuver are well understood and have been used on many missions, but they require careful planning because the spacecraft must arrive at the assisting planet at precisely the right time and angle to achieve the desired effect. For Galileo, the new trajectory would require not one but multiple gravity assists, with the spacecraft making close approaches to Venus and then returning to Earth twice before finally having enough velocity to reach Jupiter. This new trajectory, which came to be known by the letters VEGA for Venus-Earth-Earth Gravity Assist, would take considerably longer than the original direct flight plan. Instead of arriving at Jupiter in roughly 2 years, Galileo would now require approximately 6 years to complete its journey, looping through the inner solar system before finally heading outward to its destination. The delay was unfortunate but unavoidable, and the mission planners set about redesigning the flight profile to accommodate these new constraints while ensuring that the scientific objectives could still be met. The redesigned trajectory also raised new concerns about the spacecraft itself, because the flight path would now take Galileo much closer to the Sun than the original plan had envisioned. During the Venus flyby and portions of the Earth return loops, the spacecraft would be subjected to solar heating that exceeded the levels for which it had been designed. The engineers at the Jet Propulsion Laboratory had to develop new thermal protection measures, including sunshades and modified operating procedures, to ensure that the spacecraft's sensitive instruments and systems would not be damaged by the increased solar exposure. While the technical teams worked to address the challenges posed by the new trajectory, another concern was being raised by members of the public who were worried about a different aspect of the mission. Galileo carried a pair of radioisotope thermoelectric generators, which used the heat produced by the natural decay of plutonium dioxide to generate electrical power for the spacecraft. These generators were necessary because Jupiter is so far from the Sun that solar panels large enough to provide adequate power would have been impractically massive, and radioisotope thermoelectric generators had proven themselves on numerous previous missions to the outer solar system. However, the use of plutonium on a mission that would be launched aboard the space shuttle and that would make multiple close approaches to Earth raised concerns among some advocacy groups and members of the public. The worry was that if something went wrong during launch, either with the shuttle itself or with the upper stage, the plutonium could be released into the environment and pose a health hazard to people in the surrounding area. The concerns were heightened by the memory of the Challenger disaster, which had demonstrated that shuttle launches were not without risk, and by the fact that the new gravity assist trajectory would bring Galileo back to Earth for close flybys, creating additional opportunities for potential mishaps. The National Aeronautics and Space Administration conducted extensive safety analyses of the radioisotope thermoelectric generators, examining the various ways in which an accident could occur and the potential consequences for public health. The generators were designed with multiple layers of protection, including sturdy casings and heat-resistant materials, intended to contain the plutonium even in the event of a launch failure or an unplanned atmospheric reentry. The agency concluded that the risks were acceptably small and that the benefits of the mission justified proceeding with the launch, a position that was supported by independent reviews but that did not fully satisfy all of the critics. In the period leading up to the eventual launch, protests were held by anti-nuclear activists who wanted to prevent Galileo from leaving Earth with its plutonium power sources. Some of the protesters were concerned specifically about the risk of accident, while others opposed the use of nuclear materials in space on broader philosophical grounds. The activists called for the mission to be delayed or cancelled, or for alternative power sources to be developed, though the reality was that no viable alternative existed for a mission to the outer solar system where sunlight was too weak to be useful for power generation. The concerns about the Earth flybys were particularly acute, because the gravity assist maneuvers would bring Galileo hurtling back toward our planet at high velocity, passing through regions of space where malfunction could potentially send the spacecraft into the atmosphere. The mission designers calculated these flybys with extreme precision, ensuring that the spacecraft would pass at safe distances and that even significant navigation errors would not result in an unplanned Earth impact. The casings around the plutonium were designed to survive atmospheric reentry intact even in the worst-case scenarios, though the agency acknowledged that no system could provide an absolute guarantee of safety. The months stretched into years as the shuttle fleet slowly returned to flight status and the various missions that had been delayed by Challenger were gradually rescheduled. Galileo remained in storage at the Jet Propulsion Laboratory throughout this period, its systems being maintained and its hardware being periodically tested to ensure that the long wait was not causing any degradation. The engineers kept careful watch over their spacecraft, knowing that when the time finally came to launch, everything would need to work as designed despite the extended delay. The period of waiting lasted 32 months in total, a span of time that tried the patience of everyone involved but that also allowed for the various modifications and improvements necessitated by the new mission profile to be implemented. The spacecraft that would eventually launch toward Jupiter was in some ways a different machine from the one that had been prepared in late 1985, adapted and modified to meet the challenges of its new trajectory and the lessons learned from the Challenger disaster and its aftermath. Finally, in October of 1989, Galileo was returned to the Kennedy Space Center to begin preparations for launch. The spacecraft was mated to its inertial upper stage and installed in the cargo bay of Space Shuttle Atlantis, which was being prepared for mission STS-34. The launch date was set for the 18th of October, nearly 4 years after the original planned launch and following a period of difficulty and delay that had tested the commitment of everyone associated with the mission. The crew of STS-34 included Commander Donald Williams, pilot Michael McCulley, and mission specialists Shannon Lucid, Franklin Chung Diaz, and Ellen Baker. These 5 astronauts would carry Galileo to orbit and deploy it for its long journey to Jupiter, a journey that would now take 6 years instead of 2, but that would nevertheless proceed thanks to the perseverance and ingenuity of the many people who had refused to let the mission be cancelled despite all of the obstacles that had been placed in its path. On the morning of October 18, 1989, Space Shuttle Atlantis lifted off from the Kennedy Space Center, carrying Galileo in its cargo bay along with the inertial upper stage that would send the spacecraft on its way. The launch proceeded smoothly, with none of the difficulties that had plagued earlier attempts, And within hours, Galileo had been deployed from the shuttle and its upper stage had ignited, sending the spacecraft on the first leg of its long and circuitous journey toward Jupiter. As Galileo departed Earth orbit and began its slow spiral through the inner solar system, the spacecraft was finally doing what it had been designed to do, exploring the solar system and gathering data about the environments through which it passed. The delays had been long and the changes had been significant, but the mission was underway at last, and the years of waiting were beginning to fade into memory as the focus shifted to the scientific discoveries that lay ahead. The first major milestone on the new trajectory would be the flyby of Venus in February of 1990, followed by a return to Earth in December of that same year and another Earth flyby in December of 1992. Only then, after these multiple gravity assists had boosted its velocity to sufficient levels, would Galileo finally turn its instruments toward the outer solar system and begin the long coast to Jupiter, where it was scheduled to arrive in December of 1995, 6 years after leaving Earth. The tragedy of Challenger had changed everything for Galileo, forcing a complete reimagining of how the mission would reach its destination and adding years of delay to an already lengthy timeline. But the mission had survived, adapted, and persevered, and as the spacecraft headed toward its first planetary encounter at Venus, there was reason to hope that all of the difficulties had been worth enduring, that the scientific rewards waiting at Jupiter would justify the long and winding path that Galileo had been forced to take. On the 18th of October in the year 1989, the morning arrived at Kennedy Space Center with that particular quality of stillness that sometimes settles over Florida's Atlantic coast in autumn, when the summer's oppressive humidity has begun to ease and the air carries just a hint of the cooler months to come. The sky above Launch Complex 39B held scattered clouds, and the weather teams who had been monitoring conditions through the night found themselves cautiously optimistic that the day would cooperate with the plans that had been so many years in the making. The Space Shuttle Atlantis stood on the pad, gleaming white against the blue Florida sky, connected to its rust-colored external tank and twin solid rocket boosters in that distinctive configuration that had become familiar to anyone who followed the American space program. Within the payload bay of the orbiter, secured carefully in its cradle and waiting with mechanical patience, rested the Galileo spacecraft, ready at last to begin its long journey toward the distant realm of Jupiter. The crew of STS-34 had been awakened early that morning, following the traditional rituals that preceded every shuttle launch, eating their breakfast together and suiting up in the bright orange launch and entry suits that astronauts wore during the critical phases of flight. Commander Donald Williams led this crew, a naval aviator and veteran astronaut who had previously flown aboard Discovery and who brought to this mission the steady, experienced hand that such a significant undertaking required. Williams had accumulated thousands of hours in high-performance aircraft and understood intimately the delicate balance between careful preparation and the acceptance of calculated risk that spaceflight demanded. Beside him in the cockpit would sit pilot Michael McCulley, for whom this mission represented his first journey into space, though his background as a naval aviator and test pilot had prepared him thoroughly for the responsibilities he would assume. The mission specialist crew comprised 3 individuals whose diverse expertise would prove essential to the success of the flight. Shannon Lucid, a biochemist by training and already a veteran of one previous shuttle mission, brought not only her scientific knowledge but also the calm, methodical approach to problem-solving that would characterize her long and distinguished career in space. She would go on to set records for spaceflight duration among American astronauts, but on this October day she was focused simply on the tasks at hand, on the deployment of a spacecraft that represented the hopes of planetary scientists around the world. Franklin Chang Diaz, born in Costa Rica and possessing a doctorate in plasma physics, was serving on his second shuttle flight and carried with him both the technical expertise to manage complex systems and a deep appreciation for the international dimensions of space exploration. Ellen Baker, a physician and geologist on her first spaceflight, rounded out the crew with her medical training and her understanding of the Earth sciences that complemented the mission's planetary exploration objectives. These 5 individuals rode the elevator up the launch tower in the hours before launch, crossed the access arm to the orbiter, and settled into their assigned positions within the cramped confines of Atlantis's flight deck and mid-deck. The countdown proceeded through its final hours with that measured cadence of checks and verifications that characterized shuttle operations, each step performed with careful attention to the procedures that had been refined over years of experience. The launch window for this particular day was relatively brief, constrained by the orbital mechanics that would eventually send Galileo on its indirect path toward Jupiter. And so the ground teams worked with quiet efficiency to ensure that no technical issues would force a delay. At 12:53 in the afternoon, Eastern Daylight Time, the moment arrived that so many people had worked toward for so very long. The main engines of Atlantis ignited first, building to full thrust while the shuttle remained held to the pad by explosive bolts. And then the solid rocket boosters joined in with their tremendous additional force, and Atlantis lifted from Launch Complex 39B in a column of fire and steam that rolled across the Florida marshlands. The sound reached the viewing areas seconds later, that deep, visceral rumble that seemed to penetrate the chest cavity and remind observers of the tremendous energies being unleashed. The shuttle climbed through the scattered clouds and arced over the Atlantic Ocean, accelerating toward orbit while below, the spectators and the mission controllers and the engineers who had built Galileo watched with a mixture of relief and anticipation. For the team at the Jet Propulsion Laboratory in Pasadena, California, and for their colleagues at NASA centers around the country, this launch represented the culmination of nearly 12 years of effort since the project had received its initial approval in 1977. Those years had brought challenge after challenge, redesign after redesign, and delay after delay, until it might have seemed to some that Galileo would never actually leave the Earth. The original plan had called for a launch in 1982 using the Space Shuttle and a powerful Centaur upper stage that would have sent the spacecraft on a direct trajectory to Jupiter, arriving after only about 2 years of flight. But the shuttle program had experienced its own delays, and then the Challenger disaster in January of 1986 had halted all shuttle flights and led to a fundamental reassessment of what payloads and operations could safely be conducted from the orbiter. The liquid-fueled Centaur stage, with its volatile hydrogen and oxygen propellants, was deemed too dangerous to carry in the shuttle's payload bay, and so the mission planners had been forced to find an alternative. The inertial upper stage, which used solid propellants and was already certified for shuttle use, became the replacement, but this change carried significant consequences. The IUS could not provide the same energy as the Centaur, and therefore Galileo could not fly directly to Jupiter but would instead need to follow a much longer, more circuitous route that employed gravity assists from Venus and Earth itself to gradually build up the velocity needed to reach the outer solar system. This Vega trajectory, as it came to be called, standing for Venus-Earth-Earth Gravity Assist, would extend the journey to Jupiter from 2 years to approximately 6 years, a substantial increase that required the spacecraft to be capable of surviving and functioning through a much longer cruise phase. The safety modifications required after Challenger had added weight to the spacecraft and reduced margins throughout the design, and the engineers had labored to accommodate these changes while preserving the scientific capabilities that made the mission worthwhile. There had been protests from groups concerned about the plutonium dioxide fuel that powered Galileo's radioisotope thermoelectric generators, the RTGs that would provide electrical power to the spacecraft in the dim reaches of the outer solar system where solar panels could not gather sufficient energy. These protests had generated considerable press attention in the weeks before launch, though NASA had conducted extensive safety analyses and had concluded that the risks were acceptably small. The solid casing that surrounded the plutonium was designed to survive even the most severe accident scenarios, and the agency had proceeded with launch preparations while acknowledging the legitimate concerns that citizens raised about nuclear materials in space. All of this history, all of these struggles and compromises and persistent efforts, formed the backdrop against which Atlantis rose into the October sky, and those who understood the magnitude of what had been required to reach this moment felt a particular depth of emotion as they watched the shuttle disappear into the blue. The initial phase of powered flight lasted approximately 8.5 minutes, after which the main engines shut down and the external tank was jettisoned to tumble back toward the atmosphere and break apart over the ocean. Atlantis was now in orbit, circling the Earth at approximately 17,500 miles per hour, and within the payload bay, Galileo waited in darkness for the orbital operations that would send it on its way. The next several hours were occupied with the careful preparations for deployment, as the crew configured the spacecraft and its attached inertial upper stage for release from the orbiter. The deployment would occur over the night side of Earth, during a period when Atlantis was out of direct communication with ground stations, but being tracked by the tracking and data relay satellite system that provided continuous coverage for shuttle missions. Commander Williams and his crew worked through their checklists methodically, verifying that all systems were functioning as expected and that Galileo was ready for the separation that would mark its transition from cargo to independent spacecraft. Approximately 6 hours and 16 minutes after launch, with Atlantis flying tail first to provide the proper orientation, the springs that held Galileo in its cradle pushed the spacecraft gently away from the shuttle's cargo bay. The separation was slow and deliberate, with Galileo and its attached IUS drifting away from Atlantis at a rate of only a few feet per second, the two objects gradually increasing their distance as the orbiter performed a maneuver to move clear of the deployment zone. The crew watched through the windows and monitored their instruments as the spacecraft that had occupied so much of their payload bay became an independent object floating in the darkness of space, still tethered to the Earth's gravity but soon to break free and venture outward toward another world. The procedures required Williams to fly Atlantis to a safe distance before the inertial upper stage would ignite, because the exhaust from the solid rocket motors would create a hazard to the shuttle if it remained too close. The separation distance grew over approximately 45 minutes, with ground controllers tracking both vehicles and confirming their positions, until the moment arrived for the IUS to perform its critical function. The first stage of the IUS fired for approximately 150 seconds, accelerating Galileo and adding substantially to its velocity, and then after a brief coast period, the second stage ignited and burned for approximately 105 seconds more. These two burns, occurring as the spacecraft passed over the night side of Earth, imparted the energy needed to send Galileo out of Earth orbit and onto an interplanetary trajectory that would carry it first toward the inner solar system, toward a rendezvous with Venus in February of 1990. For the mission controllers at the Jet Propulsion Laboratory, the minutes following IUS ignition were tense ones, as they waited for confirmation that the burns had proceeded as planned and that Galileo had successfully departed Earth orbit. The spacecraft was still too far away for detailed telemetry, but tracking data from the Deep Space Network began to indicate that Galileo was indeed on the expected trajectory, climbing away from Earth and beginning its long journey outward. The confirmation came in stages, as various data points were collected and analyzed, and gradually the picture emerged of a spacecraft that was healthy and functioning properly, its systems responding as designed and its orientation stable as it began to encounter the conditions of deep space. The communication checks that followed in the hours and days after deployment provided the mission team with detailed information about Galileo's status. The spacecraft's computer systems were operating normally. Its attitude control thrusters were maintaining the correct orientation, and the power output from its radioisotope thermoelectric generators was within expected parameters. The scientific instruments remained safely stowed for the long cruise phase, protected from the space environment until they would be needed to observe Venus, the asteroids, and ultimately Jupiter itself. The high-gain antenna, folded in its launch configuration, would remain closed until later in the mission, with communications conducted through the low-gain antenna that provided a more limited but still adequate data rate for cruise phase operations. The relief that washed through the mission team at the Jet Propulsion Laboratory was profound and thoroughly earned. Many of the engineers and scientists who had worked on Galileo had done so for the better part of a decade, and some had devoted even longer to the goal of returning American spacecraft to the exploration of Jupiter, a world that had not been visited since the Pioneer and Voyager flybys of the 1970s and early 1980s. Those earlier missions had transformed humanity's understanding of the Jovian system, revealing the volcanic fury of Io, the icy shell of Europa, the ancient battered surface of Callisto, and the complex atmospheres and magnetospheres that characterized this miniature solar system in orbit around the giant planet. But flyby missions could only observe for brief periods as they passed through the system, and the scientific community had long recognized the need for an orbiter that could study Jupiter and its moons repeatedly over an extended period. Galileo represented that opportunity, and its successful launch meant that after years of frustration, the scientific objectives that had motivated the mission might finally be achieved. The press coverage reflected the significance of the moment, with major news organizations reporting on the launch and explaining to the public why this mission mattered for our understanding of the solar system. The fact that Galileo was the first planetary mission ever launched from the Space Shuttle added historical interest to the coverage, as did the complexity of the gravity assist trajectory that would require patience from everyone who awaited the spacecraft's arrival at Jupiter. Journalists explained the Vega trajectory to their audiences, describing how Galileo would fly past Venus once and Earth twice, using the gravity of these planets like a series of catapults to boost its velocity without expending precious fuel. Public interest in the mission was substantial, reflecting the enduring fascination that Jupiter holds in the human imagination. As the largest planet in our solar system, possessing more than twice the mass of all the other planets combined, Jupiter has drawn the attention of observers since ancient times, when its steady brightness in the night sky led various cultures to associate it with their most powerful deities. The Galilean moons, discovered by the namesake of this spacecraft in 1610, had played a crucial role in the development of modern astronomy by providing evidence that not all celestial bodies orbited the Earth. Now, nearly 4 centuries later, a spacecraft bearing Galileo's name would examine those same moons with instruments of remarkable sophistication, seeking to understand the geological and potentially even biological processes that might be operating in these distant worlds. The ISTIS-34 crew continued their mission for several more days after deploying Galileo, conducting other experiments and observations before returning to Earth on October 23. Their landing at Edwards Air Force Base in California marked the successful completion of the deployment phase of the Galileo mission, and the attention of the planetary science community shifted fully to the Jet Propulsion Laboratory, where controllers would guide the spacecraft through the years of cruise operations that lay ahead. The journey to Jupiter would test the patience of everyone involved, as Galileo flew first inward toward Venus, then swung back past Earth twice more, each encounter adding to its velocity and refining its trajectory, before finally entering the realm of the giant planets in late 1995. But all of that lay in the future on this October day in 1989, and for the moment, the predominant feeling among those who had worked so hard to reach this point was simply one of accomplishment and cautious optimism. The spacecraft was healthy, the trajectory was correct, and the mission that had survived budget threats, Challenger, and countless technical challenges was at last underway. The next 6 years would bring their own difficulties and surprises, including the discovery that the high-gain antenna would not fully deploy and that communications would need to be conducted at far lower data rates than originally planned. But the ingenuity that had brought Galileo to this launch would prove equal to those future challenges as well, and the scientific return from the mission would ultimately exceed what many had dared to hope. As the autumn of 1989 gave way to winter, Galileo continued its silent journey through the inner solar system, its trajectory curving toward the first gravity assist at Venus, its instruments quiescent but ready, its mission finally and truly begun. The 12 years of development and delay were now history, recorded in filing cabinets and human memories, and ahead lay only the vast distances of space and the promise of discovery at a world that had captivated human curiosity for millennia. The spacecraft that bore the name of the great Italian astronomer was on its way, carrying the hopes of a generation of scientists and the sophisticated instruments that would reveal Jupiter and its moons as never before, and the night sky through which it traveled held no judgment of the struggles that had preceded this journey, only the ancient light of distant stars and the patient orbit of the destination that awaited. On the 10th of February in the year 1990, some 4 months after departing from Earth aboard the Space Shuttle Atlantis, the Galileo spacecraft found itself approaching a world that had never been part of its original scientific agenda, yet would nonetheless offer an unexpected gift of discovery. Venus, that brilliant morning and evening star that has captivated human observers since the earliest days of our species, hung in the darkness of space some 108 million kilometers from the Sun, shrouded in its perpetual veil of thick sulfuric acid clouds, and Galileo was drawing ever closer to this mysterious neighbor of ours. The spacecraft would pass within 16,106 kilometers of the Venusian surface, threading through the gravitational influence of that cloud-wrapped world in a carefully calculated maneuver that would fundamentally alter its trajectory through the inner solar system. This encounter was not about Venus itself, not primarily, for Galileo had been built and designed and lovingly prepared for the distant realm of Jupiter, where the giant planet and its family of fascinating moons awaited exploration. Yet space missions, like so many endeavors of human curiosity, often yield their richest rewards in the unplanned moments, in the opportunities that arise when we are simply passing through. The concept of a gravity assist, which formed the essential purpose of this Venus encounter, is one of those elegantly simple ideas in orbital mechanics that nonetheless requires a moment of patient contemplation to fully appreciate. When a spacecraft approaches a planet, it enters into a kind of gravitational conversation with that world, falling toward it under the influence of that invisible attractive force that governs the motion of all massive bodies throughout the cosmos. As the spacecraft swings around the planet, curving through space along a hyperbolic trajectory, it is temporarily captured in a gravitational embrace before continuing onward into the void. Now, if the planet were stationary, perfectly fixed in space, the spacecraft would depart with exactly the same speed relative to the planet as it had upon arrival, merely redirected in its path. But planets are not stationary, of course, for they themselves are moving through space in their own vast orbits around the Sun. And this motion is the key to understanding how gravity assists actually function. Venus, on that February day in 1990, was traveling through space at approximately 35 kilometers per second in its endless circuit around our star. When Galileo approached Venus from behind, matching its direction of travel and then swinging around the planet, it essentially borrowed a small portion of Venus's orbital momentum. The spacecraft departed the encounter moving faster relative to the Sun than it had been moving before, having extracted energy from the planet's motion through the simple expedient of falling through its gravitational field at just the right angle. One might wonder, in those quiet moments before sleep, whether Venus noticed this tiny theft of momentum, this infinitesimal slowing of its own orbital velocity. The answer, reassuringly, is that while the effect does technically exist, the mass difference between a planet and a spacecraft is so extraordinarily vast that Venus's orbit was altered by an amount far too small to measure, a change so minute that it vanishes into the background noise of gravitational perturbations from other bodies in the solar system. For Galileo, however, the effect was quite significant indeed. The spacecraft gained approximately 2.5 kilometers per second of velocity relative to the Sun through this encounter, a boost that would be essential for its subsequent journey back toward Earth and eventually outward to Jupiter. Without this assistance from Venus's gravity, the Centaur upper stage that had propelled Galileo away from Earth would have needed to be considerably more powerful, and the mission architecture would have been substantially different. The gravity assist technique, first demonstrated in practice by the Mariner 10 mission to Mercury in 1974, had become by Galileo's time a standard tool in the mission planner's repertoire, though it remained, and remains still, a rather beautiful example of working with nature rather than against it, of using the gravitational architecture of our solar system as a kind of interplanetary transport network. The trajectory that brought Galileo to Venus had been calculated years in advance, worked out with extraordinary precision by the navigation specialists at the Jet Propulsion Laboratory in Pasadena, California. These calculations had to account for the positions of Venus and Jupiter at various points in time, seeking an alignment that would allow Galileo to use multiple gravity assists to build up sufficient velocity for the journey to the outer solar system. The path that emerged from these calculations was known as the Venus-Earth-Earth gravity assist trajectory, often abbreviated simply as VEGA, a route that would take Galileo first inward toward Venus, then back to Earth not once but twice, before finally heading outward toward its ultimate destination. Each of these encounters would add energy to Galileo's orbit, gradually transforming a relatively modest initial velocity into the tremendous speed needed to reach Jupiter in a reasonable amount of time. It was a journey measured not in the straight lines that our intuition might prefer, but in graceful curves and loops that took full advantage of the celestial mechanics governing our solar system. As Galileo approached Venus in the days leading up to the closest encounter, the mission controllers and scientists found themselves presented with an opportunity that had not been extensively planned during the spacecraft's development. The encounter had always been intended primarily as a navigational maneuver, a means to an end rather than an end in itself, and the scientific instruments aboard Galileo had been designed and optimized for conditions at Jupiter, not the quite different environment of Venus. The temperature near Venus, for instance, posed potential concerns for a spacecraft whose thermal design had been prepared for the frigid outer reaches of the solar system, and the intense sunlight at Venus's orbital distance was more than twice as strong as what Galileo would experience at Earth. Nevertheless, the scientists involved in the mission recognized that passing so close to another planet, any planet, represented a chance for observation that ought not be wasted. And so, in the months before the encounter, plans were developed to turn Galileo's instruments toward Venus and gather what data they could, transforming a gravity assist into a genuine scientific flyby. This flexibility, this willingness to embrace unexpected opportunities, would prove to be one of the hallmarks of the Galileo mission throughout its long operational life. The observations that Galileo conducted during its passage by Venus focused considerably on the planet's thick atmosphere, that dense and chemically complex envelope of gases that completely obscures the surface from view in visible light. Venus's atmosphere is composed primarily of carbon dioxide, with thick clouds of sulfuric acid droplets floating at altitudes between roughly 45 and 70 kilometers above the surface, creating a greenhouse effect so powerful that surface temperatures reach nearly 470 degrees Celsius, hot enough to melt lead. From Earth, and from previous spacecraft that had visited Venus, scientists had built up a picture of this hostile world. But Galileo carried instruments that could contribute new perspectives, particularly in the infrared portion of the electromagnetic spectrum. The near-infrared mapping spectrometer aboard Galileo, designed to study the composition of Jupiter's moons, proved capable of peering through certain gaps in Venus's cloud cover, wavelengths at which the clouds became somewhat transparent, allowing infrared radiation from deeper in the atmosphere to escape into space. What the instrument revealed was a planet far more dynamic than its uniform cloud tops might suggest. The infrared observations conducted by Galileo during the Venus encounter detected what scientists described as hot spots, regions where thermal radiation from the lower atmosphere and possibly from the surface itself was escaping through thinner portions of the cloud deck. These observations helped to refine our understanding of the vertical structure of Venus's atmosphere, the way temperature varies with altitude, and the manner in which the cloud layers are distributed around the planet. The clouds of Venus, it became clear, were not a simple uniform blanket but rather a complex and variable layer whose properties changed from place to place, sometimes thinning enough to allow glimpses of the furnace-like conditions below. For the scientists analyzing this data, the Venus flyby provided a valuable complement to previous missions, adding another set of observations from yet another viewing geometry, another time, another set of instruments. Knowledge of planetary atmospheres, like knowledge of most natural phenomena, accumulates gradually through just this kind of repeated observation, each mission adding its own small contributions to the ever-growing edifice of understanding. Perhaps the most intriguing discovery that emerged from Galileo's brief visit to Venus was the detection of lightning in the planet's atmosphere. Lightning, that dramatic electrical discharge so familiar to us from thunderstorms on Earth, had been a matter of some controversy regarding Venus. Previous Soviet Venera landers had reported possible detections of lightning as they descended through the atmosphere in the 1970s and 80s, but the evidence remained ambiguous, and some scientists questioned whether the instruments might have been detecting other phenomena instead. The Pioneer Venus orbiter had also searched for signs of electrical activity without producing definitive results. Galileo, however, carried instruments that were well suited to detecting the optical flashes and radio emissions associated with lightning, and during the flyby, these instruments recorded evidence that strongly supported the presence of lightning in Venus's thick clouds. The spacecraft's solid-state imaging camera, though primarily designed for the very different conditions at Jupiter, captured brief flashes of light from the night side of Venus that were consistent with electrical discharges occurring deep within the cloud layers. Meanwhile, the plasma wave instrument detected radio signals of the type typically produced by lightning activity. The confirmation of lightning on Venus told scientists something important about the meteorological processes occurring within that world's massive atmosphere. Lightning on Earth is generated by the movement of charged particles within storm clouds, where strong updrafts and downdrafts create the conditions for charge separation and eventual electrical breakdown of the air. The presence of similar phenomena on Venus suggested that despite the very different composition and structure of its atmosphere, dynamic processes were at work that shared at least some fundamental similarities with terrestrial weather. The clouds of Venus, it seemed, were not merely passive layers of sulfuric acid mist but active participants in an atmospheric circulation driven by solar heating and planetary rotation. For a spacecraft on its way to Jupiter, where lightning had also been detected by the Voyager missions, this Venus observation provided a useful preview of the kinds of electrical phenomena that might be encountered in the giant planet's far more massive atmosphere. The solar system, these observations quietly suggested, operates according to a consistent set of physical principles that manifest themselves in recognizable ways even when the specific conditions vary enormously from world to world. The fact that the Venus science was not originally planned as a major component of the Galileo mission makes it all the more satisfying to contemplate. In that gentle way one contemplates things when preparing for rest. The mission team adapted to circumstances, recognized an opportunity, and made the most of what they had available. This is, in many ways, the essence of good exploration, whether one is navigating the solar system or simply finding one's way through the ordinary challenges of daily existence. Plans are important, certainly, for without plans the Venus encounter would never have occurred at all. But flexibility and attentiveness to unexpected possibilities are equally valuable qualities. The scientists and engineers who operated Galileo demonstrated both, turning a navigational waypoint into a genuine scientific contribution to our understanding of Venus. Following the closest approach to Venus, as Galileo began its outward journey back toward the orbit of Earth, the mission controllers conducted a series of trajectory correction maneuvers to fine-tune the spacecraft's path. These small adjustments, accomplished by firing Galileo's onboard thrusters for carefully calculated durations, ensured that the spacecraft would arrive at precisely the right place and time for its upcoming encounter with Earth. The trajectory emerging from any gravity assist, while calculated with great accuracy beforehand, always requires some post-encounter refinement based on the actual tracking data received from the spacecraft. Tiny differences between the predicted and actual conditions, perhaps in the exact mass distribution within Venus or the precise state of the spacecraft at closest approach, accumulate into trajectory errors that must be corrected if the subsequent portions of the mission are to succeed. For Galileo, these corrections were accomplished smoothly, the thrusters responding as expected, the navigation team confirming that the spacecraft was on course for its next destination. The health of the spacecraft following the Venus encounter was a matter of considerable interest to the mission team. particularly given the thermal concerns associated with approaching so close to the Sun. At Venus's orbital distance, the solar intensity is approximately 1.9 times what it is at Earth, meaning that Galileo's thermal control systems had to work somewhat harder to maintain appropriate temperatures throughout the spacecraft. The mission controllers conducted careful checks of all major systems following the flyby, examining the data returned by the spacecraft's engineering sensors, looking for any signs of thermal stress or other anomalies that might have resulted from the encounter. The results were reassuring, with all systems reporting nominal function, all temperatures within acceptable ranges, all instruments performing as expected. Galileo had passed its first major test of the interplanetary journey, demonstrating that its design was robust enough to handle not only the cold of deep space but also the relative warmth of the inner solar system. This confidence in the spacecraft's health would prove valuable in the years ahead, as Galileo faced challenges that its designers had never fully anticipated. With the Venus encounter successfully completed, Galileo settled into a long cruise phase that would eventually bring it back to the vicinity of Earth. The distance to be traveled was considerable, and the spacecraft would need 947 days to complete this portion of its journey before the first of 2 planned Earth flybys. Nearly 3 years of patient waiting lay ahead, 3 years during which the spacecraft would continue its silent journey through the void, its instruments occasionally gathering data on the solar wind and cosmic ray environment, its radio transmitting health and status information back to the attentive ears of the Deep Space Network. For those following the mission, this cruise phase required a kind of patience quite different from the intense activity surrounding planetary encounters, a willingness to trust in the spacecraft and the calculations that guided it, knowing that the next significant milestone was still many months away. The cruise phase of an interplanetary mission is a time of quiet activity, not idleness but rather a steady rhythm of routine operations punctuated by occasional instrument calibrations and trajectory corrections. The mission controllers monitor the spacecraft's health, tracking its temperature, power levels, and the status of its various subsystems. The navigation team continues to refine the trajectory, using radiometric tracking data to determine the spacecraft's precise position and velocity, comparing these measurements against predictions and making small adjustments as needed. The science team reviews the data collected during planetary encounters, writing papers, presenting results at conferences, and planning for future observations. All of this work proceeds at a measured pace, without the urgency that accompanies close planetary approaches, in what might be thought of as the spacecraft's version of ordinary daily life. For Galileo, the 947 days following Venus would include all of these activities and more, as the spacecraft gradually made its way back toward Earth for the first gravity assist from its home planet. And so we leave Galileo for now, having watched it swing past Venus and gain the velocity it needed for the next stage of its journey. The spacecraft has proven itself capable of operating in the inner solar system. Its instruments have contributed unexpected science to our understanding of Venus, and the path to Jupiter remains clear. In the darkness of interplanetary space, Galileo continues its patient flight, its high-gain antenna folded, its instruments largely dormant, its nuclear power source steadily providing the electricity needed to keep its systems alive. The stars will slowly around the spacecraft as it rotates gently for thermal control, and the Sun grows gradually smaller as the distance increases. Earth lies ahead, still many months distant, and beyond Earth lies Jupiter, the ultimate destination, where wonders await that will occupy the spacecraft for years to come. But those discoveries belong to the future. And for now, there is only the quiet journey, the steady accumulation of distance, and the patient ticking of the onboard clock counting down the days until the next encounter. 947 days, each one bringing Galileo a little closer to home, each one carrying it forward along the elegant trajectory that human ingenuity had calculated and celestial mechanics would faithfully execute. The Venus detour was complete, the first gravity assist accomplished, and the long voyage continued onward through the serene and silent reaches of space. On the 11th of April, 1991, the Galileo spacecraft was making its way through the inner solar system, having completed its first gravity assist maneuver around Venus and beginning the long journey that would eventually carry it to Jupiter. The spacecraft had been traveling for nearly 18 months by this point, and the time had come to unfurl one of its most important components, the high-gain antenna that would serve as the primary means of communication between Galileo and the scientists waiting patiently on Earth. This antenna, when fully deployed, would measure 4.8 meters across, roughly the width of a small room, and it was designed to send back the treasures of data that the spacecraft would gather as it explored the Jovian system. The deployment command was sent, and the team waited with the quiet anticipation that accompanies any significant spacecraft operation, expecting the antenna to bloom open like a great metallic flower turning toward the distant sun. What happened instead would become one of the most significant equipment failures in the history of planetary exploration, though the word failure perhaps does not capture the complexity of what occurred, nor does it account for the remarkable human response that would follow. The antenna, you see, was designed somewhat like an umbrella, with 18 slender ribs that were meant to swing outward and pull with them a mesh of gold-plated molybdenum wire, creating a large parabolic dish that could focus radio signals with extraordinary precision. When the deployment mechanism was activated on that April day, the spacecraft dutifully attempted to carry out its instructions, and the ribs began their outward journey. But only 15 of the 18 ribs moved into their proper positions, while 3 ribs remained stubbornly in place, held fast by forces that no one on Earth could see or touch from hundreds of millions of kilometers away. The antenna was stuck in a partially opened configuration, resembling nothing so much as an umbrella that had been caught in a gentle wind and refused to open fully. This was not a dramatic explosion or a sudden loss of signal, but rather a quiet mechanical stubbornness that would have profound implications for the entire mission. The engineers and scientists who received the telemetry data from Galileo could see clearly what had happened, even though they could not yet understand why. 3 ribs had not deployed, and no amount of wishing or hoping would change that simple fact. The spacecraft continued on its trajectory, utterly indifferent to the consternation it was causing among the humans who had built it, and the partially opened antenna cast its incomplete shadow as Galileo sailed through the darkness of space. The investigation into what had caused this malfunction began immediately, with engineers at the Jet Propulsion Laboratory and at Hughes Aircraft Company, which had built the antenna, working methodically to understand how such a carefully designed mechanism could have failed. The antenna had been tested extensively before launch, as all spacecraft components must be, and it had functioned perfectly during those tests. The ribs were held in place by pins that were designed to release when the deployment command was given, allowing small motors to drive the ribs outward along carefully machined tracks. Each rib was fitted with a standoff pin that would release from a cup as the rib moved, and these pins were coated with a dry lubricant to ensure smooth operation. The lubricant used was a bonded molybdenum disulfide compound, chosen specifically because it would perform well in the vacuum and temperature extremes of space. What the investigation eventually revealed was both mundane and heartbreaking in its simplicity. The lubricant had worn away from the standoff pins, not through any dramatic failure or design flaw, but simply through the passage of time and the accumulation of small movements. Galileo had originally been scheduled to launch in 1986, and the antenna had been built and tested well before that date. But then the Space Shuttle Challenger had been lost in January of that year, taking with it 7 crew members and throwing the entire American space program into a period of profound re-examination. The shuttle fleet was grounded for 32 months, and Galileo, which was designed to be launched from the shuttle's payload bay, waited in storage at the Kennedy Space Center. During this extended period, the spacecraft was moved multiple times, transported from one facility to another, and subjected to the vibrations of trucks and cranes and handling equipment. Each time the spacecraft was moved, the standoff pins experienced tiny movements against their cups, back and forth, small enough to be imperceptible but large enough to gradually abrade the thin coating of lubricant that protected them. By the time Galileo finally launched in October of 1989, some of those pins had lost enough lubricant that they had effectively become welded to their cups through a process called cold welding or fretting corrosion. In the vacuum of space, without the protective oxide layer that forms on metal surfaces in Earth's atmosphere, clean metal surfaces that touch each other can bond at the atomic level. 3 of the standoff pins had become so thoroughly stuck that the relatively small force of the deployment motors could not break them free, and so 3 ribs remained in place while their 15 companions unfurled as designed. The engineers who had built the antenna felt the weight of this discovery with particular keenness, for they had created something beautiful and functional, something that had worked perfectly in testing, only to see it fail because of circumstances entirely beyond their control. The delay caused by the Challenger accident was no one's fault, certainly not theirs, and yet the antenna they had crafted with such care would never fulfill its intended purpose. There is a particular kind of grief that comes from watching something you have made fall short of its potential, and the antenna team experienced this fully as the investigation confirmed what had gone wrong. They had done everything right, and it had not been enough, and now the spacecraft they had helped to build would have to find another way to accomplish its mission. But the story does not end with this quiet tragedy, for the engineers at the Jet Propulsion Laboratory were not inclined to accept defeat, and they began almost immediately to explore whether the antenna might yet be coaxed into opening. The first attempts were straightforward, simply sending the deployment command again and again, hoping that some small shift in the mechanism might allow the stuck ribs to break free. Each time, the telemetry returned the same disappointing news: 15 ribs deployed, 3 ribs stuck, no change. The engineers then tried more creative approaches, including a technique that came to be called sunbathing, in which the spacecraft was oriented so that the partially opened antenna would be alternately heated by the sun and cooled by the shadow of the spacecraft body. The theory was that thermal expansion and contraction might create enough movement in the mechanism to free the stuck pins, much as you might work a stuck jar lid by running it under hot water. Over the course of many months, the spacecraft was put through thousands of cycles of heating and cooling, and the deployment command was sent again and again. The engineers tried pulsing the deployment motors in various patterns, hoping to build up momentum that might overcome the friction holding the pins in place. They attempted to spin the spacecraft to create centrifugal forces that might help pull the ribs outward. Each attempt was methodical and patient, conducted with the understanding that any solution would have to work across the vast distance of space, using only the limited mechanisms available on the spacecraft. The engineers could not send someone to tap on the antenna with a wrench or spray lubricant on the stuck parts. They could only send commands and wait for the telemetry that would tell them whether anything had changed. Nothing changed. By 1993, after more than 2 years of troubleshooting attempts, the team had to accept that the high-gain antenna would never fully deploy. The 3 stuck ribs had been welded in place too thoroughly to be freed by any method available to them, and the partially opened antenna could not be used for its intended purpose. The mesh of gold-plated wire that was supposed to form a precise parabolic surface was instead a crumpled and incomplete shape, incapable of focusing radio signals with any useful accuracy. The high-gain antenna, which had been designed to transmit data at 134 kilobits per second, would remain a silent monument to what might have been, and the mission would have to find another way to communicate with Earth. The alternative was the low-gain antenna, a much simpler device that had been included on the spacecraft primarily as a backup for basic housekeeping communications. This antenna had no moving parts to fail, no ribs to deploy, no lubricant to wear away. It was simply a small omnidirectional transmitter that could send signals in all directions at once. The trade-off for this simplicity and reliability was a dramatic reduction in data transmission capability. While the high-gain antenna could have sent data at 134,000 bits per second, the low-gain antenna could manage only between 10 and 160 bits per second, depending on the distance between the spacecraft and Earth. At its best, this was roughly 1,000 times slower than what the high-gain antenna would have provided, and at its worst, it was more than 10,000 times slower. To put this in perspective, a single image from Galileo's camera might contain several million bits of data. Using the high-gain antenna, such an image could have been transmitted in less than a minute. Using the low-gain antenna at its fastest rate, the same image would take several hours to transmit, and at the slowest rates, it might take more than a day. If nothing were done to address this limitation, the mission's scientific return would be reduced by approximately 99% compared to what had been planned. Instead of returning tens of thousands of images and vast quantities of scientific data, Galileo would be able to send back only a tiny fraction of what its instruments could gather. The mission would still function, technically speaking, but it would be a shadow of what it was meant to be. This was the situation that confronted the engineers at the Jet Propulsion Laboratory, and their response to it stands as one of the most impressive examples of creative problem-solving in the history of space exploration. They could not fix the antenna, but they could change the way the spacecraft used the antenna it had, and they could change the way the data was prepared before transmission. The solution would require rewriting essentially all of the flight software on the spacecraft, implementing sophisticated data compression algorithms that had never been designed to run on Galileo's aging computers, and developing new ground-based signal processing techniques that could extract every possible bit of information from the weak signals that the low-gain antenna would send. The compression scheme that the engineers developed was elegant in its approach, though demanding in its implementation. Rather than simply transmitting raw data from the instruments, the spacecraft would first analyze the data and remove redundant or unimportant information. Images, for example, contain substantial redundancy, with adjacent pixels often having very similar values. By encoding only the differences between pixels rather than the absolute value of each pixel, significant compression could be achieved. Similarly, for scientific data, The spacecraft could perform preliminary analysis on board and transmit only the most scientifically valuable information rather than every measurement from every instrument. The engineers also developed techniques for handling data that had been corrupted during transmission, which became increasingly important given the weak signal from the low-gain antenna. Error-correcting codes were implemented that allowed the ground stations to reconstruct data even when a significant portion of the transmission had been lost to noise. The Deep Space Network, the array of large radio antennas that NASA uses to communicate with distant spacecraft, was enhanced with new receivers that were specifically optimized for the weak signals from Galileo. Multiple antennas were sometimes linked together to create a virtual antenna with greater sensitivity than any single dish could provide. The software that implemented all of these techniques had to be written for a computer that was, by the standards of the early 1990s, already quite antiquated. Galileo's main flight computer used technology that had been state-of-the-art in the 1970s. With processing power and memory that would be considered laughably inadequate for even simple applications today. Writing sophisticated compression algorithms for such limited hardware required extraordinary ingenuity, and the engineers who accomplished this task did so under the constant pressure of knowing that the spacecraft was getting closer to Jupiter with each passing day. The new software was uploaded to the spacecraft across millions of kilometers of space, and it worked, transforming Galileo from a crippled mission into one that could still accomplish remarkable science. When all of these techniques were combined, the data return from Galileo was reduced by approximately 70% compared to the original plans, rather than the 99% reduction that would have occurred without any intervention. This was still a significant loss, and there were surely images that were never taken and measurements that were never made because there simply was not enough bandwidth to transmit them. But 70% of a mission is vastly more than 1% of a mission, and the scientific discoveries that Galileo ultimately made at Jupiter were transformative in their importance. The images of volcanic eruptions on Io, the evidence for a subsurface ocean on Europa, the detailed studies of Jupiter's atmosphere and magnetic field, all of these were possible because of the work that was done to overcome the stuck antenna. The experience of the Galileo mission also led to innovations that would benefit future spacecraft. For the data compression and signal processing techniques that were developed in response to the antenna failure proved useful in many subsequent applications. The engineers who had faced this challenge had been forced to think deeply about how to extract maximum value from limited communication bandwidth, and the solutions they developed became part of the standard toolkit for deep space exploration. In this way, the malfunction that had seemed so devastating in 1991 became a source of knowledge that would help future missions succeed. There is something quietly reassuring about this story, something that speaks to the resilience of human ingenuity in the face of unexpected difficulties. The antenna failure was real, and the loss it represented was genuine, but it did not end the mission or render the spacecraft useless. Instead, it prompted a creative response that, while not restoring what had been lost, found a new path forward that preserved much of what the mission had hoped to achieve. The engineers who accomplished this did so not through any single brilliant insight but through the steady accumulation of many small improvements, each one contributing to the overall solution. They worked patiently and methodically, as engineers do, and they did not give up when the first attempts at fixing the antenna failed, or the 10th, or the 100th. They simply kept working, and eventually they found a way. The Galileo spacecraft continued on its journey to Jupiter, carrying with it the partially opened antenna that would never fully deploy, along with the new software that would allow the mission to succeed despite this limitation. The 3 stuck ribs remained in place throughout the mission, a permanent reminder of the lubricant that had worn away during those long months of waiting after Challenger, and of the unforeseen consequences that can flow from events that seem, at the time, to have nothing to do with the systems they ultimately affect. The spacecraft arrived at Jupiter in 1995, 4 years after the antenna failure, and it proceeded to conduct a mission that, while different from what had been originally planned, was nonetheless one of the most scientifically productive planetary explorations ever undertaken. The images came back slowly, a few bits at a time, but they came back, and they showed us wonders that we had never imagined. In the autumn of 1991, as the Galileo spacecraft continued its long and winding journey toward Jupiter, mission controllers at the Jet Propulsion Laboratory prepared for an encounter that had never before been attempted in the history of space exploration. On the 29th of October of that year, the spacecraft would pass close by a small rocky body tumbling through the darkness of the asteroid belt, an object known to astronomers as 951 Gaspra, and in doing so would become the first human-made object ever to conduct a close flyby of an asteroid. This encounter, though secondary to the primary mission of studying Jupiter and its moons, represented a milestone of considerable significance, for it would provide the first detailed glimpse of one of the countless small worlds that populate the vast region between the orbits of Mars and Jupiter, objects that had previously been visible only as points of light even through the most powerful telescopes on Earth. The asteroid that Galileo would visit had first been identified 3/4 of a century earlier, in 1916, when a Russian astronomer named Grigory Neujmin detected a faint moving speck against the background stars while conducting observations at the Symiz Observatory on the Crimean Peninsula. Neujmin named his discovery after Gaspra, a resort town on the Black Sea coast where the Russian writer Leo Tolstoy had once stayed, and where Neujmin himself had spent time during summer holidays. 4 decades following its discovery, Gaspra remained little more than a catalogue entry, a numbered object whose orbit could be calculated but whose physical characteristics could only be guessed at through indirect measurements of its brightness and the way that brightness varied as the asteroid rotated. No telescope on Earth could resolve any details of its surface, for even at its closest approach to our planet, Gaspra appeared as nothing more than a dimensionless point of light, its secrets hidden by the vast distances of interplanetary space. The Galileo mission planners had recognized early in the design phase that the spacecraft's circuitous route to Jupiter, necessitated by the change from a direct trajectory to one involving multiple gravity assists from Venus and Earth, would carry it twice through the inner portion of the asteroid belt. This circumstance, which arose from the unfortunate necessity of using a less powerful upper stage following the Challenger accident, turned out to offer an unexpected opportunity, for it meant that the spacecraft might be directed to pass close by one or more asteroids if suitable candidates could be found along or near its flight path. After careful analysis of the orbital mechanics involved, mission planners identified Gaspra as an accessible target that could be reached with only minor adjustments to the spacecraft's trajectory, and so the first asteroid flyby in history became an official part of the Galileo mission. As the encounter date approached, the spacecraft began a carefully choreographed sequence of observations, turning its scan platform to aim its suite of instruments toward the small rocky world that was growing slowly larger in its field of view. The approach velocity was approximately 8 kilometers per second, which is to say that the spacecraft was closing the distance to Gaspra at a rate of about 29,000 kilometers per hour, a speed that would allow only a brief window for close observations but which could not be significantly reduced without expending far more propellant than the mission could spare. At 8 kilometers per second, The entire close encounter would last only minutes, and so every second of imaging time had to be carefully planned and precisely executed. The closest approach occurred at a distance of 1,601 kilometers from the center of the asteroid, close enough for the cameras to resolve features as small as a few tens of meters across, yet far enough to ensure no risk of collision with the tumbling body or any debris that might surround it. At this distance, Gaspra filled a significant portion of the camera's field of view, and for the first time in history, human eyes would see an asteroid not as a point of light but as a world unto itself, with surface features and a distinct three-dimensional shape. The moment was one of quiet triumph for the engineers and scientists who had worked for years to make it possible, though they would have to wait some time to see the results of their efforts, for the images and data collected during the flyby could not be transmitted immediately to Earth. The high-gain antenna problem that had revealed itself earlier in the mission meant that data transmission was painfully slow, limited to the trickle that could be managed through the low-gain antenna system. This constraint meant that the precious images of Gaspra would have to be stored on the spacecraft's tape recorder and transmitted back to Earth over a period of many months, with the highest priority images sent first and the remainder following in order of scientific importance. Despite these limitations, the spacecraft managed to capture 57 images of Gaspra during the encounter, a number that would provide scientists with an unprecedented look at the small body and allow them to construct a detailed picture of its shape, surface features, and composition. When the first images of Gaspra finally arrived at Earth and were processed by the imaging team, they revealed a world quite unlike anything that had been seen before in such detail. The asteroid presented an irregular, elongated shape, somewhat reminiscent of a potato or perhaps a misshapen lump of rock-studded bread dough, measuring approximately 19 kilometers along its longest axis, 12 kilometers across its intermediate dimension, and 11 kilometers in its shortest extent. This pronounced asymmetry was consistent with the prevailing theories about asteroid formation and evolution, which suggested that most asteroids are not spherical like the larger planets and moons, but are instead irregularly shaped fragments, either remnants of larger bodies that were shattered by ancient collisions or primordial rubble that never accumulated enough mass for gravity to pull it into a spherical shape. The surface of Gaspra, as revealed in the Galileo images, was marked by numerous small craters, the scars left by countless impacts with smaller objects over the long history of the solar system. These craters ranged in size from the limit of the camera's resolution up to a few kilometers across, though notably absent were any very large craters that might have been expected if Gaspra had been exposed to the full bombardment of the asteroid belt for the entire 4.5 billion-year history of the solar system. This relative paucity of large craters led scientists to conclude that the surface of Gaspra was considerably younger than the solar system itself, and careful analysis of the crater population, comparing the observed crater density to theoretical models of the impact rate in the asteroid belt, yielded an estimated surface age of approximately 200 million years. This age estimate suggested that Gaspra might be a relatively recent fragment, broken off from a larger parent body by a catastrophic impact sometime in the Triassic period, when dinosaurs were just beginning their rise to dominance on Earth. The fresh surface, geologically speaking, would explain why the asteroid showed so few of the large craters that accumulate over billions of years of exposure to the constant rain of smaller debris that permeates interplanetary space. In this interpretation, Gaspra was not a primordial remnant from the formation of the solar system, but rather second or third generation object, a piece of whatever original material had coalesced in this region of the solar nebula so long ago. In addition to the craters, The images revealed a pattern of subtle grooves and linear features running across portions of Gaspra's surface, suggesting that the interior of the asteroid might be fractured or perhaps composed of loosely consolidated material rather than solid monolithic rock. These grooves, some of which extended for several kilometers across the surface, appeared to trace lines of structural weakness within the body, possibly the result of impacts that had shaken the asteroid without breaking it apart entirely. The presence of such features hinted at a complex internal structure, perhaps one in which large blocks of material were held together primarily by their own weak gravity rather than by the cohesive strength of solid rock. And this interpretation would later be supported by observations of other asteroids that showed similar evidence of internal fracturing and loose aggregation. The spectroscopic observations made during the flyby confirmed that Gaspra belonged to a category known as S-type asteroids, which are characterized by surfaces rich in silicate minerals and metals, particularly iron and nickel mixed with various rocky compounds containing silicon and oxygen. S-type asteroids are among the most common in the inner portion of the asteroid belt, and they are thought to represent material that was heated and at least partially differentiated early in the history of the solar system, perhaps forming the outer layers or fragments of small bodies that never quite became full-fledged planets. The metallic and silicate composition suggested that Gaspra might be related to the stony iron meteorites that occasionally fall to Earth, providing a direct link between the distant objects observed by spacecraft and the samples that scientists could study in their laboratories. The project scientist for the Galileo mission, Torrance Johnson, who had devoted years of his career to planning and overseeing the scientific investigations of this ambitious endeavor, experienced a moment of profound satisfaction when the first processed images of Gaspra appeared on the monitors at the Jet Propulsion Laboratory. After years of delays and setbacks, after the Challenger tragedy and the antenna malfunction and all the other obstacles that had threatened to diminish the mission's scientific return, here at last was something entirely new, an image of a world that no human had ever seen clearly before. Johnson described the experience as deeply moving, the culmination of so much effort and the vindication of the decision to include asteroid encounters in the mission plan despite the complexities they added to an already demanding flight profile. For Johnson and his colleagues, the images of Gaspra represented more than just a scientific achievement, though they were certainly that as well. They represented a new way of understanding the small bodies of the solar system, a transition from abstract points of light in astronomical catalogues to tangible worlds with surfaces and shapes and histories of their own. Each crater on Gaspra told a story of an ancient impact. Each groove hinted at forces that had shaped the asteroid over millions of years, and each measurement of composition added another piece to the puzzle of how the solar system had formed and evolved. The encounter demonstrated that asteroids, far from being mere debris cluttering the space between the planets, were worthy subjects of scientific study in their own right, each one a frozen record of processes that had shaped the early solar system. The success of the Gaspra flyby had implications that extended well beyond the immediate scientific results, for it served to validate the entire concept of asteroid encounter missions and demonstrated that such flybys could be accomplished reliably with the technology available at the time. Prior to Galileo's visit to Gaspra, no spacecraft had ever attempted a close approach to an asteroid, and there had been legitimate questions about whether such encounters could be planned and executed with sufficient precision to yield useful scientific data. The successful navigation to within 1,600 kilometers of a small, irregularly shaped target tumbling through space at a relative velocity of 8 kilometers per second showed that the techniques of celestial mechanics and spacecraft guidance had reached a level of sophistication adequate to the task, and this demonstration would pave the way for future missions dedicated entirely to asteroid exploration. In the years following the Gaspra encounter, space agencies around the world would launch numerous missions to study asteroids, including the near Shoemaker mission that would later orbit and land on the asteroid Eros, the Japanese Hayabusa missions that would return actual samples from asteroids to Earth, and the OSIRIS-RX mission that would collect material from the asteroid Bennu and return it for laboratory analysis. All of these later achievements built upon the foundation laid by Galileo's brief but historic visit to Gaspra, which showed that such missions were not only possible but scientifically valuable. The images and data from that October encounter in 1991 opened a door that would never close again, establishing asteroid science as a vibrant field of planetary exploration. The 57 images captured during the flyby, though a relatively modest number by the standards of later missions, provided enough coverage to allow scientists to construct a detailed shape model of Gaspra and to map the distribution of craters and other features across most of its visible surface. These images were transmitted back to Earth over many months using the low-gain antenna, each one representing hours of precious communication time, but each one also adding to the growing understanding of this small rocky world. The patience required to receive this data, waiting week after week for each new image to trickle down from space, was a testament to the dedication of the mission team and the value they placed on every bit of scientific return the crippled spacecraft could provide. The shape of Gaspra, with its elongated potato-like profile, became iconic in the years following the encounter, appearing in textbooks and popular accounts of solar system exploration as the prototype of what an asteroid looks like up close. This shape, so different from the spherical forms of larger planetary bodies, illustrated dramatically the way that gravity dominates the structure of large objects, pulling them into spheres, while smaller objects retain whatever irregular shapes they happen to acquire through the random processes of accretion and fragmentation. Gaspra was large enough to have noticeable gravity, enough to hold loose material against its surface, but not nearly large enough for that gravity to have crushed and rounded the body into a symmetric form. The rotation of Gaspra, which carries it through one complete turn every 7 hours or so, was already known from Earth-based observations of its varying brightness, but the Galileo images allowed scientists to determine the orientation of the rotation axis and to understand how the asteroid's irregular shape affected the pattern of illumination across its surface. As Gaspra tumbles through space, different faces are presented to the Sun, creating a complex pattern of shadows that shifts and changes over the course of each rotation period. The careful timing of the flyby ensured that the spacecraft could image portions of the asteroid that were illuminated during the encounter, maximizing the scientific value of the brief observing window available. The encounter with Gaspra, brief as it was, demonstrated something profound about the nature of exploration, showing that even a quick passage by a distant object could yield scientific treasures if the instruments were capable and the planning was careful. The spacecraft had spent only minutes in the close vicinity of the asteroid, yet the data gathered in those minutes would occupy researchers for years, providing insights into asteroid composition, structure, and evolution that could never have been obtained from Earth-based observations alone. This economy of exploration, the ability to extract maximum scientific value from limited encounter time, would become increasingly important as missions ventured ever deeper into the solar system, where communication delays and limited resources demanded the most efficient possible use of every opportunity. As Galileo continued on its journey following the Gaspra encounter, leaving the small asteroid behind to resume its solitary orbit around the Sun, the mission team could reflect with satisfaction on what had been accomplished. They had visited a place where no spacecraft had ever been before, had taken the first close-up photographs of a type of solar system body that represents the most numerous class of objects orbiting our star, and had proven that such encounters could be performed safely and productively. The data was still flowing back, image by image through the narrow bandwidth of the low-gain antenna, but already it was clear that the Gaspra flyby had exceeded expectations and had opened new horizons for planetary science. The asteroid Gaspra continues to this day its ancient journey around the Sun, completing one orbit every 3 1/3 years, tumbling end over end through the darkness, its surface slowly accumulating new craters from the occasional impacts that all small bodies in the asteroid belt must endure. The spacecraft that visited it has long since completed its mission and met its planned end in the atmosphere of Jupiter, but the images and data from that October day in 1991 remain, archived and available for future researchers to study and reanalyze as new questions arise and new techniques become available. In this way, the brief encounter between a passing spacecraft and a small rocky world continues to yield scientific fruit, a lasting legacy of humanity's first close look at an asteroid. On the 28th of August, in the year 1993, the Galileo spacecraft found itself drifting through a region of space that exists between the orbits of Mars and Jupiter, a vast and quietly populated zone that we call the asteroid belt. And on this particular day, at this particular hour, the spacecraft was approaching a modest, elongated body of rock and dust known to astronomers as 243 Ida, a name that sounds rather like something you might call a gentle elderly relative, which seems fitting somehow for an object that has been tumbling peacefully through the darkness for such an extraordinarily long time. The approach had been planned for months, calculated with the kind of patient precision that allows a spacecraft traveling at tremendous speed to arrive at precisely the right location at precisely the right moment. And as Galileo drew nearer to this tumbling fragment of ancient solar system material, its cameras and instruments began their quiet work of observation, recording everything they could about this unremarkable-seeming asteroid that was about to reveal something quite remarkable indeed, though nobody aboard the distant control rooms on Earth could have known this at the time. The closest approach occurred at a distance of approximately 2,400 kilometers, which is close enough to see considerable detail but far enough to provide a comfortable margin of safety, the kind of distance that allows the spacecraft to gather its observations without any risk of collision. And at this range, the cameras captured image after image of Ida's cratered, irregular surface, storing the data carefully for later transmission back to the waiting scientists on our own small world. Ida, you see, is a considerably larger object than Gaspra, the asteroid that Galileo had visited some 2 years earlier during its long journey outward, and where Gaspra measures roughly 19 by 12 by 11 kilometers. Ida stretches to approximately 56 kilometers along its longest axis, with a width of about 24 kilometers and a depth of around 21 kilometers, giving it the appearance of something like an elongated potato, or perhaps a slightly flattened croissant, though such comparisons do little justice to the complex geography of craters and ridges and subtle undulations that cover its ancient surface. The shape of Ida tells us something about its history, about the collisions and fragmentations that have shaped it over billions of years, and its irregular form is not unusual among asteroids of this size, for these are objects that lack sufficient gravity to pull themselves into spherical shapes the way planets and large moons do, and so they retain the angular, asymmetric forms that result from their violent origins and subsequent gentle modifications. After the flyby was complete, after the cameras had stopped clicking and the instruments had finished their measurements, The spacecraft continued on its unhurried way toward Jupiter, carrying within its memory banks thousands of images and countless data points that would take many months to transmit back to Earth, for the distances involved are so vast, and the bandwidth available so limited, that the transfer of information from spacecraft to ground station proceeds at what might seem to us an almost painfully gradual pace. And so the images sat waiting, stored in the quiet electronic memory of Galileo, while the spacecraft drifted ever further from the asteroid it had so briefly visited, and the scientists on Earth went about their patient work of preparing for the eventual arrival of all that carefully gathered data. It was not until the following year, on the 17th of February, 1994, that a member of the imaging team named Anne Harch was carefully examining the transmitted images of Ida, looking through them with the methodical attention that characterizes good scientific work, when she noticed something unexpected in one of the frames, something small and faint but unmistakably present, a tiny point of light hovering in the space near the asteroid's limb. At first, one might suppose such a thing could be explained away as a cosmic ray hit on the detector, or a piece of debris, or some other artifact of the imaging process. But as Anne Harch examined more images, as she traced the position of this tiny bright spot across multiple frames, it became clear that this was something real, something that was maintaining a consistent position relative to Ida, something that was, in fact, orbiting the asteroid. The discovery was extraordinary, though the word extraordinary perhaps carries more drama than is appropriate for a scientific finding that was, in its essence, simply the recognition of something that had been there all along, waiting quietly to be noticed. And what Anne Harch had found was a moon, a tiny natural satellite orbiting an asteroid, and this was the first time such an object had ever been confirmed to exist. The little moon was given the name Dactyl, a name drawn from Greek mythology, for the Dactyli were a group of mythical beings associated with Mount Ida on the island of Crete, and so the naming created a gentle linguistic connection between the asteroid and its diminutive companion, a connection that seemed fitting for two objects that had apparently been traveling through space together for a very long time. Dactyl measures approximately 1.6 kilometers across, which is to say it is about the size of a modest hill on Earth. A rocky body so small that you could walk around its entire circumference in perhaps an hour or two, assuming you could somehow maintain your footing on its negligible gravity, which would be so weak that a gentle hop might send you drifting off into space entirely. The discovery raised immediate questions, as discoveries tend to do, and chief among them was the puzzle of how Dactyl came to be there at all, orbiting faithfully around Ida in the darkness between the worlds. There were, broadly speaking, two possibilities that scientists considered, and both seemed reasonable in their own ways, and neither could be immediately ruled out based on the available evidence. The first possibility was that Dactyl had formed separately from Ida, that it had once been an independent body moving through space on its own trajectory, and that at some point in the distant past it had wandered close enough to Ida to be captured by the asteroid's modest gravitational pull, becoming trapped in orbit around its larger companion. This capture hypothesis had a certain elegance to it, for we know that gravitational capture does occur in the solar system, and there seemed no particular reason why it could not happen on the scale of asteroids as well as on the larger scales of planets and their moons. But capture is not a simple thing, you see, for when one body approaches another in space, the mathematics of orbital mechanics generally dictate that it will simply swing past and continue on its way, perhaps deflected somewhat but not trapped. And for capture to occur there must be some mechanism to dissipate energy, to slow the approaching body enough that it cannot escape. and this is not easy to arrange in the emptiness of space. The second possibility was that Dactyl and Ida had formed together, that they shared a common origin, perhaps both having been blasted free from the same parent body during some ancient collision, fragments of a larger whole that had remained gravitationally bound to one another as they tumbled away into their own independent orbit around the Sun. This co-formation hypothesis also had its appeal, for it avoided the difficulties of capture mechanics, and it was consistent with what scientists were beginning to understand about the Coronis family of asteroids, to which Ida belongs. The Coronis family, you see, is a group of asteroids that share similar orbits and similar compositions, and the leading explanation for their existence is that they are all fragments of a single, much larger parent body that was destroyed in a catastrophic collision sometime in the distant past, perhaps around 1 or 2 billion years ago, though such dates are difficult to determine with precision. If Ida itself is a fragment of this collision, then it seemed plausible that Dactyl might be a smaller fragment that happened to end up in orbit around its larger sibling, a leftover piece of the same ancient catastrophe that created the entire Coronis family. The debate between these two hypotheses continued for some time, as scientific debates often do, with evidence being marshaled on both sides and careful analyses being conducted to try to distinguish between the possibilities. Some researchers pointed to the similarity in color and composition between Ida and Dactyl as evidence that they formed together, for if Dactyl had been captured from elsewhere in the asteroid belt, one might expect it to have a different makeup than its host asteroid. Others noted that the dynamics of binary asteroid formation during collisions were not yet well understood, and that it was difficult to say with confidence how likely such a co-formation event might be. In the end, as with many scientific questions, the answer proved to be somewhat less clear-cut than either camp might have hoped, and the possibility remains that Dactyl's true origin involves elements of both hypotheses, or perhaps something else entirely that we have not yet imagined. What is certain, however, is that the discovery of Dactyl opened up an entirely new area of planetary science, the study of binary asteroids and asteroid satellites, and in the years since Galileo's flyby of Ida, many more such systems have been discovered, leading us to understand that moons around asteroids are not the rare anomalies they once seemed to be, but rather a common feature of the asteroid belt's population. The images of Ida also allowed scientists to estimate the age of its surface, using a technique that involves counting craters. For you see, the surfaces of airless bodies like asteroids accumulate impact craters over time as they are struck by smaller objects, and by counting the number and size of craters on a surface, and by making assumptions about the rate at which impacts occur in that region of space, it is possible to make educated estimates about how long that surface has been exposed. Using this method, scientists determined that Ida's surface is approximately 1 billion years old, which is considerably older than the surface of Gaspra, and this difference in surface age tells us something about the different histories of these two objects, about the different environments they have experienced, and about the different processes that have shaped them over the long ages. The billion-year age estimate is consistent with the idea that Ida is a fragment of the Coronis family parent body collision, though it is difficult to pin down the timing more precisely than this, and there remains some uncertainty about exactly when that collision occurred and how Ida's surface has evolved since then. One particularly valuable piece of information that came from the discovery of Dactyl was the ability to calculate Ida's density. For you see, when you have an object orbiting another object, and you can measure the orbital period and the distance between them, you can use the mathematics of orbital mechanics to determine the mass of the central body, And once you know the mass and have estimated the volume from the images, you can calculate the density. From observations of Dactyl's orbit around Ida, scientists were able to determine that Ida has a density of approximately 2.6 grams per cubic centimeter, which is lower than the density of solid rock. And this suggests that Ida is not a solid monolithic body but rather a rubble pile, a loose aggregation of fragments held together by gravity, with significant void spaces between the pieces. This rubble pile structure is now understood to be common among asteroids of Ida's size, and it tells us something about the violent history of these objects, about the collisions that have shattered and reassembled them over billions of years, leaving them as loose congregations of debris rather than intact chunks of primordial material. The determination of Ida's density was important not just for understanding this particular asteroid, but for understanding asteroids in general, for it provided a data point that could be compared with other density measurements, helping to build up a broader picture of how asteroid interiors are structured and how they vary from one object to another. Before Dactyl was discovered, there had been theoretical predictions that asteroids might have moons, and there had been some suggestive but inconclusive observations that hinted at the possibility. But Galileo's images provided the first unambiguous confirmation that such objects exist, and this confirmation transformed what had been speculation into established fact. The importance of this discovery for understanding asteroid formation and the dynamics of the asteroid belt cannot be overstated, though in keeping with the gentle tone of our narration, we will state it calmly rather than with emphasis. Binary asteroids, we now know, provide unique opportunities for scientific study, for they allow us to measure masses and densities in ways that would otherwise be impossible, and they reveal information about the collisional and gravitational history of the asteroid belt that we could not obtain from studying single asteroids alone. Since Dactyl's discovery, ground-based observations and subsequent spacecraft missions have found many more asteroid moons, and we now recognize that perhaps 15% or more of near-Earth asteroids may be binary or multiple systems, a proportion that suggests that the formation of asteroid satellites is a robust and common process, though the details of that process are still being worked out. The Galileo spacecraft, meanwhile, continued on its journey toward Jupiter, carrying with it not only the images of Ida and Dactyl but also the growing recognition that even the supposedly barren reaches of the asteroid belt held surprises for those patient enough to look carefully. The flyby of Ida lasted only a few hours, a brief encounter in the context of Galileo's 14-year mission, but the scientific returns from that encounter have lasted for decades, inspiring research and raising questions that continue to be explored today. The images that Harch examined so carefully in February of 1994 revealed a tiny world orbiting a larger but still small world, both of them drifting through the asteroid belt on their endless journey around the Sun. And though neither Ida nor Dactyl will ever matter very much to human affairs in any practical sense, they have mattered a great deal to human understanding, which is perhaps the more important thing in the end. The surface of Ida, as revealed in Galileo's images, shows a history of bombardment, with craters of all sizes overlapping and superimposed upon one another, each impact representing a moment of violence in an otherwise peaceful existence, and yet the overall impression is one of quietude, of ancient stillness, of a body that has been doing very little for a very long time except slowly tumbling end over end as it orbits the Sun. Dactyl, too small for detailed surface imaging at the resolution available to Galileo, remains somewhat mysterious, a tiny companion whose exact history may never be fully known, but whose very existence changed what we thought we understood about the small bodies of our solar system. The Coronis family, that dispersed collection of fragments from an ancient catastrophe, continues to orbit the Sun in roughly similar paths, a ghost of the larger body that once existed, and Ida and Dactyl are part of that ghostly family, siblings of a sort to thousands of other small bodies that share their heritage. The gentle regularity of their orbits, the slow predictable tumbling of their rotation, the patient accumulation of new craters over timescales that dwarf all of human history, these are the rhythms of existence in the asteroid belt, and there is something restful in contemplating them, something calming in the thought of all those small worlds going quietly about their business far from the noise and urgency of our own. And so, as we consider the story of Ida and Dactyl, we find ourselves reminded that the universe contains countless quiet corners where nothing very dramatic happens for billions of years at a stretch, where the only events of note are the occasional gentle collision of tiny grains of dust, where the only witnesses are the unchanging stars. The discovery of Dactyl, important as it was scientifically, did not change anything about the lives of those two small bodies, for they had been orbiting together long before Galileo arrived, and they continue to orbit together now that Galileo is gone, indifferent to our observations and our theorizing, content simply to exist in the darkness between worlds. This is, in its way, a comforting thought, the idea that there are objects out there that do not need our attention, that do not depend on our understanding, that simply are what they are regardless of whether anyone is watching or not. And with that comforting thought, we may leave Ida and Dactyl to their eternal dance, content in the knowledge that they will still be there, tumbling slowly, orbiting peacefully, when we wake tomorrow refreshed and ready to learn more about the wonders of our solar system. In the winter of 1993, while the Galileo spacecraft was still making its long and patient journey toward Jupiter, something quite remarkable was unfolding in the distant reaches of our solar system, and this discovery would soon present the mission with an opportunity that no one had anticipated, a chance to witness an event that occurs perhaps only once in 1,000 years, and to do so from a vantage point that no other observer in the solar system could possibly share. A comet had been discovered, captured by Jupiter's immense gravitational pull, and it was falling inward, destined to collide with the giant planet in a cosmic encounter that would captivate astronomers around the world and provide Galileo with an unexpected scientific windfall before its primary mission had even begun. The comet in question had been spotted in March of 1993 by the husband and wife team of Carolyn and Eugene Shoemaker, working alongside their colleague David Levi at the Palomar Observatory in California, and when they examined their photographic plates they noticed something unusual about this particular comet, something that set it apart from the many comets that drift through our solar system on their lonely elliptical paths. Rather than appearing as a single fuzzy point of light with a tail streaming behind it, this comet presented itself as a string of fragments, a chain of icy bodies stretched out in a line like pearls on a celestial necklace, and further observations revealed the reason for this peculiar appearance. The comet had passed so close to Jupiter in 1992 that the planet's enormous tidal forces had torn it apart, fragmenting the original nucleus into more than 20 separate pieces, and now these fragments were orbiting Jupiter in a slowly dispersing train, each one following its own slightly different path around the giant planet. The calculations that followed the discovery were both precise and sobering, for they revealed that this string of cometary fragments, now officially designated Comet Shoemaker-Levy 9, was not simply orbiting Jupiter in a stable fashion, but was instead spiraling inward on a collision course that would bring it crashing into the planet's atmosphere in July of 1994. This prediction was met with tremendous excitement in the astronomical community. For while impacts of this scale must occur from time to time throughout the solar system, they had never been observed directly by human beings, and the opportunity to watch such an event unfold was truly unprecedented. Telescopes around the world began making preparations to observe the impacts, knowing that this would be a moment of genuine scientific importance, a chance to study what happens when a series of kilometer-sized bodies plunge into the atmosphere of a gas giant at tremendous speed. The Galileo spacecraft, still more than a year away from its arrival at Jupiter, found itself in a uniquely fortunate position for observing these impacts, and the mission planners quickly recognized the scientific potential of this unexpected opportunity. At the time of the predicted collisions, Galileo would be approaching Jupiter from an angle that would give it a direct line of sight to the impact sites on the planet's far side, the side facing away from Earth, and this meant that the spacecraft would be able to observe the actual moments of impact in a way that no Earth-based telescope could possibly achieve. The geometry of the situation was such that all of the predicted impact sites would occur on the hemisphere of Jupiter that was turned away from Earth at the moment of collision, hidden from view behind the planet's vast bulk, and so observers on our home world would have to wait for Jupiter's rotation to bring each impact site into view before they could study the aftermath of each event. This circumstance made Galileo's observations particularly valuable, for the spacecraft could capture data from the precise moments of impact, recording the initial fireballs and the immediate atmospheric disturbances that would be invisible to any observer on Earth or in Earth orbit. The Hubble Space Telescope, various ground-based observatories, and other instruments would all be watching Jupiter intently during that week in July, but only Galileo would have this direct view of the impacts themselves, this unobstructed window onto the collisions as they actually occurred. The scientific community was therefore keenly interested in whatever data Galileo could provide, knowing that the spacecraft's unique perspective would offer insights that could not be obtained from any other source. However, the collection of this data would not be straightforward, for Galileo was still operating under the constraints imposed by its malfunctioning high-gain antenna, the large umbrella-shaped dish that had failed to deploy properly back in 1991 and that had limited the spacecraft's ability to transmit large quantities of data back to Earth. The original mission design had assumed that the high-gain antenna would be available for communications, allowing the spacecraft to send back vast amounts of information at a relatively rapid rate. But with only the small low-gain antenna functioning, the data transmission rate was reduced to a tiny fraction of what had been planned. This meant that Galileo could not simply point its instruments at Jupiter and record everything that happened, sending it all back to Earth in a flood of information, but would instead have to be selective about what it observed and how it stored and transmitted that data. The mission team developed careful plans for the comet impact observations, working within the limitations of the antenna malfunction to extract as much scientific value as possible from this rare event. The spacecraft's instruments would be programmed to make specific observations at calculated times, storing the most important data in its onboard tape recorder for later transmission to Earth at the slow rate that the low-gain antenna permitted. This careful planning was essential, for there would be no opportunity to repeat these observations or to correct any mistakes, and the team wanted to ensure that Galileo captured the most scientifically valuable information that its instruments could provide. The impacts began on the 16th of July, 1994, and continued over the following 6 days, with 21 distinct fragments striking Jupiter's atmosphere in a series of collisions that released enormous amounts of energy into the planet's cloud tops. The fragments had been assigned letters of the alphabet for identification purposes, And as each one fell into Jupiter, the astronomical community watched with growing amazement at the scale and violence of the events unfolding before them. Fragment A struck first, plunging into Jupiter's southern hemisphere and creating a plume of heated material that rose high above the cloud tops before falling back into the atmosphere. And this initial impact set the pattern for the collisions that followed, each one producing its own distinctive fireball and atmospheric disturbance. From Galileo's vantage point, still some 240 million kilometers from Jupiter at the time, the spacecraft's instruments recorded data that would later prove invaluable for understanding these impacts. The near-infrared mapping spectrometer and the solid-state imaging camera were among the instruments trained on Jupiter during this period, capturing information about the temperatures and compositions of the impact sites in ways that complemented the observations being made from Earth. While the distance meant that Galileo's images lacked the fine detail that closer observations might have provided, the spacecraft's unique viewing angle meant that it could see phenomena that were completely hidden from terrestrial observers, and this made its data scientifically irreplaceable. The impact of Fragment W, which struck Jupiter on the 22nd of July near the end of the impact sequence, was among the most spectacular events observed by Galileo, producing a fireball that rose approximately 3,000 kilometers above the tops of Jupiter's clouds, a plume of superheated material thrown upward by the tremendous energy released when the cometary fragment plunged into the atmosphere at a velocity of around 60 kilometers per second. To put this scale into some perspective, this fireball rose to a height roughly equivalent to a quarter of Earth's diameter, and the energy released in this single impact was estimated to be equivalent to hundreds of thousands of nuclear weapons detonating simultaneously, though even this comparison fails to capture the true magnitude of such a cosmic collision. Galileo's instruments recorded the thermal signature of this rising fireball, capturing data about its temperature and its evolution over time in ways that help scientists understand the physics of large-scale atmospheric impacts. While Galileo observed from its unique vantage point in space, Earth-based observatories were conducting their own intensive campaign of observations, and the collaboration between these different perspectives proved enormously fruitful for the scientific understanding of the event. As Jupiter rotated on its axis, each impact site would eventually come into view from Earth, typically about 25 minutes after the collision itself, and observers would then be able to study the aftermath of each impact in detail. The pattern that emerged was striking, for each major impact left behind a dark spot in Jupiter's atmosphere, a region where material from the cometary fragment and from Jupiter's deeper atmosphere had been lofted to high altitudes and spread out to form a conspicuous blemish on the planet's face. These dark spots grew to remarkable sizes, with some of them reaching diameters comparable to the diameter of Earth itself, and they remained visible in Jupiter's atmosphere for months after the impacts occurred. The largest spots were clearly visible even through small backyard telescopes, allowing amateur astronomers around the world to observe the aftermath of this cosmic collision with their own eyes. And for professional astronomers, the spots provided a window into Jupiter's atmospheric composition and dynamics that had never before been available. The material that had been excavated from deep within Jupiter's atmosphere by the impacts included chemical compounds that are normally hidden below the visible cloud tops, and by studying the spectral signatures of these compounds in the impact sites, scientists were able to learn new things about the structure and composition of the planet's atmosphere. The collaboration between Galileo's observations and those from Earth-based and Earth-orbiting telescopes allowed scientists to build a comprehensive picture of what had happened during each impact, combining the direct views of the initial collisions that only Galileo could provide with the detailed follow-up observations that the larger and more powerful telescopes on Earth could achieve. The Hubble Space Telescope, freed from the distorting effects of Earth's atmosphere, provided particularly sharp images of the impact sites, revealing the complex structure of the debris plumes and the way they evolved over time as Jupiter's winds stretched and distorted them. Ground-based observatories equipped with infrared instruments detected the intense heat released by each impact, measuring temperatures that revealed the tremendous energies involved in these collisions. The scientific importance of the Shoemaker-Levy 9 impacts extended well beyond the immediate spectacle of watching cometary fragments crash into Jupiter, for the event provided a natural experiment that allowed scientists to probe Jupiter's atmosphere in ways that would otherwise have been impossible. By observing how the impact energy propagated through the atmosphere, how the debris plumes rose and fell back, and how the dark spots evolved over time, researchers gained new insights into the structure, composition, and dynamics of Jupiter's gaseous envelope. The impacts essentially served as a series of enormous probes, depositing energy and material at depth within Jupiter's atmosphere and allowing scientists to study how the planet responded to these perturbations. For understanding cometary composition, the impacts were equally valuable, for the spectral signatures observed in the impact sites revealed information about the materials that had been carried into Jupiter's atmosphere by the falling fragments. Observations detected evidence of water, sulfur compounds, and various other materials in the impact sites, helping to constrain the composition of the original comet and to test theories about the makeup of these icy wanderers from the outer solar system. The Shoemaker-Levy 9 event thus served as a kind of natural laboratory, allowing scientists to study both Jupiter and the comet in ways that no planned experiment could have achieved. The data that Galileo collected during the impact week had to be transmitted back to Earth slowly, constrained by the low data rate of the small antenna, and so the full scientific analysis of the spacecraft's observations took considerable time to complete. The mission team had carefully prioritized the observations to ensure that the most valuable data was captured and stored, and the gradual return of this information over the following months provided new pieces of the puzzle that scientists were assembling to understand the impacts. When combined with the wealth of data from ground-based observatories and from the Hubble Space Telescope, Galileo's unique contribution helped to create a remarkably complete picture of what had happened when Shoemaker-Levy 9 met its end in Jupiter's atmosphere. The event also had broader implications for our understanding of the solar system and for humanity's awareness of the potential hazards posed by cosmic impacts. While Jupiter is a much larger target than Earth and sweeps up far more of the debris wandering through the inner solar system, the Shoemaker-Levy 9 impacts served as a vivid reminder that collisions between celestial bodies are not merely historical events from the distant past, but ongoing processes that continue to shape the planets and moons of our solar system. The images of Earth-sized dark spots marring Jupiter's face, visible for months after the impacts occurred, made a lasting impression on both the scientific community and the general public, and the event stimulated increased interest in detecting and tracking near-Earth objects that might pose a threat to our own planet. For the Galileo mission itself, the Shoemaker-Levy 9 observations represented an unexpected bonus, a chance to conduct valuable science before the spacecraft had even arrived at its primary destination. The fact that Galileo was able to make meaningful contributions to this historic event, despite the limitations imposed by the antenna malfunction, was a testament to the ingenuity and dedication of the mission team, who found ways to extract scientific value from their spacecraft even under challenging circumstances. The experience also provided useful practice for the techniques of data compression and careful observation planning that would become essential during the primary mission at Jupiter. when the antenna limitations would continue to constrain the volume of data that could be returned to Earth. As the last of the cometary fragments finished their impacts and the dark spots they had created began their slow fade from Jupiter's face, the Galileo spacecraft continued on its journey toward the giant planet, still more than a year away from arrival but now enriched by the experience of having witnessed one of the most spectacular cosmic events ever observed by humanity. The comet that had briefly shared Jupiter's orbit was now dispersed throughout the planet's atmosphere, its constituent materials mixing with the gases of Jupiter and becoming part of the giant planet's vast bulk. And the Galileo mission had played a small but significant role in recording this final chapter of Shoemaker-Levy 9's existence. The observations from that week in July of 1994 would continue to yield scientific insights for years to come, as researchers analyzed and reanalyzed the data to extract every last bit of information about what had happened during those remarkable days. The event remains one of the most thoroughly documented cosmic collisions in history, a testament to the power of combining observations from multiple perspectives and multiple instruments to build a comprehensive understanding of a complex phenomenon. And for those who followed the Galileo mission, the Shoemaker-Levy 9 impacts served as a dramatic prelude to the main act, a taste of the scientific riches that awaited when the spacecraft finally reached Jupiter and began its long campaign of orbital exploration. On the 13th of July, in the year 1995, the Galileo spacecraft performed one of the most delicate and consequential operations of its entire mission, an act of gentle separation that would send a small probe on a solitary journey into the clouds of Jupiter. This moment, which had been planned and rehearsed and simulated countless times over more than a decade of preparation, arrived with a quietness that belied its significance, as the orbiter and its companion probe, which had traveled together through the solar system for nearly 6 years, prepared to part ways in the deep silence of interplanetary space. The spacecraft was, at this moment, approximately 81 million kilometers from Jupiter, a distance so vast that light itself required more than 4 minutes to traverse it, and the probe would spend the next 147 days drifting through the vacuum toward its destination, a patient coast through emptiness that would end in a brief and brilliant encounter with the giant planet's atmosphere. The preparations for this separation had begun many hours before the actual release, as the spacecraft systems were methodically configured for the precise sequence of events that would follow. The probe itself, a compact and remarkably sturdy assembly of instruments and protective shielding, had been attached to the orbiter throughout the long journey from Earth, riding along as a silent passenger through all the gravitational assists and course corrections that had brought Galileo to this point in its trajectory. Now, the time had come for the probe to continue on its own, following a path that would diverge ever so slightly from that of the orbiter, carrying it to a different aim point in Jupiter's atmosphere where it would make its fiery descent. The orbiter, for its part, would perform a deflection maneuver after the separation, adjusting its own trajectory to ensure that it would arrive at Jupiter on a path suitable for orbital insertion, while also positioning itself to receive the precious data that the probe would transmit during its brief period of atmospheric sampling. The separation sequence began with a careful spin-up of the probe, a procedure designed to impart the rotational stability that would keep the small spacecraft properly oriented during its long coast and subsequent entry. The probe was spun up to a rate of 10.5 revolutions per minute, a gentle rotation that would serve as a kind of gyroscopic stabilization, preventing the probe from tumbling or drifting off its intended attitude as it traveled through the void. This spin rate had been carefully calculated to provide sufficient stability without inducing any unwanted effects on the probe's instruments or systems, a balance between the need for orientation control and the constraints of the probe's compact design. The rotation would continue throughout the coast phase, the probe spinning slowly and steadily as it fell toward Jupiter, its orientation maintained by the simple physics of angular momentum rather than by any active control systems. Once the spin-up was complete, the actual separation occurred through the release of the mechanisms that had held the probe to the orbiter throughout the mission. Spring-loaded devices provided a gentle push, imparting a small velocity change that would gradually increase the distance between the two spacecraft over the following days and weeks. The relative velocity was modest, just a fraction of a meter per second, but over the vast distances and long timescales involved, this small initial separation would grow into a substantial divergence in their paths. The probe drifted away from the orbiter with a quietness appropriate to the vacuum of space. No sound accompanying this parting of companions, only the silent operation of mechanical systems performing exactly as they had been designed to perform so many years before. On the orbiter, following the probe's release, another critical system was deployed in preparation for the data relay that would occur nearly 5 months later. The communications relay antenna, which would receive the probe's transmissions during atmospheric entry and relay them to Earth, was unfurled and positioned for optimal reception. This antenna represented the sole link through which the probe's scientific findings would reach the waiting researchers on Earth, as the probe itself was far too small and power-limited to communicate directly across the vast distance to our planet. The relay arrangement meant that the orbiter would serve as an intermediary, catching the probe's relatively weak signals and retransmitting them with its own more powerful communication system, a carefully choreographed partnership that would allow the probe's brief moments of discovery to be preserved and shared with the scientific community. Perhaps the most poignant aspect of the probe's release was the finality that accompanied it. For once the separation had occurred, no further commands could be sent to the small spacecraft. From this moment forward, the probe would operate entirely on its pre-programmed sequence, a series of instructions stored in its onboard computer that would govern every aspect of its behavior from the quiet coast phase through the violent entry and the subsequent descent through Jupiter's clouds. The engineers and scientists who had designed and built the probe had to trust that their work was complete, that every contingency had been anticipated and every necessary instruction had been properly encoded in the probe's memory. There would be no opportunity for corrections or adjustments, no chance to respond to unexpected conditions or to refine the probe's operations based on new information. The probe was, in a very real sense, on its own now, carrying out the mission that had been entrusted to it with a faithfulness that could not be altered or amended. This autonomy was both a necessity and a source of considerable anxiety for the mission team, as the probe's journey and entry would unfold according to its internal programming regardless of what might be observed or desired by the controllers on Earth. The time delays involved in communicating across interplanetary distances made real-time control impossible in any case, but the complete absence of any command capability after separation meant that the probe's fate was sealed at the moment of release. Every line of code, every timing sequence, every threshold and trigger in the probe's programming represented a decision made months or years earlier. Decisions that could not be revisited now that the probe was embarked on its solitary journey. The mission team could only watch and wait, trusting in the thoroughness of their preparations and the robustness of their designs. The trajectory that the probe followed after separation was subtly different from that of the orbiter, a divergence that had been deliberately introduced to send the probe to an optimal entry point in Jupiter's atmosphere. While both spacecraft were heading toward the same giant planet, they were aimed at different regions and different encounter conditions. The probe seeking an entry angle and location suitable for atmospheric sampling, while the orbiter required a trajectory compatible with orbital insertion and the subsequent tour of the Jovian moons. This divergence in aim points meant that the probe would arrive at Jupiter on a slightly different schedule and approach the planet from a slightly different direction, entering the atmosphere at a location selected for its scientific interest and its suitability for the probe's particular design and capabilities. The waiting period that followed the separation was a time of quiet anticipation for the mission team, a span of nearly 5 months during which the probe coasted silently through space, gradually drawing closer to its destination while the orbiter continued its own preparations for the encounter. During this coast phase, the probe was essentially dormant, its systems quiescent to conserve the limited power available from its batteries, which would not be needed in earnest until the final hours before entry. The probe carried no solar panels, as Jupiter's great distance from the Sun made solar power impractical, and instead relied on batteries that would provide energy for the entry sequence and the subsequent descent. These batteries waited in the cold of space, their charge slowly diminishing but still sufficient, the probe's internal clock ticking away the seconds and minutes and hours until the pre-programmed awakening would occur. Bill O'Neill, who served as the project manager for the Galileo mission, later reflected on this milestone of the probe's release with the measured perspective of one who had shepherded the mission through countless challenges and setbacks. For O'Neill and the entire mission team, the separation represented both an achievement and a relinquishment, a moment when years of work were entrusted to the small spacecraft now drifting through the darkness toward Jupiter. The probe carried with it the hopes and efforts of hundreds of engineers and scientists who had contributed to its design and construction, and its release marked the transition from a phase of active preparation to one of patient waiting. O'Neill understood that the mission's success now depended on factors largely beyond the team's control, on the proper functioning of systems that could not be monitored or adjusted, on the accuracy of calculations and the reliability of components tested on Earth but now operating in the unforgiving environment of deep space. The atmospheric probe, as it coasted toward Jupiter, carried with it one of the most remarkable heat shields ever constructed, a protective barrier designed to withstand conditions that would destroy virtually any known material. When the probe entered Jupiter's atmosphere, traveling at approximately 47 kilometers per second, the friction and compression of the atmospheric gases would generate temperatures reaching as high as 15,500 degrees Celsius on the forward face of the heat shield, a temperature more than twice that of the visible surface of the Sun. At these extreme conditions, the heat shield would not simply absorb or reflect the incoming energy but would instead ablate, its material deliberately designed to char and vaporize and carry away the tremendous heat through the process of its own destruction. The shield was constructed primarily of carbon phenolic material, a composite of carbon fibers embedded in a phenolic resin matrix, which would gradually erode during the entry while protecting the instruments and electronics nestled behind it. The design of this heat shield represented years of research and testing, as engineers worked to create a protective system capable of surviving an entry more violent than any previously attempted by a spacecraft. The probe would experience deceleration forces reaching approximately 230 times the force of gravity on Earth, a brutal slowing that would occur over the span of roughly 2 minutes as the probe plunged into the Jovian atmosphere. During this brief but intense period, the heat shield would bear the full brunt of the entry, its outer layers sacrificing themselves to protect the precious scientific instruments within. The mass of the heat shield constituted a significant fraction of the probe's total weight, a necessary investment in protection that limited the mass available for instruments and other systems, but ensured that those instruments would survive to perform their intended measurements. The engineers who designed the probe were keenly aware that a mission of this importance and this difficulty required multiple layers of redundancy. Backup systems designed to ensure that data would be transmitted successfully even if primary systems failed during the descent. The probe carried 2 redundant copies of its most critical systems, including the communications equipment that would relay measurements back to the orbiter during the descent. If one transmitter failed, the other would continue operating, ensuring that the precious data would still reach the waiting receiver on the orbiter. Similarly, the probe's command and data handling systems incorporated redundancy, with backup processors and memory systems ready to take over if primary components were damaged by the violent forces of entry or the harsh radiation environment of Jupiter's magnetosphere. The communications link between the probe and the orbiter was designed with careful attention to reliability, using a relatively simple modulation scheme that would be robust against interference and signal degradation. The probe would transmit on 2 separate frequencies, the signals carrying the same data to provide additional redundancy against any single-point failures in the communications chain. The orbiter, for its part, would listen on both frequencies, recording all received signals for later transmission to Earth even if real-time relay proved impossible. This belt-and-suspenders approach to communications reflected the irreplaceable nature of the probe's data, measurements that could never be repeated if they were lost due to equipment failure or transmission errors. The power system for the probe's descent phase relied on batteries that had been designed for this single, critical mission, their energy carefully rationed to support approximately 75 minutes of operation after entry. These lithium-sulfur dioxide batteries were chosen for their high energy density and their ability to function reliably after years of storage in space, and they represented the sole source of electrical power for the probe's instruments and transmitters during the descent. The batteries would wake the probe from its long dormancy as entry approached, powering up the systems that would record and transmit the scientific measurements, their stored energy transforming into the signals that would carry Jupiter's secrets back toward Earth. The probe's instrument suite, nestled safely behind the massive heat shield, comprised a carefully selected set of sensors designed to measure the composition, structure, and dynamics of Jupiter's atmosphere. Each instrument had been hardened against radiation and tested extensively to ensure survival through the violent entry, and each would contribute unique information about the giant planet's atmospheric properties. The instruments would measure temperature, pressure, and density at various depths in the atmosphere, analyze the chemical composition of the gases, detect cloud layers, and sample the abundance of various elements and isotopes. Together, these measurements would provide the first direct sampling of a giant planet's atmosphere, data that would inform our understanding of Jupiter's formation and evolution. As the probe coasted through the void toward Jupiter, the orbiter continued on its own path, the 2 spacecraft gradually diverging as their separate trajectories carried them toward different aspects of the same encounter. The orbiter would arrive at Jupiter slightly before the probe's entry, positioning itself to serve as the communications relay and to perform its own orbital insertion burn, the engine firing that would slow it sufficiently to be captured by Jupiter's gravity. The timing of these events was carefully choreographed, the orbiter's maneuvers planned to ensure that it would be properly positioned to receive the probe's transmissions at the critical moment, neither too close to be overwhelmed by the intensity of the entry heating nor too far to reliably detect the probe's relatively weak signals. The waiting continued through the summer and autumn of 1995. the probe drawing ever closer to Jupiter while the mission team on Earth monitored the orbiter's health and prepared for the complex sequence of events that would mark the encounter. The probe itself could not be monitored directly, its dormant systems silent during the coast, but the team could track its trajectory through precise measurements of the orbiter's position and velocity, knowing that the probe followed a related but slightly different path toward the same destination. Each passing day brought both spacecraft closer to the giant planet, closer to the culmination of a journey that had begun with a launch from Cape Canaveral in October of 1989 and that had followed a winding path through the inner solar system before finally heading outward toward Jupiter. The patience required during this waiting period was of a particular kind, a professional patience born of long experience with the timescales of planetary exploration. The mission team understood that their work was largely complete for the moment, that the preparations had been made and the sequences programmed and the systems configured, and that nothing remained but to wait for events to unfold according to the choreography they had devised. This waiting was not passive, of course, as preparations continued for the encounter itself and for the orbital mission that would follow, but the probe's fate was sealed, its trajectory fixed, its programming immutable. It would either succeed or fail based on the quality of work done months and years earlier, and no amount of attention or anxiety could alter its path now. The probe's coast through space was a kind of suspended animation, the spacecraft drifting silently through the vacuum with only the slow spinning to mark its passage. No sound, no motion visible to any observer, only the steady march of time as the distance to Jupiter gradually decreased and the distance from Earth gradually increased. The Sun, still the dominant source of light in this region of space, grew smaller as the probe moved outward, while Jupiter, initially just a bright point of light, slowly grew larger and more impressive as the spacecraft approached. The probe, spinning at its steady 10.5 revolutions per minute, was wholly indifferent to these changes in the celestial scenery, its sensors dormant, its computers waiting for the pre-programmed time when they would wake and begin the final sequence of operations. The engineering teams who had built the probe and programmed its operations understood that their work now existed in a kind of suspended judgment, a state where success or failure remained unknown and unknowable until the probe reached Jupiter and either performed as designed or failed in some manner that might never be fully understood. They had done everything within their power to ensure success, testing and retesting components, running simulations of every conceivable failure mode, building in redundancy and margin wherever possible. But they also understood the humility that comes with sending a spacecraft to perform a task no machine had ever performed before, entering the atmosphere of a giant planet at speeds and under conditions that pushed the boundaries of human engineering knowledge. And so the probe continued on its way, a small capsule of human curiosity and ingenuity falling toward the largest planet in our solar system, carrying instruments designed to taste the alien atmosphere and report back on what they found. The wait would continue for 147 days from the moment of separation, days that would bring the probe inexorably closer to its brief moment of sampling and transmission, the culmination of a mission conceived decades earlier and now approaching its defining encounter. The probe had no awareness of the significance of its journey, no consciousness of the years of effort that had gone into its creation, but it carried that significance nonetheless, a messenger from Earth sent to explore a world vastly different from our own and to return with knowledge that would deepen our understanding of the giant planets and our place in the solar system. On the 7th of December, in the year 1995, a small capsule no larger than a kitchen table began its final approach toward the swirling clouds of Jupiter, and in doing so, It would achieve something that no human creation had ever accomplished before, entering the atmosphere of one of the giant outer planets and sending back measurements from within that vast and turbulent realm. The probe had been released from the main Galileo spacecraft some 5 months earlier, in July, and since that moment of separation it had been falling silently through the darkness of space, drawing ever closer to its destination with no engines firing, no course corrections possible, simply following the precise trajectory that mission planners had calculated years before. During those long months of coast, the probe had been essentially dormant, its batteries conserving their precious charge for the brief but intense period of activity that lay ahead, and all the while Jupiter grew larger in the space ahead, though of course the probe had no eyes with which to see it, only the patient certainty of orbital mechanics guiding it toward the predetermined entry point. The speed at which the probe approached Jupiter's atmosphere was truly remarkable, though we might describe it in the same measured tones one would use to describe any natural phenomenon. For speed is simply a number and the universe operates according to its own indifferent scales. The probe was traveling at 47.4 kilometers per second as it encountered the first wisps of Jovian atmosphere, which translates to roughly 170,000 kilometers per hour, and this made it the fastest entry into any planetary atmosphere ever achieved by a human-made object, a record that stands to this day. To place this velocity in some kind of perspective, one might note that it is approximately 50 times faster than a rifle bullet, or that at such a speed one could travel from Sydney to Perth in less than 2 minutes. Though such comparisons are perhaps not terribly meaningful when we are speaking of a small probe meeting the upper atmosphere of a gas giant nearly 800 million kilometers from Earth. The entry began in the early afternoon by spacecraft time, if we may speak of such things, and what followed was a period of approximately 2 minutes during which the probe experienced forces that would have been quite unsurvivable for any human passenger. The deceleration reached a peak of approximately 170 times the force of Earth's gravity, or 170 g as engineers would express it, and this tremendous force was the result of the probe slamming into the increasingly dense Jovian atmosphere and being slowed from its immense velocity to something more manageable for the parachute phase that would follow. 170 g is a force that would crush most objects instantly, and yet the probe had been designed to withstand precisely this punishment, with its delicate instruments nested within a protective shell that was itself wrapped in a heat shield of extraordinary sophistication. The probe was oriented so that its blunt heat shield faced forward into the oncoming atmosphere, and it was this shield that bore the full brunt of the entry forces, protecting everything behind it like a faithful guardian meeting an overwhelming adversary with quiet determination. The heat generated during those 2 minutes of atmospheric entry was almost beyond comprehension, for when an object travels at such speeds through gas, the air in front of it cannot move aside quickly enough and instead becomes compressed into a superheated plasma, a glowing mass of ionized particles that would be the end of any ordinary material. The temperature at the front of the heat shield reached approximately 15,000 degrees Celsius, which is roughly twice the temperature of the surface of our own Sun. And if you find that comparison soothing in its reminder that even the Sun is simply another object governed by the same physics, then perhaps that is the right frame of mind in which to receive such information. The heat shield was constructed from a material called carbon phenolic, which is a type of ablative material designed not to resist heat in the traditional sense, but rather to sacrifice itself in a controlled manner, carrying the heat away from the protected interior as it vaporized and streamed backwards into the wake of the descending probe. Over the course of those 2 minutes of entry, the heat shield lost approximately 80 kilograms of its original mass to this ablation process, which is to say that nearly half of the heat shield simply boiled away into the Jovian atmosphere, transformed from solid material into gas and plasma that dispersed into the alien sky. The heat shield had begun with a mass of somewhat more than 150 kilograms, and by the time the worst of the entry heating was over, it had shed so much of itself that it was significantly lighter, its surface scarred and pitted by the ordeal it had endured. But this sacrifice was precisely as intended, for the ablation process had carried away the tremendous thermal energy that would otherwise have penetrated to the instruments within, and the interior of the probe remained at temperatures that its electronics could survive. A small island of human technology protected from an environment that would otherwise have destroyed it in moments. As the probe descended deeper into the atmosphere and its velocity decreased, the forces acting upon it began to subside, and when the probe had slowed to approximately 400 kilometers per hour, a series of events unfolded in rapid succession according to a pre-programmed timeline that left nothing to chance. First, a small mortar fired to deploy a pilot parachute, a modest canopy that served to pull out the main parachute, which then blossomed above the probe and began to slow its descent even further. The heat shield, its protective duty now complete, was released and fell away into the depths of Jupiter's atmosphere, tumbling downward toward whatever fate awaited it in the increasingly dense gas below. The probe itself, now suspended beneath the main parachute, was considerably lighter without its protective shell, and for the first time its scientific instruments were exposed directly to the Jovian atmosphere, the air of another world flowing past sensors that had been designed and built in laboratories on Earth. What followed was a period of 57.6 minutes during which the probe descended approximately 160 kilometers into Jupiter's atmosphere, and during this time it transmitted a continuous stream of data back to the Galileo orbiter, which was passing overhead at a distance that allowed it to receive the probe's signal before continuing on its own journey into orbit around the giant planet. The probe's transmitter was modest in power, as all space systems must be, and the data rate was correspondingly limited, but even so it managed to relay approximately 3,600 bits of information to the orbiter with each pass. A modest amount by modern standards, but a treasure trove of scientific information when one considers that each bit represented a measurement taken within the atmosphere of Jupiter itself. The orbiter recorded this data faithfully, storing it for later transmission back to Earth, where it would be analyzed by teams of scientists who had waited years for this moment and would spend years more understanding what the probe had found. The probe carried 6 scientific instruments, each designed to measure a different aspect of the Jovian atmosphere, and together they painted a picture of that alien sky that was both confirming of some expectations and surprising in others. The first of these was the atmospheric structure instrument, which measured temperature, pressure, and density as the probe descended, building up a profile of how these fundamental properties changed with depth in the Jovian atmosphere. Temperature is a measure of how energetically the gas molecules are moving, and pressure is a measure of how much weight of atmosphere is pressing down from above, and density tells us how many molecules are packed into a given volume of space. And together these 3 quantities describe the basic physical state of any atmosphere in a way that allows comparison with theoretical models and with the atmospheres of other worlds. The second instrument was the neutral mass spectrometer, which was designed to identify the various gases present in the Jovian atmosphere and to measure their relative abundances. A mass spectrometer works by ionizing the gas molecules and then separating them according to their mass, rather like sorting coins by weight, and in this way it can determine not only what elements are present but also what molecules they have formed and in what proportions. The Jovian atmosphere is composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe, but it also contains trace amounts of many other substances including methane, ammonia, water, and various compounds of hydrogen with other elements, and the mass spectrometer was designed to measure all of these with considerable precision. The third instrument was the helium abundance detector, which was dedicated specifically to measuring the ratio of helium to hydrogen in the Jovian atmosphere. This ratio is of particular interest to planetary scientists because it provides clues about the formation and evolution of Jupiter, and because helium is thought to gradually separate from hydrogen in the deep interiors of gas giant planets, sinking toward the core over billions of years in a process that has implications for the planet's internal structure and heat budget. The helium abundance detector found that Jupiter's atmosphere contained somewhat less helium than the primordial solar nebula from which the solar system formed, suggesting that this helium settling process has indeed been occurring over the lifetime of the planet. The fourth instrument was the nephelometer, which is a device for detecting and characterizing clouds and particulate matter in the atmosphere. The word nephelometer comes from the Greek word for cloud, and the instrument works by shining a beam of light into the atmosphere and measuring how much light is scattered back by particles suspended in the gas. Jupiter's atmosphere contains multiple layers of clouds made from different substances at different altitudes, including ammonia ice, ammonium hydrosulfide, and possibly water ice, and the nephelometer was designed to detect the boundaries between these layers and to characterize the size and concentration of the particles within them. The fifth instrument was the net flux radiometer, which measured the flow of heat energy within the atmosphere by detecting both visible light from the sun and infrared radiation emitted by the warm atmosphere itself. This instrument could look both upward and downward, measuring how much energy was arriving from above and how much was coming from below, and in this way it could determine whether any given layer of the atmosphere was absorbing more energy than it was emitting or vice versa. Such measurements are important for understanding the overall energy balance of Jupiter's atmosphere and for understanding the meteorological processes that drive its famous storms and wind patterns. The sixth and final instrument was the lightning and energetic particle detector, which was designed to detect the radio frequency signals produced by lightning strokes and also to measure the flux of high-energy particles in the Jovian environment. Lightning on Jupiter had been suspected from earlier observations by the Voyager spacecraft, which had photographed what appeared to be lightning flashes on the night side of the planet, and the probe instrument confirmed that lightning does indeed occur in the Jovian atmosphere, though it appeared to be less frequent and less energetic than some models had predicted. The findings that emerged from the probe's brief descent were in some ways surprising and required scientists to revise their understanding of Jupiter's atmosphere. Perhaps the most unexpected result was that the atmosphere contained far less water than had been predicted by most theoretical models. Water is a key indicator of the oxygen content of a planet's atmosphere, and because oxygen is one of the most abundant elements in the universe, scientists had expected Jupiter to contain a considerable amount of water vapor. The probe found water levels perhaps 10 times lower than expected, a result that was puzzling and that led to much subsequent discussion about whether the probe had perhaps entered a particularly dry region of the atmosphere, an unusual meteorological feature that was not representative of Jupiter as a whole. The winds encountered by the probe were also stronger than many scientists had anticipated, reaching speeds of approximately 530 km per hour at the deepest levels measured. What was particularly surprising was not just the magnitude of these winds, but the fact that they continued to strengthen with depth, at least over the range that the probe was able to measure. Some theories had suggested that the powerful jet streams visible at Jupiter's cloud tops were shallow features driven by solar heating, and that wind speeds would diminish below the cloud layers where sunlight does not penetrate. But the probe data showed exactly the opposite pattern, with winds increasing as the probe descended. This finding suggested that Jupiter's atmospheric circulation is driven at least in part by heat escaping from the planet's interior rather than solely by energy from the Sun, a hypothesis that has important implications for our understanding of atmospheric dynamics on giant planets. The probe also found evidence of vigorous vertical mixing in Jupiter's atmosphere, with the abundances of various trace gases suggesting that material from deep levels was being transported upward more efficiently than some models had predicted. This mixing has implications for the chemistry of the upper atmosphere and for the appearance of the cloud features that we observe from a distance. Jupiter's atmosphere is not a static or stratified system, but rather a dynamic environment where gases from different levels are constantly being stirred together by turbulent motions on scales ranging from small eddies to giant storm systems. As the probe descended ever deeper, the pressure and temperature continued to increase according to the profiles measured by the atmospheric structure instrument, and eventually the probe reached depths where conditions exceeded the design limits of its systems. At a pressure of approximately 23 bars, which is to say 23 times the sea level atmospheric pressure on Earth, and at a temperature of around 150 degrees Celsius, the probe's transmission ceased and contact was lost. The probe continued to fall for some time afterward, though we have no data from this final phase, and as it descended into increasingly extreme conditions, it was eventually crushed by the mounting pressure and vaporized by the rising temperature, its material becoming part of Jupiter's atmosphere. The atoms that had been assembled into a spacecraft in clean rooms on Earth now dispersing into the swirling clouds of a gas giant. The data that the probe had transmitted during its 57.6 minutes of descent was safely stored aboard the Galileo orbiter, which continued its own mission to study Jupiter and its moons for the next 8 years. The information from those brief measurements would be analyzed and reanalyzed by scientists for decades, and our understanding of Jupiter's atmosphere continues to be informed by what that small probe discovered during its final descent. The probe itself is gone now, its physical form long since dispersed into the Jovian atmosphere, but the data it collected remains, a testament to human curiosity and engineering ingenuity, and a reminder that even the most hostile environments in our solar system can be explored, measured, and understood, one careful observation at a time. On the 7th of December, 1995, after 6 years of patient travel through the inner and outer solar system, after gravity assists from Venus and Earth, after crossing the asteroid belt and capturing humanity's first close views of asteroids Gaspra and Ida, the Galileo spacecraft finally approached its destination, the largest planet in our solar system, the gas giant Jupiter, a world so massive that it contains more material than all the other planets combined, a world that has fascinated astronomers since Galileo Galilei first turned his telescope toward it nearly 4 centuries earlier and discovered 4 small points of light orbiting around it, the moons that would eventually bear his name and that his namesake spacecraft had traveled so far to study. The journey to this moment had been extraordinarily long, not merely in distance but in time, and the mission team at the Jet Propulsion Laboratory in Pasadena, California, had spent years preparing for what would unfold on this particular winter day, a day that would see not one but 2 critical events occurring almost simultaneously: the descent of the atmospheric probe into Jupiter's clouds and the insertion of the main spacecraft into orbit around the planet, both operations representing the culmination of more than a decade of planning, building, testing, and waiting, and both carrying with them the possibility of failure after so much effort and so many miles. The orbital insertion burn was scheduled to begin at precisely 5:27 in the evening, Pacific Standard Time, and in the hours leading up to this moment, the spacecraft was falling toward Jupiter under the influence of the planet's tremendous gravitational pull, accelerating as it approached, gaining speed that would need to be shared if Galileo were to remain in the Jovian system rather than simply swinging past and continuing on into the outer darkness of the solar system, a brief visitor rather than a long-term resident, a flyby mission rather than the orbiting laboratory it was designed to be. The physics of orbital insertion are elegant in their simplicity, though demanding in their execution, requiring that a spacecraft traveling at high velocity fire its engines in the direction of its motion, thereby reducing its speed relative to the planet it wishes to orbit. And if the reduction is sufficient, the planet's gravity will capture the spacecraft into a closed elliptical path rather than allowing it to escape along an open hyperbolic trajectory, the mathematics of celestial mechanics dictating precisely how much velocity must be lost for capture to occur, and the engineers having calculated that Galileo would need to slow itself by approximately 630 meters per second, a change in velocity that would require the main engine to fire for 49 minutes, burning through its propellant while the spacecraft arced through the most intense region of Jupiter's magnetic environment. At 5:27 p.m. Pacific Standard Time, 800 million kilometers from Earth, the 400-Newton main engine ignited, and Galileo began the long process of slowing itself down, the engine pushing against the direction of travel with a steady, patient thrust, not the violent burst of a launch vehicle but a sustained and measured burn, the kind of propulsion that works gradually over time, accumulating its effect minute by minute as the propellant flowed and combusted and the spacecraft's velocity decreased imperceptibly at first and then more noticeably as the burn continued. 49 minutes of controlled fire in the cold vacuum of space, near a world where no human had ever ventured and none ever would in person. A mechanical emissary performing its duties with the reliability that the engineers had designed into it. During this critical burn, Galileo passed behind Jupiter as seen from Earth, entering a period of communication blackout that lasted approximately 1 hour, during which time no signals could reach the spacecraft and no telemetry could return to the anxious teams waiting in the mission control room at JPL, a room filled with men and women who had dedicated years of their professional lives to this mission, who had nursed it through budget crises and technical failures and launch delays, who had watched with dismay when the high-gain antenna failed to deploy and then adapted with ingenuity and determination to work around that setback, and who now sat in silence or spoke in hushed voices as the clock ticked through those interminable minutes when they could do nothing but wait and hope that all was proceeding according to plan on the far side of the largest planet in the solar system. The blackout was a consequence of simple geometry, the bulk of Jupiter blocking the direct line of sight between Galileo and Earth, radio waves being unable to pass through the dense gases of the planet's atmosphere or the even denser material of its possible rocky core, and so the spacecraft was on its own during the most critical phase of the orbital insertion, its computer executing the commands that had been uploaded days earlier, its sensors monitoring the performance of the engine and making whatever small adjustments were necessary to ensure that the burn proceeded correctly. The entire operation automated because the distances involved made real-time control from Earth impossible. The one-way light time from Jupiter meaning that any signal reporting a problem would arrive at Earth only after the problem had already resolved itself one way or another. As Galileo performed its orbit insertion burn, it was also passing through the most intense regions of Jupiter's radiation belts, bands of charged particles trapped by the planet's powerful magnetic field, particles that had been accelerated to tremendous energies and that could damage sensitive electronic components, disrupt computer memory, and degrade solar panels. And the spacecraft's path during insertion took it closer to Jupiter than it would ever go again during its primary mission. As close as 4 Jupiter radii from the planet's center, well within the most hazardous zones. And the engineers had designed the spacecraft with radiation hardening and had selected components that could withstand elevated radiation doses. But there is always uncertainty when operating in environments as extreme as Jupiter's magnetosphere, conditions that cannot be fully replicated in any laboratory on Earth. The radiation environment near Jupiter is among the most hostile in the solar system, created by the interaction between the planet's rapid rotation, its enormously strong magnetic field, and the particles that are continuously supplied by volcanic eruptions on the Moon Io, particles that become ionized and trapped and accelerated until they form belts of radiation far more intense than those surrounding Earth. Belts that would prove to be one of the primary limiting factors on Galileo's mission lifetime, slowly degrading its systems even as it continued to return valuable data, a harsh tax levied by Jupiter on any visitor that wished to study its secrets up close. While the orbital insertion was underway, the atmospheric probe that Galileo had released 5 months earlier was simultaneously entering Jupiter's atmosphere, a titanium and heat shield package that would be subjected to the most severe atmospheric entry ever attempted, decelerating from 47 kilometers per second to subsonic speeds in approximately 2 minutes, experiencing forces that would peak at approximately 230 times the acceleration of gravity, and temperatures on the heat shield reaching 14,000 degrees Celsius, hotter than the surface of the Sun, all in the service of delivering a small suite of instruments to sample directly the composition, structure, and dynamics of Jupiter's atmosphere, a task that could only be accomplished by diving into the clouds themselves. The choice to attempt both the probe entry and the orbital insertion on the same day was dictated by orbital mechanics and mission design constraints, but it meant that the operations team faced an incredibly complex sequence of events, with both spacecraft requiring attention and support, both performing critical and irreversible maneuvers, both facing the possibility of failure, and the team had prepared extensively for this convergence, rehearsing scenarios and distributing responsibilities and maintaining the calm, methodical professionalism that characterizes deep space operations, where problems unfold slowly enough to be analyzed but too far away to be fixed by any direct intervention. At 6:13 in the evening, Pacific Standard Time, 46 minutes after the burn was scheduled to conclude, the first signals from Galileo emerged from behind Jupiter and reached the Deep Space Network antennas in Australia, antennas designed to receive the faintest whispers from spacecraft billions of kilometers away. And those signals confirmed what the team had been hoping for but could not be certain of until that moment: that the burn had proceeded successfully, that the engine had fired for the full duration, that the spacecraft had shed the necessary velocity, and that Galileo was now captured in orbit around Jupiter, bound to the giant planet by invisible threads of gravity, the first spacecraft to achieve orbit around one of the outer planets. In the mission control room at JPL, the confirmation was met with quiet celebration, with handshakes and embraces and the release of tension that had been building for years, the engineers and scientists allowing themselves to feel, for a moment, the magnitude of what they had accomplished, the technical achievement of navigating a spacecraft to within 3 kilometers of its intended aim point after traveling 3.7 billion kilometers through the solar system, a journey that had included 3 planetary encounters, a transit across the asteroid belt, and 6 years of cruise operations, all culminating in a 49-minute engine burn on the far side of a planet so distant that its light takes more than 40 minutes to reach Earth. The precision of that navigation is worth dwelling upon, for it represents one of the quieter but more remarkable achievements of the mission. The ability to know where the spacecraft was and where it was going with sufficient accuracy to hit a target 3 kilometers wide after a journey of nearly 4 billion kilometers. A feat made possible by careful tracking using radio signals, by incorporating observations of stars and planetary limbs to refine position estimates, by modeling the effects of solar radiation pressure and gravitational perturbations from passing bodies, and by making a series of small trajectory correction maneuvers along the way, each one nudging Galileo slightly closer to its intended path, until by the time it reached Jupiter, it was almost exactly where it needed to be. The initial orbit into which Galileo was captured was highly elliptical, stretching out from a closest approach of approximately 4 Jupiter radii to an apopsis, or farthest point, that took the spacecraft well beyond the orbit of Callisto, the outermost of the 4 Galilean moons, an orbit with a period of approximately 198 days, meaning that almost 7 months would pass between the spacecraft's first close approach to Jupiter and its return to that vicinity. A long, slow loop outward and then back, during which time the spacecraft would continue to transmit data and the mission team would analyze the results of the orbit insertion and the probe entry and begin planning for the satellite encounters to come. This initial orbit was always intended to be temporary, a capture orbit that would be modified through subsequent propulsive maneuvers to create a tour of the Galilean satellites, bringing Galileo close to each of the 4 large moons in turn, Io and Europa and Ganymede and Callisto, each encounter designed to return scientific data about that particular moon while also using the moon's gravity to adjust the spacecraft's orbit for the next encounter, a technique called gravity assist or gravitational slingshot, the same technique that had been used to send Galileo on its roundabout path to Jupiter in the first place. The satellite tour that would follow the orbital insertion was a masterpiece of mission design, a complex choreography of encounters and maneuvers that would allow Galileo to visit each of the 4 large moons multiple times, gathering data about their surfaces and interiors and atmospheres and magnetic environments, data that would transform our understanding of these small worlds and reveal them to be far more complex and dynamic than anyone had anticipated. With active volcanoes on Io and a possible subsurface ocean on Europa and ancient, heavily cratered terrain on Callisto and a magnetic field generated within the interior of Ganymede. But all of that lay in the future, and on this December evening in 1995, the immediate task was simpler and more fundamental: to confirm that the spacecraft had survived and was functioning properly after its passage through the intense radiation belts and its long engine burn, to begin receiving the data from the atmospheric probe that had transmitted its findings during its descent into Jupiter's clouds, and to allow the mission team a few hours of well-deserved rest before the work of operating an orbiting spacecraft around Jupiter would begin in earnest. The communication blackout had been one of the more nerve-wracking aspects of the orbital insertion for the team on Earth, accustomed as they were to having continuous contact with their spacecraft, or at least the ability to have contact whenever the geometry permitted, and the knowledge that Galileo was performing its most critical maneuver while completely out of touch, unable to receive any assistance or guidance, relying entirely on its onboard programming and the redundancy built into its systems, was a test of faith in their own engineering, a reminder that deep space exploration is ultimately a solitary endeavor for the machines we send, surrounded by emptiness, dependent on their own resources. The relief that washed through the control room when the first telemetry arrived was palpable. The kind of collective exhalation that occurs when a long-dreaded outcome fails to materialize. When the spacecraft that might have been lost is instead confirmed to be healthy. When the engine that might have failed to ignite or failed to shut down at the proper moment instead performed exactly as designed. When the radiation that might have disrupted critical electronics instead passed through without causing permanent damage. And the mission that might have ended after 6 years of travel instead was just beginning its most productive phase. The data from the atmospheric probe arrived at Earth encoded in the transmissions that Galileo had recorded during the probe's descent and then relayed back to Earth after emerging from behind Jupiter. And though the probe itself was long since destroyed, crushed and vaporized by the increasing pressure and temperature as it sank deeper into the Jovian atmosphere, its 57 minutes of data represented a unique and precious record of direct measurement within the atmosphere of a giant planet. Information about chemical composition and wind speeds and cloud structure and the abundances of various elements. Information that could be obtained in no other way. In the days following the successful orbital insertion, as the spacecraft continued on its long elliptical path away from Jupiter, the first close images of the planet's cloud tops began to arrive at Earth, transmitted through the low-gain antenna at agonizingly slow data rates, each image taking many minutes to complete. The patience of the team rewarded with views of unprecedented detail, showing the complex patterns of bands and zones and spots and storms that characterize Jupiter's visible face, the result of the planet's rapid rotation and its internal heat and the dynamics of an atmosphere far deeper and more massive than Earth's entire ocean. These early images confirmed that despite the failure of the high-gain antenna, Galileo would still be able to return valuable imaging data, just in smaller quantities and over longer periods of time than originally planned. The science team having developed new data compression techniques and new strategies for selecting which observations to make and which data to transmit, making the most of the limited bandwidth available, turning what could have been a crippling setback into a challenge that brought out the best in the mission's engineers and scientists. The 6-year cruise to Jupiter had tested everyone's patience, a journey that included long periods of relative quiet punctuated by brief, intense periods of activity during the planetary encounters and the asteroid flybys, and the successful arrival at Jupiter felt like the end of a very long journey, though in truth it was merely the end of the beginning, the start of what would become an extended mission that would last nearly 8 years. Far longer than the 2 years originally planned. A mission that would revolutionize our understanding of the Jovian system and reveal it to be a miniature solar system in its own right. The precision of the orbital insertion, the survival of the passage through the radiation belts, the successful relay of the probe data, the first images of the cloud tops, all of these represented the culmination of efforts that had begun more than a decade earlier, when the mission was first conceived and then designed and then built and then launched. And each success was the result of countless decisions made by thousands of people, engineers and scientists and technicians and managers, all working toward this moment when a machine built by human hands would become an artificial satellite of the largest planet in our solar system, extending human senses across the vast gulf of space to a world of storms and moons and mysteries. As Galileo settled into its long elliptical orbit around Jupiter in December of 1995, the spacecraft began to turn its instruments toward the innermost of the 4 large Galilean moons, a world that had long puzzled astronomers and planetary scientists alike, a world whose surface appeared strangely smooth in the images returned by the Voyager spacecraft nearly 2 decades earlier. And that smoothness, that absence of impact craters that should have accumulated over billions of years, suggested something remarkable was happening on this small moon, something that continuously resurfaced and renewed the terrain. erasing the ancient record of cosmic bombardment that marked nearly every other solid body in the solar system. This world was Io, named for a priestess of Hera in Greek mythology, and it would prove to be one of the most extraordinary discoveries of the entire Galileo mission, revealing a moon in a state of perpetual geological turmoil, its interior churned by forces that originated not from within the moon itself but from the gravitational embrace of its giant parent planet and its neighboring moons, creating conditions that transformed this small world into the most volcanically active body known to exist anywhere in our solar system. The first extraordinary observation came during Galileo's initial orbit around Jupiter, when the spacecraft's instruments captured images of a volcanic plume rising from a feature known as Prometheus, a name drawn from the Titan of Greek mythology who brought fire to humanity, and the aptness of this name became immediately apparent when scientists examined the data. The plume extended approximately 100 kilometers above the surface of Io, a towering fountain of volcanic material ejected with such force that it reached heights impossible on Earth, where our atmosphere and stronger gravity would constrain such eruptions to far more modest elevations. On Io, however, the combination of low gravity and an essentially absent atmosphere allowed volcanic gases and fine particulate matter to rise to remarkable heights before falling back to the surface in graceful parabolic arcs, creating circular deposits of frost and fine debris around the volcanic vents. The Prometheus plume had actually been observed briefly by Voyager in 1979. But Galileo's sustained observations revealed that this eruption had continued essentially without interruption for at least 16 years, and likely much longer, a persistent volcanic fountain that spoke to the continuous and relentless nature of the forces driving Io's geological activity. In June of 1997, Galileo's cameras captured something even more dramatic unfolding at a volcanic feature called Pilon Patira, a caldera-like depression that suddenly erupted with tremendous violence, sending material high above the surface and depositing a dark blanket of pyroclastic debris across an area spanning more than 400 kilometers. The scale of this eruption was difficult to comprehend, as the dark deposit spread across the colorful surface of Io like a shadow, covering older terrain features and creating a stark visual record of the eruption's extent. The material ejected from Pilon Patira was distinctly different from the bright sulfurous deposits that characterized much of Io's surface, appearing instead as dark gray or black patches that scientists eventually determined to be composed of silicate minerals, rock material similar in composition to the basaltic lavas that erupt from volcanoes in Hawaii and Iceland on Earth. This observation was significant because it demonstrated that Io's volcanism was not merely a surface phenomenon involving the melting and redistribution of sulfur compounds, but rather involved the deep interior of the Moon, where temperatures were sufficient to melt silicate rock and drive true magmatic eruptions comparable to, and indeed exceeding, the most powerful volcanic events on our own planet. The temperatures measured at Io's eruption sites provided perhaps the most startling data of all, as Galileo's instruments detected thermal emissions indicating surface temperatures exceeding 1700 degrees Celsius at active volcanic vents, temperatures far higher than any recorded at volcanic eruptions on Earth. Our planet's hottest lavas, the ultramafic komatiites that erupted billions of years ago when Earth's interior was younger and hotter, reached temperatures of perhaps 1600 degrees Celsius. But such eruptions have not occurred on Earth for more than 2 billion years, and modern terrestrial volcanism produces lavas with temperatures typically ranging from about 700 to 1200 degrees Celsius. Io, by contrast, was generating eruptions hotter than anything Earth had produced in geological eons. And this discovery forced scientists to reconsider their understanding of the Moon's internal composition and the mechanisms driving its extraordinary volcanic activity. The extreme temperatures suggested that Io's lavas were rich in magnesium and iron, similar in composition to the ultramafic rocks of Earth's mantle, indicating that the tidal heating penetrated deep into Io's interior and generated magmas from the Moon's deepest layers. Understanding why Io exhibits such extreme volcanic activity requires examining the gravitational relationships between this small moon, its giant parent planet Jupiter, and its neighboring moons Europa and Ganymede, relationships that create a phenomenon known as tidal heating through a process called orbital resonance. Io orbits Jupiter at a distance of approximately 422,000 kilometers, completing one orbit every 1.77 Earth days. And this proximity to the massive planet subjects the Moon to powerful gravitational forces that raise tidal bulges in Io's solid body, much as the Moon raises tidal bulges in Earth's oceans but with far greater intensity. If Io's orbit were perfectly circular, these tidal bulges would remain fixed in position and generate relatively little internal heating. But the gravitational influence of Europa and Ganymede prevents Io's orbit from achieving this circular equilibrium. Europa orbits Jupiter in precisely twice the time it takes Io to complete one orbit, while Ganymede orbits in precisely twice the time of Europa, creating a 4:2:1 orbital resonance that has persisted for billions of years. And this resonance maintains a slight but significant eccentricity in Io's orbit, causing the Moon's distance from Jupiter to vary continuously as it travels around the planet. As Io moves closer to Jupiter during the portion of its orbit nearest the planet, the tidal bulges raised in its body grow larger, and as it moves away during the more distant portion of its orbit, these bulges subside. And this constant flexing of the entire Moon generates tremendous friction within its interior, converting orbital energy into heat. The amount of heat generated through this tidal flexing exceeds 100 trillion watts, more than 100 times the total heat produced by all volcanic and geothermal activity on Earth. And this heat must escape from Io's interior, which it does through the constant volcanic eruptions that characterize the Moon's surface. In this way, Io exists in a state of dynamic equilibrium, with gravitational energy continuously pumped into its interior through tidal heating and continuously released through volcanic activity, maintaining the Moon in a condition of perpetual geological upheaval that has persisted for billions of years and will likely continue for billions of years more, as long as the orbital resonance with Europa and Ganymede remains intact. In October of 1999, the Galileo spacecraft executed an extremely close flyby of Io, passing just 611 kilometers above the tortured surface of this volcanic moon, closer than any spacecraft had ever approached this world. This close passage was not without risk, as Io exists within the most intense radiation environment in the solar system, bathed in energetic particles trapped in Jupiter's powerful magnetic field, particles that posed a significant threat to Galileo's electronic systems. The spacecraft's controllers carefully planned the encounter to minimize radiation exposure while maximizing the scientific return, and the flyby proved extraordinarily successful, returning images and data of unprecedented detail that revealed the complex and varied nature of Io's volcanic terrain. The close approach images showed lava flows extending for hundreds of kilometers across the surface, volcanic calderas filled with molten lakes of magma, and towering volcanic plumes frozen in mid-eruption, their graceful arcs of ejected material captured by the spacecraft's cameras as monuments to the Moon's ceaseless geological activity. The surface of Io presents one of the most visually striking appearances of any world in the solar system, painted in vivid shades of yellow, orange, red, white, and black that shift and blend across the landscape in patterns that change noticeably over timescales of years or even months. These dramatic color variations arise primarily from the presence of sulfur and sulfur dioxide on Io's surface, compounds that occur in multiple crystalline forms or allotropes that produce different colors depending on their temperature and structural arrangement. Hot sulfur near active volcanic vents appears dark red or black, while cooler sulfur deposits transition through orange and yellow hues as they solidify and crystallize at lower temperatures. And sulfur dioxide frost, condensing from volcanic gases, creates brilliant white patches around eruption sites and in regions shadowed from direct sunlight. The overall effect is that of a pizza or a diseased and mottled fruit. Comparisons that scientists have sometimes used to describe Io's appearance, though perhaps more charitably one might describe it as a world of fire and brimstone made manifest, its tortured surface bearing perpetual witness to the tremendous geological forces operating beneath. The dark pyroclastic deposits observed at eruption sites like Pilon Patera, combined with the extreme temperatures measured at active vents, confirmed that Io's volcanism involves silicate rock material rich in iron and magnesium, not merely the sulfur-based activity that early researchers had hypothesized. The lavas erupting on Io appear to be ultramafic in composition, containing high proportions of magnesium iron silicate minerals similar to those found in Earth's mantle. And these lavas flow with remarkably low viscosity, spreading across the surface in thin sheets that can extend for hundreds of kilometers before solidifying. The dark material deposited by the Pilon Patera eruption eventually faded and changed color over subsequent years as sulfur compounds from ongoing volcanic activity were deposited on top of it, demonstrating the continuous nature of Io's resurfacing processes and explaining why impact craters are essentially absent from the Moon's surface. Any crater that might form on Io is quickly buried by volcanic deposits, erased from the geological record within timescales measured in thousands or perhaps tens of thousands of years, an eye blink in planetary terms. Galileo's instruments also detected and characterized the thin atmosphere that clings to Io's surface, an atmosphere composed primarily of sulfur dioxide gas with traces of other sulfur compounds and possibly some atomic oxygen and sulfur. This atmosphere is extraordinarily tenuous, with a surface pressure less than 1/1,000,000th of Earth's atmospheric pressure, and it varies dramatically across the surface and through time, thickening near active volcanic vents where fresh gases are being released and thinning in regions distant from current eruptions. The atmosphere also collapses partially during Io's passage through Jupiter's shadow, when temperatures drop low enough to cause sulfur dioxide gas to freeze out onto the surface as frost, only to sublimate back into the atmosphere when sunlight returns. This frost atmosphere cycle creates a dynamic and ever-changing envelope around the Moon, one intimately connected to the volcanic activity that supplies its gases. The interaction between Io's atmosphere and Jupiter's powerful magnetosphere creates some of the most energetic phenomena in the outer solar system, as volcanic gases escaping from Io become ionized by solar radiation and by the intense particle radiation within Jupiter's magnetic field. These ions are swept up by the rotating magnetosphere and accelerated to tremendous velocities, creating a torus of plasma that encircles Jupiter along Io's orbital path, a donut-shaped ring of electrically charged particles that radiates intensely at ultraviolet wavelengths. Some of this material falls into Jupiter's atmosphere along magnetic field lines, creating auroral displays at the planet's poles that are linked to Io's position in its orbit, visible as bright spots in ultraviolet images that track across Jupiter's polar regions as the Moon moves. The electrical currents flowing between Io and Jupiter through this magnetic connection carry millions of amperes of current, a vast circuit linking the tiny Moon to its giant parent through the conducting medium of the ionized gas. Among the many remarkable features discovered on Io during Galileo's observations were mountains of extraordinary height, peaks rising from the surface to elevations that exceed any mountains found on Earth. The tallest of these, known as Busol Mantis, rises approximately 17.5 kilometers above its base, making it considerably taller than Mount Everest, which stands only 8.8 kilometers above sea level on Earth. These mountains do not appear to be volcanic constructs like the shield volcanoes of Hawaii or the great volcanoes of Mars, but rather seem to be tectonic in origin, blocks of Io's crust that have been thrust upward by compressional forces within the Moon's lithosphere. The mechanism driving this mountain building remains somewhat uncertain, but it may be related to the continuous burial of Io's surface by volcanic deposits, which adds material to the surface faster than it can be accommodated, causing the crust to buckle and thrust fault, raising blocks of terrain to tremendous heights. The slopes of these mountains are precipitous, with grades far steeper than comparable features on Earth, and massive landslides have been observed on their flanks, sending avalanches of debris spreading across the surrounding plains. The comprehensive picture of Io that emerged from Galileo's observations was one of a world entirely dominated by volcanic processes, a world where the interior is maintained in a partially molten state by tidal heating, where magma continuously rises to the surface through hundreds of volcanic vents, where lava flows spread across the terrain in vast sheets, where volcanic plumes fountain material to heights of hundreds of kilometers, and where the entire surface is resurfaced on timescales of mere thousands of years. This Moon exists in a state of perpetual geological crisis, its surface torn apart and remade continuously, its interior churned by forces that originate in the gravitational dance between worlds, a dance that has continued for billions of years and will continue for billions more. Io stands as the most dramatic example of tidal heating in our solar system, a demonstration of how gravitational interactions between celestial bodies can drive geological processes of tremendous power and persistence, transforming a world that might otherwise be cold and dead into a crucible of fire, a moon of eternal volcanism orbiting endlessly around its giant parent planet in the outer reaches of the solar system. And so Galileo continued its observations of this tortured moon throughout its extended mission, returning data from multiple flybys that built an increasingly detailed understanding of Io's volcanic processes and their connection to the Moon's orbital dynamics and internal structure, adding to our knowledge of this remarkable world with each successive encounter, revealing new eruptions, mapping changing surface features, and documenting the ceaseless geological activity that makes Io unique among all the worlds we have explored. The small spacecraft, orbiting patiently around Jupiter for years beyond its designed lifetime, served as our eyes on this distant moon of fire and brimstone, sending home observations that transformed our understanding of what volcanism can be and where it can occur, demonstrating that even small worlds can harbor tremendous geological power when the conditions are right, when the gravitational forces are sufficient, and when the orbital dynamics maintain the necessary heating for billions upon billions of years. Among all the moons of Jupiter, there is one that captured the imagination of scientists more completely than perhaps any other body in our solar system, and that moon is Europa, the fourth largest of the Galilean satellites, a world of ice and mystery that the Galileo spacecraft would visit again and again over the course of its extended mission. Between the years 1996 and 2000, the spacecraft performed 11 separate flybys of this remarkable moon, each one carefully planned to reveal new details of its frozen surface. And together these encounters would transform our understanding of what might exist beneath that shell of ice, suggesting the presence of something quite extraordinary, a vast ocean of liquid water hidden from view, kept warm by forces we shall explore in due time, and carrying with it the tantalizing possibility that Europa might be one of the most promising places in our solar system to search for life beyond Earth. Europa is a relatively small world, only slightly smaller than our own moon, with a diameter of approximately 3,100 kilometers. And yet what it lacks in size it more than compensates for in scientific interest, for its surface presents a landscape unlike any other in our solar system, a global shell of water ice that appears remarkably smooth when viewed from a distance, crossed by countless lines and fractures that form intricate patterns resembling the cracks one might observe on a frozen pond, though of course at a scale vastly larger than any pond on Earth. The Voyager spacecraft had glimpsed these features years earlier and had noted that Europa's surface appeared strangely young, marked by relatively few impact craters compared to other icy moons. But it was Galileo that would provide the detailed observations necessary to understand why this surface looked so fresh, and what processes might be responsible for continually renewing it. The February 1997 flyby brought the spacecraft within 586 kilometers of Europa's surface, close enough to capture images of extraordinary detail, revealing features that had never been seen before on any world. Among the most striking of these features were the long linear markings that scientists came to call lineae, which is simply the Latin word for lines. And these lineae stretch across Europa's surface for hundreds and sometimes thousands of kilometers, crossing over one another in complex patterns that record a history of tectonic activity spanning many millions of years. The lineae appear in various forms, some as simple dark bands staining the ice, others as paired ridges with a central trough running between them, and the spacecraft's cameras revealed that these features often occur in sets, with newer lineae cutting across older ones, allowing scientists to piece together a rough chronology of how Europa's surface has evolved over time. The formation of these lineae is thought to be connected to the powerful tidal forces that Jupiter exerts upon this small moon. For Europa orbits its giant parent planet at a distance of approximately 670,000 kilometers, completing one orbit every 3.5 Earth days. And during each orbit, the gravitational pull of Jupiter flexes and stretches the moon's interior in a rhythmic cycle of compression and extension. This tidal flexing generates heat within Europa's interior through a process called tidal heating, the same mechanism that makes the nearby moon Io the most volcanically active body in our solar system. Though on Europa the effects are more subtle and manifest not as eruptions of lava but as a gentle warming that may be sufficient to maintain liquid water beneath the frozen surface. The lineae are thought to form as this tidal flexing causes the ice shell to crack and shift, opening fractures that may allow material from below to rise toward the surface before freezing in place. Particularly intriguing were the double ridge features that Galileo observed crossing Europa's terrain, consisting of two parallel raised ridges separated by a shallow valley or trough, and these formations presented something of a puzzle to scientists attempting to understand their origin. One hypothesis that gained favor suggests that these double ridges form through a process involving liquid water or warm ice rising through cracks in the surface, with the ridges themselves being built up gradually as material erupts along the fracture margins and freezes in place. If this hypothesis is correct, then the double ridges represent direct evidence that liquid water, or at least warm mobile ice, exists at relatively shallow depths beneath Europa's surface, perhaps only a few kilometers down, and that this material can occasionally make its way toward the surface through cracks in the overlying ice shell. Along many of the lineae, and especially concentrated in certain disturbed regions, Galileo's cameras revealed the presence of reddish-brown material that stained the otherwise bright white ice. And this coloration drew considerable scientific interest because it suggested the presence of chemical compounds that might have originated from below the surface. The exact composition of this brown material remains uncertain even now, but spectroscopic observations indicated the presence of hydrated salts, minerals that form in the presence of liquid water, and possibly other compounds including some that contain sulfur. Of particular interest was the possibility that this material might contain organic compounds, the carbon-based molecules that form the chemical foundation of life as we know it, though the evidence for organics remained inconclusive given the limitations of the instruments available on the spacecraft. Nevertheless, the presence of this material, apparently deposited along cracks and fractures that may connect to the interior ocean, suggested that studying these surface deposits might provide a way to learn about the composition of the ocean below without needing to drill through the ice. Among the most remarkable discoveries made during the Europa flybys was the detection of peculiar terrain features that scientists came to call chaos regions, areas where the orderly pattern of lineae gives way to a jumbled landscape of broken ice blocks, tilted rafts, and irregular knobs rising from a relatively smooth matrix material. The largest and most thoroughly studied of these chaos regions is called Connemara Chaos, named after a region in Western Ireland, and the high-resolution images that Galileo returned of this area revealed something quite extraordinary. Within Connemara Chaos, there are blocks of ice, some measuring several kilometers across, that appear to have broken away from the surrounding terrain and moved to new positions, rotating and drifting like icebergs in a sea before becoming frozen once again in place. Scientists studying these images found that they could mentally reconstruct the original surface by sliding the blocks back together like pieces of a jigsaw puzzle, demonstrating that the blocks had indeed been floating freely in some medium before refreezing. The implications of the chaos regions were profound, for they suggested that at some point in Europa's relatively recent past, liquid water, or at least warm, mobile ice had existed close enough to the surface to allow these blocks to break free and drift. The matrix material between the blocks, the smooth substance in which they now sit embedded, appears to have welled up from below, flooding the area before solidifying, and this matrix shows signs of flow features suggesting it was once at least partially liquid. Whether this liquid was pure water, briny saltwater, or warm ice behaving in a plastic fashion remains a subject of scientific discussion, but the chaos regions provide some of the most compelling visible evidence that Europa's ice shell is not a static, frozen barrier but rather a dynamic system where material from the interior can interact with the surface. The question of how thick Europa's ice shell might be was one of considerable importance to scientists, for the answer would determine how isolated the underlying ocean is from the surface and from the space environment above. Using various methods including analysis of the size and shape of impact craters, the geometry of chaos regions, and modeling of tidal heat flow, scientists estimated that the ice shell has a thickness somewhere in the range of 10 to 30 kilometers, though the true value remains uncertain and may vary from place to place across the Moon. A thicker ice shell would mean greater separation between the ocean and the surface, making it more difficult for any future mission to access the liquid water below, while a thinner shell would mean easier access but also raised questions about how the shell maintains its stability against the tidal stresses constantly working upon it. Perhaps the most significant piece of evidence for a subsurface ocean came not from the cameras but from the magnetometer instrument carried aboard the Galileo spacecraft, which was designed to measure magnetic fields in the environment around Jupiter and its moons. As the spacecraft flew past Europa, the magnetometer detected a weak but unmistakable magnetic field associated with the Moon, a field that varied in a particular way as Europa moved through different parts of Jupiter's powerful magnetic environment. The pattern of this variation indicated that the field was not internally generated in the way that Earth's magnetic field is generated by its molten iron core, but rather was an induced field, created by electrical currents flowing within some conducting layer inside the Moon. For such currents to flow, there must exist within Europa a layer of electrically conducting material, and the most plausible candidate for this conducting layer is an ocean of salty water, since dissolved salts would provide the ions necessary to carry electrical current. The magnetic field measurements, combined with the visual evidence from the chaos regions and the lineae, together built a compelling case for the existence of a global subsurface ocean on Europa, an ocean that may contain twice as much liquid water as all the oceans of Earth combined. This ocean is thought to lie beneath the ice shell, resting upon a rocky seafloor that may have its own geological activity, perhaps including hydrothermal vents similar to those found at the bottom of Earth's oceans. On Earth, hydrothermal vents support thriving ecosystems that derive their energy not from sunlight but from chemical reactions between hot water and rock, and the possibility that similar environments might exist on Europa raised profound questions about the potential for life in this distant ocean. One of the most striking characteristics of Europa's surface that Galileo confirmed and documented in detail was the remarkable scarcity of impact craters, which stands in sharp contrast to heavily cratered bodies like our own Moon or the neighboring Galilean satellite Callisto. Across the entire surface of Europa, scientists identified fewer than a dozen craters large enough to be clearly resolved in Galileo's images, and this paucity of craters tells us something important about the age of the surface. In our solar system, impact craters accumulate over time as asteroids and comets collide with planetary bodies, so a surface with few craters must be relatively young, having been renewed or resurfaced at some point in the geologically recent past, erasing the record of earlier impacts. Estimates based on the crater density suggest that Europa's surface may be no more than 40 to 90 million years old on average, which in geological terms is remarkably young, suggesting that whatever processes resurface this Moon may still be active today. The evidence for recent or ongoing geological activity on Europa came from multiple sources beyond just the crater counts. The chaos regions showed signs of relatively recent disruption. The lineae displayed cross-cutting relationships indicating a long history of formation, and the overall youthful appearance of the surface pointed toward a world that is still geologically alive. This activity is ultimately powered by the tidal heating that Jupiter's gravity produces within the Moon, a continuous source of energy that prevents Europa's interior from freezing solid and that may drive convection within both the ice shell and the underlying ocean. In some sense, Europa can be thought of as a giant heat engine, with Jupiter's gravitational embrace providing the energy input that keeps the interior warm and the surface dynamic. The flybys of Europa were carefully designed to maximize the scientific return while avoiding hazards to the spacecraft, for Jupiter's radiation environment is extremely hostile to electronics, and Europa orbits within the most intense portion of the radiation belts that surround the giant planet. Each time Galileo passed close to Europa, its electronic systems received a substantial dose of radiation, and over time this radiation took a cumulative toll on the spacecraft's components, causing various anomalies and malfunctions that the ground controllers worked creatively to overcome. The decision to send Galileo on so many Europa flybys, 11 in total, reflected the high scientific priority placed on understanding this moon, even at the cost of accelerated wear on the aging spacecraft. Throughout these encounters, the images and data returned by Galileo sparked discussions that extended far beyond the immediate scientific findings, raising questions about the possibility of life beyond Earth and prompting proposals for future missions that might explore Europa in greater detail. The evidence suggesting a potentially habitable ocean beneath the ice captured the imagination of scientists and the public alike, and in the years following Galileo's mission, serious consideration began to be given to missions that might return to Europa to continue the exploration. These discussions eventually led to the development of the Europa Clipper mission, designed to conduct detailed reconnaissance of the Moon through multiple flybys, carrying instruments far more sophisticated than those available to Galileo, with the goal of assessing Europa's habitability and selecting potential landing sites for future exploration. As the Galileo mission continued into its extended phases, Europa remained a primary target, and each subsequent flyby added new pieces to the puzzle of this enigmatic world. Some flybys focused on obtaining high-resolution images of specific features, others on gathering magnetometer data from different positions relative to Jupiter's magnetic field, and still others on attempting to detect any tenuous atmosphere or plume activity that might be escaping from the surface. The spacecraft's instruments worked together to build a comprehensive picture of Europa as a dynamic world with a complex interior structure, where liquid water exists in quantities that stagger the imagination, hidden beneath a shell of ice that bears witness to the forces constantly working upon it. The discoveries at Europa represented one of the most significant scientific achievements of the Galileo mission, transforming our understanding of where in the solar system life might potentially exist and demonstrating that oceans need not be limited to planets in the inner solar system where liquid water can exist on the surface. Europa showed us that beneath the frozen exterior of an icy moon, warmed by the gentle but persistent heat of tidal forces, conditions suitable for life might persist for billions of years, entirely independent of the distant sun whose light reaches Jupiter as only a faint glow. This realization expanded the potential habitable real estate of our solar system enormously and prompted a fundamental reconsideration of where we might search for life beyond Earth. The gentle work of exploration continues at Europa through the instruments and missions that have followed Galileo, but it was this pioneering spacecraft, with its modest cameras and magnetometers, that first revealed the secrets hidden beneath the ice, showing us a world where an ocean sloshes in eternal darkness, where tidal forces crack and refresh the surface in endless cycles, and where, perhaps, somewhere in the depths, conditions exist that might support forms of life we have yet to imagine. The 11 flybys that Galileo performed between 1996 and 2000 stand as a remarkable achievement of robotic exploration, patient and methodical in their accumulation of knowledge, each one bringing us closer to understanding this small icy moon that has come to occupy such a prominent place in our thoughts about life in the universe. Ganymede is a world of considerable size and surprising complexity, a moon so large that it surpasses even the planet Mercury in diameter, and yet it orbits Jupiter as merely one member of that planet's extensive family of natural satellites. When Galileo arrived in the Jovian system and began its methodical survey of the 4 great moons, Ganymede revealed itself to be far more than a simple ball of rock and ice drifting through the darkness. It proved to be a world with its own magnetic field, a feature so unexpected and so scientifically significant that it changed our understanding of what a moon could be and how the interior of an icy body might behave across the vast stretches of geological time. The diameter of Ganymede measures approximately 5,268 kilometers, making it the largest moon in our entire solar system by a comfortable margin. To place this in perspective, Mercury, the innermost planet orbiting our Sun, has a diameter of roughly 4,880 kilometers, which means that Ganymede exceeds the size of an actual planet. And yet, despite this impressive bulk, Ganymede possesses only about 45% of Mercury's mass, because it is composed largely of water ice and silicate rock rather than the denser iron and rocky materials that make up the small terrestrial planet. This combination of great size and relatively low density gives Ganymede its characteristic nature as an icy world, one where water in its various frozen forms plays a dominant role in shaping the landscape and, as scientists would come to discover, potentially harbors liquid water deep beneath the frozen surface. In June of 1996, the Galileo spacecraft performed its first close flyby of Ganymede, passing within 835 kilometers of the Moon's surface and gathering data that would prove to be among the most remarkable findings of the entire mission. As the spacecraft approached and then receded from Ganymede, its magnetometer instrument detected something that caught the attention of scientists immediately: a disturbance in the magnetic field environment that could not be explained by Jupiter's powerful magnetosphere alone. The data revealed that Ganymede possesses its own intrinsic magnetic field, a field generated within the Moon itself rather than merely induced by external forces. This made Ganymede unique among all the moons in the solar system, the only natural satellite known to produce its own substantial magnetic field through internal dynamo action, much as Earth generates its magnetic field through the churning of molten iron in its outer core. The discovery of Ganymede's magnetic field carried profound implications for understanding the Moon's internal structure. For a world to generate an intrinsic magnetic field through dynamo action, it must possess a layer of electrically conducting fluid that is in motion, creating the self-sustaining currents that produce magnetic effects. In the case of Earth, this conducting fluid is the liquid iron of the outer core, and scientists concluded that Ganymede must similarly possess a core containing liquid iron or an iron-rich alloy that remains molten to this day. The strength of Ganymede's magnetic field is considerably weaker than Earth's, but it is nonetheless sufficient to carve out a small magnetosphere within Jupiter's much larger magnetic environment, a bubble of magnetically distinct space surrounding the Moon. This magnetosphere interacts with Jupiter's magnetic field and the plasma particles trapped within it, creating a complex electromagnetic environment around this distant icy world. The presence of a liquid iron core within Ganymede suggests that the Moon's interior has remained warm enough over billions of years to prevent complete solidification of its metallic center. This internal heat likely derives from a combination of sources, including the residual warmth from Ganymede's formation and the decay of radioactive elements within its rocky mantle. Unlike Io, with its extreme volcanic activity driven by tidal heating, Ganymede experiences relatively modest tidal forces because its orbit lies farther from Jupiter and is not subject to the same resonant pumping effects. Nevertheless, some tidal heating may contribute to the Moon's thermal budget, helping to maintain the conditions necessary for a partially molten interior and the generation of that remarkable magnetic field. As scientists continued to analyze data from multiple Galileo flybys, evidence emerged for yet another unexpected feature of Ganymede's interior: a global ocean of liquid water lying deep beneath the frozen surface. This subsurface ocean appears to be sandwiched between layers of ice, with a thick outer shell of ice on top, then the liquid water layer, and then another layer of high-pressure ice below, all sitting atop the rocky mantle and iron core. The existence of this buried ocean was inferred from subtle variations in Ganymede's magnetic field as the Moon moved through Jupiter's magnetosphere. These variations matched the pattern expected if a layer of electrically conducting saltwater were present beneath the surface, responding to changes in Jupiter's magnetic field and creating secondary magnetic effects that the Galileo magnetometer could detect. The Hubble Space Telescope would later provide additional evidence for this subsurface ocean by observing aurora on Ganymede, the glowing of the thin atmosphere caused by charged particles interacting with atmospheric gases under the influence of the magnetic field. The behavior of these auroral emissions changed in ways that supported the presence of a conducting layer beneath the ice, consistent with a salty ocean perhaps 100 kilometers thick, located roughly 150 kilometers below the surface. For those interested in the possibility of habitable environments beyond Earth, this finding placed Ganymede alongside Europa and Enceladus as a world where liquid water might persist in the outer solar system. Though the ocean's position between ice layers rather than in contact with a rocky seafloor may limit its potential for the kind of water-rock interactions thought to be important for life. The surface of Ganymede presents two distinctly different types of terrain that tell a story of geological evolution spanning billions of years. Approximately one-third of the surface is covered by ancient dark regions, heavily cratered landscapes that preserve a record of the intense bombardment that characterized the early history of the solar system. These dark terrains are among the oldest surfaces visible on Ganymede, their appearance darkened by the presence of rocky and carbonaceous materials that have accumulated over immense stretches of time. The craters in these regions range from small pits to enormous impact basins hundreds of kilometers across, their forms degraded and softened by the slow processes that modify icy surfaces over geological time, including the gradual relaxation of topography under the weak but persistent influence of gravity. The remaining two-thirds of Ganymede's surface is covered by younger grooved terrain, a landscape unlike anything seen in the inner solar system but reminiscent of features observed on other icy worlds. This grooved terrain consists of parallel ridges and troughs that can extend for hundreds of kilometers across the surface, with individual features often several hundred meters in relief. The grooves cut across the older dark terrain in complex patterns, indicating that they formed after the early cratering had occurred and representing a period of significant geological activity that resurfaced large portions of the Moon. The relative youth of the grooved terrain is evident from its lower crater density compared to the dark regions, though it is still ancient by earthly standards, likely having formed several billion years ago during an early active phase of Ganymede's history. The origin of the grooved terrain remains a subject of scientific investigation, but the leading hypothesis involves tectonic processes driven by internal changes within Ganymede. As the Moon's interior evolved and differentiated, with ice separating from rock and the various layers settling into their present configuration, the surface would have experienced stresses that could fracture and deform the ice shell. The grooves may represent extension of the crust, analogous to rift zones on Earth where the surface is pulled apart, though the mechanics differ considerably given that the crust is made of ice rather than rock. Some researchers have also proposed that cryovolcanism may have played a role, with warmer and more fluid ice or even liquid water erupting onto the surface and flooding low-lying areas between the ridges, creating the relatively smooth lanes that separate the grooved units. In December of 2000, the Galileo spacecraft performed a particularly close flyby of Ganymede, approaching to within just 900 kilometers of the surface and capturing images and data with exceptional detail. This encounter allowed scientists to examine the grooved terrain at much higher resolution than had been possible during earlier flybys, revealing the fine-scale structure of the ridges and troughs and providing new clues to their formation. The images showed that the grooves are not simple parallel features but often exhibit complex patterns, including cross-cutting relationships that indicate multiple episodes of terrain formation. Some areas displayed evidence of fault scarps where blocks of ice had moved relative to one another, further supporting the interpretation that tectonic processes had shaped this landscape. The close flyby also revealed additional details of the impact craters that scar Ganymede's surface, including the curious features known as palimpsests. These are the ghostly remnants of large impact basins that have been almost completely erased by the relaxation of the ice over time, leaving only subtle circular brightening where the crater once existed. The viscous behavior of ice at the temperatures found on Ganymede allows topographic features to slowly flatten and disappear over billions of years, a process called viscous relaxation that eventually removes all but the faint traces of even the largest impacts. Younger and smaller craters retain their shapes more clearly, creating a mixture of well-defined and degraded impact features across the surface. Among the discoveries made about Ganymede during the Galileo mission was the observation of polar caps composed of water frost at both the north and south poles of the Moon. These polar regions appear brighter than the surrounding terrain due to the presence of fine-grained frost that reflects sunlight more efficiently. The formation of these polar caps is thought to be related to the interaction between Ganymede's magnetic field and the charged particles in Jupiter's magnetosphere. At lower latitudes, bombardment by these energetic particles can darken the surface through chemical changes and sputtering, while the magnetic field provides some protection to the polar regions, allowing fresh frost to accumulate and maintain the surface brightness. The polar caps thus serve as visible markers of Ganymede's unique magnetic nature, surface features shaped not by impacts or tectonics but by the Moon's own magnetic field shielding select regions from the harsh particle environment of Jupiter's magnetosphere. The Galileo mission also detected a thin atmosphere around Ganymede, an atmosphere so tenuous that it barely qualifies as such by earthly standards, but is nonetheless present and detectable by the spacecraft's instruments. This atmosphere consists primarily of oxygen, produced by the breakdown of water ice on the surface when it is bombarded by ultraviolet light from the Sun and by energetic particles from Jupiter's radiation belts. The process, called radiolysis and photolysis, splits water molecules into hydrogen and oxygen, with the lighter hydrogen escaping into space while the heavier oxygen lingers near the surface to form this wispy atmospheric envelope. The surface pressure of Ganymede's atmosphere is roughly 1/1,000,000th that of Earth's, so vanishingly thin that it would register as essentially a vacuum by any practical standard. Yet it represents an ongoing process of chemical change at the interface between the icy surface and the space environment. The presence of both a magnetic field and a thin oxygen atmosphere creates the conditions for aurora to occur on Ganymede, and observations have indeed detected glowing emissions from the Moon's polar regions. These aurora are caused by the funneling of charged particles along magnetic field lines into the polar atmosphere, where they collide with oxygen molecules and atoms and cause them to emit light. The aurora on Ganymede are not visible to the human eye from Earth, but they can be detected by sensitive instruments observing in ultraviolet wavelengths. The study of these aurora has provided valuable information about the magnetic field geometry and the interaction between Ganymede's small magnetosphere and Jupiter's dominant magnetic environment, as well as offering additional evidence for the subsurface ocean through the subtle ways the auroral patterns shift over time. As Galileo completed its tour of the Jovian system and passed by Ganymede multiple times between 1996 and 2000, a detailed picture emerged of this giant moon as a world of considerable complexity. From its liquid iron core generating that singular magnetic field, through the rocky mantle and the possible layers of ice and liquid water, to the ancient dark terrains and younger grooved regions of its surface, Ganymede proved to be far more than a simple frozen body passively orbiting the king of planets. It is a world with its own geological history, its own internal structure, its own magnetic personality, and possibly its own hidden ocean waiting deep beneath the ice for future missions to investigate more closely. The grooved terrain in particular continues to fascinate scientists as evidence of a geologically active past, a period when internal forces reshaped the surface of this distant moon. Whether through the extension of the icy crust as the interior evolved, or through cryovolcanic flooding of low-lying regions, or through some combination of processes, Ganymede experienced episodes of renewal that erased the ancient cratering record over large portions of its surface and created the distinctive parallel features that now characterize the younger terrain. This activity appears to have largely ceased billions of years ago, leaving Ganymede in a state of geological quietude punctuated only by the occasional impact and the slow viscous relaxation of existing topography. The discoveries made at Ganymede illustrate how each world in the outer solar system holds its own surprises, its own unique combination of features that emerge only through patient observation and careful analysis. A moon larger than Mercury, possessing its own magnetic field and potentially harboring a buried ocean, crowned with polar caps of frost and wrapped in the faintest veil of oxygen atmosphere. Ganymede expanded our understanding of what is possible in the diverse family of objects that orbit the giant planets. The Galileo mission transformed this distant point of light into a known world, a place with geography and history and internal structure, a place that future generations may someday explore more closely as humanity's reach extends ever farther into the depths of the solar system. And so Ganymede takes its place in the catalogue of worlds revealed by patient spacecraft and dedicated scientists, another entry in the ever-growing library of knowledge about our cosmic neighborhood. Its magnetic field hums quietly in the darkness, generated by flows of liquid iron deep within its core, while far above, the ancient dark terrains and younger grooved regions record the story of a moon that was once geologically alive. Perhaps beneath all that ice, a saltwater ocean still waits, cold and dark and vast, one more hidden sea in a solar system that has proved to contain many more such environments than anyone expected when the age of planetary exploration began. For now, Ganymede orbits on in its eternal circuit around Jupiter, the largest moon of all, keeping its secrets while offering tantalizing glimpses to those who take the time to look and wonder and patiently gather the data that transforms mystery into understanding. Callisto sits at the outermost edge of the Galilean family, orbiting Jupiter at a distance of nearly 1.9 million kilometers, which places it well beyond the reach of the intense tidal forces that shape and reshape its closer siblings. When Galileo turned its instruments toward this distant moon, it found a world that seemed almost frozen in time, a place where the violence of the early solar system remains written across every square kilometer of surface, preserved with a fidelity that exists nowhere else in our planetary neighborhood. Callisto is, in many ways, a museum piece, a relic of an age when countless objects careened through the darkness between the planets, and the evidence of those ancient collisions has been neither erased by geological renewal nor obscured by atmospheric processes, but instead remains visible in patient testimony to events that occurred billions of years ago. The spacecraft made multiple passes by Callisto throughout its extended mission at Jupiter, gathering data that would gradually reveal this moon to be both simpler and more mysterious than anyone had anticipated. On the surface, Callisto appears to be exactly what one might expect from an ancient, geologically dead world, its face thoroughly pockmarked by impact craters of every conceivable size. From tiny pits barely visible in the highest resolution images to enormous basins that stretch across significant portions of the moon's circumference. Yet beneath that battered exterior, Galileo's magnetometer detected hints of something unexpected, something that suggested Callisto might not be entirely the frozen corpse it appeared to be. And this discovery added a layer of intrigue to a world that had previously been considered the least interesting of Jupiter's large moons. The most striking feature visible on Callisto's surface is the immense impact structure known as Valhalla, a formation so large that it dominates an entire hemisphere of the moon and serves as one of the most spectacular examples of multi-ring impact basins found anywhere in the solar system. Valhalla measures approximately 1,800 kilometers across when one includes its extensive system of concentric rings, though the central bright region spans roughly 600 kilometers in diameter. These rings ripple outward from the impact center like frozen waves in a pond, each one representing a ridge or trough formed in the immediate aftermath of a catastrophic collision that occurred in the distant past. The basin itself no longer shows significant depth, having relaxed over the eons as the ice that makes up Callisto's crust slowly flowed under its own weight. But the ring structure remains clearly visible, a testament to the enormous energy released when whatever object created Valhalla struck the moon's surface. Understanding how multi-ring basins form has occupied planetary scientists for decades, and Valhalla provides one of the clearest examples for study. When a sufficiently large impactor strikes an icy body like Callisto, the initial crater formation is followed by a complex series of adjustments as the crust responds to the sudden removal of material and the release of tremendous heat. The concentric rings appear to form through some combination of fracturing and viscous relaxation of the ice, creating alternating ridges and troughs that propagate outward from the impact center. In the case of Valhalla, this process created a pattern of rings that extends for hundreds of kilometers beyond the central basin, and studying this structure helped scientists better understand similar features observed on other icy worlds throughout the outer solar system. Callisto's surface age has been estimated at approximately 4 billion years through the careful counting and statistical analysis of impact craters, a technique known as crater counting that allows planetary scientists to determine relative ages of surfaces even when direct samples are unavailable. A surface that is 4 billion years old dates back to the period known as the Late Heavy Bombardment, an epoch early in solar system history when the inner and outer planets were subjected to an intense rain of debris left over from planetary formation. On most worlds, the craters from this period have been erased by subsequent geological processes, covered by volcanic flows or worn away by weather or subducted by tectonic activity, but Callisto's surface preserves them almost perfectly. The Moon has remained essentially unchanged since the solar system's youth, a frozen snapshot of conditions that prevailed when the planets were still settling into their current orbits and the leftover building blocks of planetary formation were being swept up through countless collisions. This remarkable preservation is possible because Callisto lacks the internal heat sources that drive geological activity on other worlds. Unlike its sibling moons closer to Jupiter, Callisto does not experience significant tidal heating because its orbit is nearly circular and it lies far enough from Jupiter that the giant planet's gravitational influence does not flex and squeeze its interior. Io, the innermost Galilean moon. orbits in an elliptical path that causes it to be constantly stretched and compressed by Jupiter's gravity, generating so much internal heat that the Moon is the most volcanically active body in the solar system. Europa experiences a similar but less intense version of this process, producing enough heat to maintain a liquid water ocean beneath its icy shell. Ganymede shows evidence of past geological activity driven by similar mechanisms. But Callisto, sitting at the outer edge of the system, receives so little tidal energy that its interior has remained essentially quiescent for billions of years, allowing it to retain its ancient surface undisturbed. Despite the apparent geological dormancy suggested by its surface, Galileo's magnetometer measurements revealed something that puzzled scientists greatly, for the data indicated that Callisto might possess a subsurface ocean of liquid water. Like Europa and Ganymede, Callisto was found to produce a magnetic signature consistent with an induced magnetic field, the kind of field generated when a conducting layer within the Moon responds to Jupiter's rotating magnetosphere. The simplest explanation for this conducting layer is a global ocean of salty water lying somewhere beneath the ice, perhaps 100 kilometers or more below the surface. This finding was surprising because Callisto was not expected to have the internal heat necessary to maintain liquid water, and yet the magnetic data seemed to require some such layer to exist. The possible presence of an ocean beneath Callisto's surface creates a scientific puzzle that has not yet been fully resolved. For if the Moon truly harbors liquid water, there must be some mechanism keeping it warm enough to remain liquid despite the absence of significant tidal heating. Some researchers have proposed that the answer lies in the specific mixture of materials that make up Callisto's interior, suggesting that the presence of ammonia or other antifreeze compounds could lower the melting point of water enough to allow liquid to persist at temperatures that would otherwise freeze pure water solid. Others have suggested that radioactive decay of elements within Callisto's rocky component might provide just enough heat to maintain a thin liquid layer, though this seems barely sufficient to explain the observations. The mystery remains open, and future missions to the Jupiter system may eventually provide the data needed to determine whether Callisto truly possesses an ocean and, if so, how it maintains itself against the relentless cold of the outer solar system. What makes this puzzle particularly intriguing is the stark contrast between Callisto's hidden complexity and its utterly inactive surface. If an ocean exists beneath the ice, it has produced no surface expression whatsoever, no evidence of the kind of geological renewal that characterizes Europa's fractured terrain or the resurfacing events visible in portions of Ganymede. The craters on Callisto's surface remain undisturbed. The ice shows no signs of convection or cryovolcanism, and the Moon appears to be completely geologically dead despite possibly harboring one of the prerequisites for habitability. This disconnect between surface and interior puzzled scientists who studied the Galileo data, and it remains one of the more thought-provoking aspects of Callisto's nature. On the 25th of May in 2001, Galileo executed its closest approach to any of the Galilean moons when it passed just 138 kilometers above Callisto's ancient surface. This remarkably close flyby allowed the spacecraft's cameras and instruments to capture data at unprecedented resolution, revealing details of the surface that had been impossible to discern from greater distances. The images returned from this encounter showed the terrain in exquisite detail, capturing features just tens of meters across and providing planetary scientists with their most intimate view of this cratered world. Among the most unusual features revealed by Galileo's close observations were strange spiky structures that scientists have come to call pinnacles. These features appear as tall, jagged protrusions rising from the surface, somewhat reminiscent of the penitents found in high-altitude snowfields on Earth, though far larger in scale. The pinnacles on Callisto reach heights estimated at 80 to 100 meters and appear to be composed primarily of ice, standing like frozen monuments across portions of the Moon's terrain. Their formation is thought to be related to the sublimation of ice, a process in which solid ice transforms directly into water vapor without passing through a liquid phase, gradually eroding the surface in patterns that leave behind these tall, pointed remnants. The sublimation process that creates pinnacles is driven by the extremely thin carbon dioxide atmosphere that Galileo detected surrounding Callisto. This atmosphere is so tenuous that calling it an atmosphere at all seems almost generous, for it represents merely the barest whisper of gas hovering above the frozen surface. Yet even this trace amount of carbon dioxide indicates that some ongoing process is releasing gas from the ice, likely through slow sublimation that occurs when sunlight warms the surface during Callisto's long days. The carbon dioxide does not persist for long before escaping into space or freezing back onto the surface, but it is constantly replenished by continued sublimation, maintaining a fragile equilibrium that allows this thin atmospheric envelope to exist. The presence of the pinnacles and the ongoing sublimation they represent shows that Callisto is not entirely static, even if it lacks the internal geological activity that characterizes other worlds. The surface is slowly evolving under the influence of solar radiation and the vacuum of space, with ice gradually transitioning to vapor and reshaping the terrain over timescales measured in millions of years. This process is extraordinarily slow by any human measure, but it demonstrates that even the most ancient and apparently unchanging surfaces continue to undergo modification by physical processes acting at their own unhurried pace. Galileo's multiple flybys of Callisto revealed a world of varied terrain despite its uniform ancient age. The cratered plains are broken by bright ray craters where relatively recent impacts have excavated fresh ice from beneath the darker surface material. The darkness of Callisto's surface, which gives it a lower reflectivity than the other Galilean moons, is thought to result from the accumulation of dust and meteoritic material over billions of years, creating a lag deposit of rocky debris that covers the underlying ice. Fresh impacts punch through this dark layer to reveal the brighter ice below, creating the streaks and rays that radiate from younger craters. Some regions of Callisto show what scientists call palimpsest craters, ancient impact structures that have been so thoroughly degraded by the slow flow of ice over geological time that they appear as mere bright spots rather than proper craters with rims and central peaks. These features represent impacts so old that even the minimal geological activity occurring on Callisto has managed to partially erase them, smoothing away the sharp topography while leaving behind ghostly circular marks on the surface. The presence of palimpsests suggests that even Callisto's ice is not perfectly rigid over the longest timescales, but flows gradually under its own weight in a process called viscous relaxation. The data gathered by Galileo has led some planners to consider Callisto as a potentially valuable destination for future human exploration of the Jupiter system. This consideration arises primarily from Callisto's position relative to Jupiter's deadly radiation belts. The giant planet is surrounded by intense zones of radiation that would be lethal to unshielded humans and damaging to electronic equipment. And the inner Galilean moons, particularly Io and Europa, orbit within these zones. Callisto, however, sits far enough from Jupiter that it lies largely outside the most dangerous radiation regions, experiencing radiation levels that, while still elevated compared to Earth, are far more manageable than those encountered closer to the planet. A crewed outpost on Callisto could potentially serve as a base for the remote operation of robotic probes exploring the inner Galilean moons, allowing human operators to control rovers and landers on Europa without the communications delay that would be involved in controlling such devices from Earth. The relative safety of Callisto's radiation environment, combined with its stable ancient surface and the presence of water ice that could potentially be extracted for life support and fuel production, makes it an intriguing option for long-term human presence in the outer solar system. Such missions remain firmly in the realm of distant future planning, but the data gathered by Galileo contributed to making these plans at least theoretically feasible. The investigation of Callisto's gravity field through tracking of the spacecraft during its flybys provided additional insight into the Moon's interior structure. Unlike Ganymede, which appears to have a differentiated interior with a dense core, mantle, and icy outer shell, Callisto seems to be only partially differentiated, with rock and ice mixed together throughout much of its interior rather than separated into distinct layers. This finding was somewhat unexpected, as scientists had assumed that all large icy moons would have experienced enough internal heating during their formation to allow denser materials to sink toward the center. Callisto's apparent lack of complete differentiation suggests that it may have formed more slowly or experienced less heating than its siblings, allowing it to retain a more primordial interior structure. The partial differentiation of Callisto adds another piece to the puzzle of how this moon maintains a possible subsurface ocean despite its lack of tidal heating. If rock and ice remain mixed throughout the interior rather than separating into distinct layers, the radioactive elements within the rocky material would be distributed throughout the Moon rather than concentrated in a core, potentially providing a more uniform but less intense heat source. Whether this distributed heating is sufficient to maintain liquid water at depth remains an open question, one that future missions carrying more sensitive instruments may eventually answer. Galileo's cameras captured the texture of Callisto's surface in remarkable detail during the close flybys, revealing a landscape that tells the story of 4 billion years of bombardment. Every square kilometer is pockmarked with craters, and the craters themselves are cratered, and those smaller craters have still smaller craters within them, creating a nested hierarchy of impacts that speaks to the relentless rain of debris that has fallen onto this moon throughout solar system history. The saturation of craters is so complete that the formation of each new impact crater necessarily destroys evidence of older ones, and the surface has reached a kind of equilibrium state in which the rate of crater formation is balanced by the rate of crater destruction. This equilibrium state makes crater counting on Callisto's oldest terrain somewhat challenging, as the standard techniques for determining surface age through crater statistics begin to break down when surfaces become completely saturated. Scientists must use sophisticated statistical methods to extract age information from such terrains, comparing the size-frequency distribution of craters to models of how impactor populations evolved over solar system history. The results consistently point to an age of approximately 4 billion years for essentially all of Callisto's surface, confirming that no significant resurfacing has occurred since the end of the heavy bombardment period. The Galileo mission's investigation of Callisto thus revealed a world that embodies deep time in a way that few other objects in the solar system can match. Its surface preserves a record of events that occurred when the solar system was young, when the planets were still accreting the last of the debris from their formation, and when collisions were a defining feature of the cosmic environment. Walking across Callisto's surface, were such a thing possible, would be walking across a landscape shaped entirely by events that occurred before life had even arisen on Earth, a terrain of incomprehensible antiquity preserved in the cold darkness of the outer solar system. Yet beneath that ancient surface, there may lie an ocean, a reservoir of liquid water hidden from view but detected through the subtle signature of induced magnetic fields. The contrast between the utterly unchanging exterior and the potentially dynamic interior gives Callisto a dual nature that makes it more interesting than its battered appearance might suggest. It stands as a reminder that appearances can be deceiving in planetary science, and that even the most apparently dead and uninteresting worlds can harbor secrets that challenge our understanding. The spacecraft's final observations of Callisto contributed to a body of knowledge that will inform future exploration of the Jupiter system for decades to come. Each flyby added details to the global map, refined the understanding of surface composition, and improved the models of interior structure. The data transmitted back to Earth during those encounters continues to be analyzed and reanalyzed as techniques improve and new questions arise. Callisto may be the most ancient and unchanged of the Galilean moons, but the scientific exploration of its nature is an ongoing process, building gradually toward a more complete understanding of this battered relic of solar system history. And now we turn our attention to the great planet itself, to the swirling, banded world that dominates its corner of the solar system with such quiet authority, and we shall spend some time together considering what the Galileo spacecraft revealed about the atmosphere of Jupiter, that vast envelope of gases and clouds and storms that has fascinated observers for centuries, and which, during the years of the Galileo mission, yielded secrets that had remained hidden since the planet first formed some 4.5 billion years ago. Jupiter's atmosphere is not a thin shell surrounding a solid surface, as is the case with our own familiar Earth, but rather a deep and continuous ocean of gas that gradually thickens and warms as one descends, eventually transitioning into liquid and perhaps, at great depth, into something approaching a metallic state, though we shall not venture quite so far down in our present discussion, content instead to drift among the clouds and storms that Galileo observed with such patience and precision over its many years of orbiting this enormous world. The spacecraft carried instruments that could see in wavelengths of light invisible to human eyes, and these instruments peered into the Jovian atmosphere at different depths, building up a picture of the cloud layers and the movements within them. And what they found was a world of extraordinary complexity, where storms can persist for centuries and where the weather patterns we observe from afar are merely the surface expression of processes occurring far below. Perhaps the most famous feature of Jupiter's atmosphere is the Great Red Spot, that oval storm system that has been observed continuously since at least the 17th century, when early telescope users first noted a persistent marking in Jupiter's southern hemisphere, and Galileo devoted considerable attention to this remarkable phenomenon, tracking its behavior over the course of the mission and revealing details of its internal structure that had never before been discernible. The Great Red Spot is an anticyclonic storm, which means that it rotates in the opposite direction to cyclones on Earth, spinning counterclockwise in Jupiter's southern hemisphere, and Galileo's cameras and spectrometers showed that this rotation is not uniform throughout the storm but varies with position, with the outer edges rotating more rapidly than the interior regions, and with complex interactions occurring where the storm meets the surrounding atmospheric flows. Wind speeds within and around the Great Red Spot were measured by tracking cloud features from one image to the next, a technique that required Galileo to observe the same region multiple times over periods of hours or days. And these measurements revealed that winds at the periphery of the storm exceed 400 kilometers per hour, which is considerably faster than the most powerful hurricanes ever recorded on Earth. And yet these winds have been blowing, more or less continuously, for at least 3.5 centuries, and possibly much longer. The interior of the Great Red Spot proved to be surprisingly complex, with multiple vortices rotating within the larger circulation, almost like smaller storms embedded within the Great Storm. And these internal features were observed to drift and merge and occasionally to be ejected into the surrounding atmosphere, where they would be sheared apart by the differential rotation of Jupiter's cloud bands, a process that Galileo documented in exquisite detail over many orbits. The color of the Great Red Spot has long puzzled observers, for it ranges from a deep brick red to a pale salmon pink, and sometimes fades almost to the white or cream color of surrounding clouds. And while Galileo's instruments helped to characterize the spectral properties of this coloration, the precise chemical responsible for the red hue remained somewhat elusive, with various compounds of sulfur and phosphorus proposed as candidates, though the matter was not definitively settled during the mission. Beyond the Great Red Spot, Galileo observed many other storm systems in Jupiter's atmosphere, some of them quite large and long-lived, though none quite so enduring as the Great Red Spot itself. And among the most interesting observations was the detection and tracking of a feature that came to be known as Oval Ba, or, more colloquially, Red Junior, which formed during the Galileo mission from the merger of three smaller white oval storms that had themselves been observed for decades. These three white ovals, which had been designated with rather prosaic names based on their positions, began to interact with one another in the late 1990s, and Galileo watched as two of them merged in 1998. And then as the resulting combined storm merged with the third oval in 2000, producing a single large storm system that was roughly half the diameter of the Great Red Spot, and which, some years after Galileo's mission ended, began to develop a reddish coloration of its own, hence the nickname Red Junior. This observation of storm merger was particularly valuable because it demonstrated that long-lived storm systems on Jupiter can form from the coalescence of smaller storms. And this has implications for understanding how the Great Red Spot itself might have originated, perhaps from the merger of many smaller storms over a period of years or decades or centuries, growing gradually to its present immense size, though we cannot know for certain because no spacecraft was present to observe those early stages. Jupiter's atmosphere is organized into a series of alternating light and dark bands that circle the planet parallel to its equator, and these bands have been given names, with the light bands called zones and the dark bands called belts. And one of the questions that scientists hoped Galileo would help answer was how deep these banded structures extend into the atmosphere, whether they are merely a shallow surface phenomenon or whether they represent the visible expression of circulation patterns that penetrate far into the planetary interior. Galileo's observations, combined with measurements from the atmospheric probe that descended into Jupiter in December 1995, suggested that the belts and zones extend much deeper than had been anticipated, with the wind patterns persisting to depths where the pressure is many times greater than at the visible cloud tops, indicating that the banded structure is not merely a superficial skin, but rather a fundamental feature of Jupiter's atmospheric dynamics, extending down for hundreds of kilometers at the very least. The atmospheric probe itself, that small capsule that separated from the main spacecraft and plunged into Jupiter's atmosphere on the 7th of December 1995, provided direct measurements of conditions below the clouds that could not have been obtained in any other way, and its findings were both revealing and somewhat perplexing, for the region into which it descended turned out to be rather atypical of Jupiter's atmosphere as a whole. The probe entered Jupiter at a location within one of the so-called hotspots, which are regions where infrared radiation from deeper, warmer levels of the atmosphere can escape more easily because the overlying clouds are thinner or absent, and these hotspots appear as dark features in visible light images because they lack the bright ammonia ice clouds that cover most of the planet's disk. and Galileo's observations showed that they are regions of downwelling, where air is descending from above and warming as it is compressed by the increasing pressure at depth. Because the probe descended through one of these downwelling regions, it encountered an atmosphere that was much drier than expected, with far less water vapor than models of Jupiter's formation had predicted, and for some time this caused considerable puzzlement among scientists, who wondered whether Jupiter as a whole might be deficient in water, a finding that would have important implications for understanding how the planet formed and accumulated its tremendous mass of gas from the primordial solar nebula. However, subsequent analysis of Galileo's remote sensing data suggested that the probe entry site was simply an unusually dry region, and that water is probably present in greater abundance elsewhere in Jupiter's atmosphere, particularly in the zones where upwelling brings material from deeper levels to the cloud tops, and this interpretation was supported by observations from the Near-Infrared Mapping Spectrometer, or NIMS, which detected signatures of water ice clouds at certain depths and locations around the planet. The NIMS instrument was particularly valuable for studying the vertical structure of Jupiter's atmosphere because it could observe at wavelengths where different gases absorb light, and by measuring how much light at each wavelength was reflected back from different parts of the planet, scientists could deduce the composition and altitude of the various cloud layers, building up a three-dimensional picture of the atmospheric structure that complemented the two-dimensional views provided by the cameras. 3 main cloud layers were identified in Jupiter's atmosphere, with the uppermost layer composed of ammonia ice crystals floating at altitudes where the temperature is around -140 degrees Celsius, and below this a layer of ammonium hydrosulfide clouds at somewhat warmer temperatures and higher pressures, and below that, deeper still, a layer of water ice and liquid water clouds, though this deepest layer was often obscured from view by the overlying cloud decks and could only be glimpsed in certain regions where gaps in the upper clouds permitted a view to greater depths. The ammonia ice clouds are responsible for the bright appearance of Jupiter's zones, those light-colored bands that alternate with the darker belts, and Galileo's cameras captured images of these clouds with unprecedented clarity, revealing them to be not smooth and featureless but textured and dynamic, with waves and ripples and turbulent eddies visible at the finest scales the cameras could resolve. One of the more dramatic discoveries made by Galileo concerned the thunderstorms that occur in Jupiter's atmosphere, for the spacecraft detected powerful lightning flashes that illuminated the clouds from within, particularly on the night side of the planet where the flashes could be seen against the darkness without interference from reflected sunlight, and measurements of these lightning bolts indicated that they were extraordinarily energetic, roughly 1,000 times more powerful than typical lightning strikes on Earth. These Jovian thunderstorms were found to be concentrated in certain regions of the planet, particularly near the boundaries between belts and zones where wind shear creates conditions favorable for the development of convective storms, and the storms themselves were observed to be towering structures, with cloud tops extending high above the surrounding deck, much as cumulonimbus clouds on Earth tower above the flatter stratus and stratocumulus clouds nearby. The energy source for these storms is the same as for thunderstorms on Earth, namely the release of latent heat when water vapor condenses into liquid droplets or ice crystals, and the fact that such powerful storms occur on Jupiter confirms that water is present in the atmosphere at levels sufficient to drive vigorous convection, even if the probe entry site happened to be anomalously dry. Over the course of its multi-year mission, Galileo observed Jupiter through many complete rotations, watching as features drifted around the planet at different rates depending on their latitude. For Jupiter's atmosphere exhibits differential rotation, with the equatorial regions completing a full rotation in just under 10 hours, while regions near the poles take a few minutes longer. And this differential rotation causes features at different latitudes to slowly shift position relative to one another. By tracking features over many rotations, scientists could measure the wind speeds at different latitudes with great precision, and these measurements revealed a pattern of alternating eastward and westward jets that correspond roughly to the boundaries between belts and zones, with the fastest winds occurring in a strong eastward jet at the equator that moves at several hundred kilometers per hour relative to the planet's interior rotation. Galileo also observed wave patterns and oscillations in Jupiter's atmosphere that varied over timescales of weeks to months to years, including quasi-periodic disturbances that propagated around the planet at predictable rates. And these observations hinted at complex interactions between different layers of the atmosphere, and possibly between the atmosphere and the deep interior, though disentangling all of these effects required years of careful analysis after the mission ended. The creation of global maps of Jupiter's cloud structure was one of the major achievements of the Galileo mission, for previous spacecraft had only glimpsed portions of the planet during their brief flybys, whereas Galileo orbited Jupiter for nearly 8 years, observing the planet from many different angles and at many different times. And by combining images taken through different filters and at different wavelengths, scientists were able to construct maps showing the distribution of different cloud types and the variations in cloud height across the entire visible disk. These maps revealed that Jupiter's atmosphere, while appearing superficially simple with its regular pattern of belts and zones, is actually enormously complex when examined in detail, with countless small storms and eddies and waves superimposed on the larger scale circulation, and with the appearance changing noticeably from one rotation to the next as features evolve and interact and occasionally disappear entirely only to be replaced by new disturbances forming elsewhere. The equatorial hotspots, those regions where the atmospheric probe descended, were revealed by Galileo's imaging and spectroscopic observations to be quasi-regularly spaced around the planet's equator, occurring at intervals of roughly 15 to 20 degrees of longitude, and their spacing and behavior suggested that they might be related to a planetary-scale wave pattern in the atmosphere, with the hotspots representing the troughs of this wave where downwelling occurs and the intervening regions representing the crests where upwelling brings moisture and ammonia-rich air to higher altitudes. This interpretation helped to explain why the probe encountered such dry conditions. For if the hotspots are indeed downwelling regions analogous to the subtropical dry zones on Earth where air descends after rising in the tropical convection zones, then one would expect them to be depleted in condensable species like water vapor, which would have been removed by condensation as the air rose elsewhere and would not have been replenished as the now dry air descended through the hotspot. The temperature structure of Jupiter's atmosphere was also mapped by Galileo's instruments, revealing variations of several degrees Celsius from one location to another at a given pressure level, with the belts generally being warmer than the zones at cloud top level but cooler at higher altitudes, a pattern consistent with the belts being regions of general downwelling where adiabatic heating warms the descending air and the zones being regions of upwelling where adiabatic cooling produces the lower temperatures associated with rising air. Jupiter radiates more energy into space than it receives from the Sun, a consequence of the planet's slow gravitational contraction and the release of potential energy as denser material sinks toward the center. And this internal heat source drives the atmospheric circulation in ways that differ fundamentally from the solar-driven circulation of Earth's atmosphere. And Galileo's observations help to constrain models of how this internal heat is transported through the atmosphere and eventually radiated away into the coldness of space. The colors of Jupiter's clouds, ranging from white through yellow and orange to brown and occasionally reddish hues, are produced by trace chemical compounds that form in the atmosphere through photochemical reactions driven by ultraviolet light from the Sun, and while the exact identities of all the chromophores, as these color-producing compounds are called, were not definitively established by Galileo, the mission provided valuable constraints on their spectral properties and their distribution across the planet's disk. As we consider all of these observations together, a picture emerges of Jupiter as a dynamic and ever-changing world, where storms can last for centuries but where the details of the cloud patterns shift from day to day, where lightning illuminates the deep clouds with flashes of stupendous power, where winds howl at speeds that would be unimaginable on Earth, and where the interplay of heat from below and radiation to space above drives a circulation of tremendous complexity, all wrapped around a planet so large that more than 1,000 Earths could fit within its volume. And yet, for all its violence and power, there is something almost soothing about contemplating Jupiter's atmosphere, perhaps because its timescales are so different from our own, with storms that have outlasted human civilizations and will likely continue long after our present concerns have faded into history. And there is a certain comfort in knowing that the great red spot will still be spinning, more or less as it has always spun, while we rest here in the quiet of this present moment. And so we come now to consider something altogether invisible, something you cannot see in any photograph, and yet something so vast that it dwarfs the planet itself many times over. This is the magnetosphere of Jupiter, that immense bubble of magnetic influence that surrounds the giant world and extends outward into space for distances that challenge our intuition. The Galileo spacecraft, in its patient years of orbiting, devoted considerable attention to measuring and mapping this invisible empire, revealing it to be the largest structure in our solar system aside from the heliosphere of the Sun itself. It is a realm of charged particles and magnetic field lines, of radiation and radio waves, and it stretches so far from Jupiter that its tail reaches beyond the orbit of Saturn, brushing against the path of that distant ringed world some 700 million kilometers away from the Sun. To understand what Galileo found, we must first appreciate that Jupiter possesses a magnetic field of extraordinary strength, generated deep within the planet where hydrogen is compressed so thoroughly that it behaves as a liquid metal, conducting electricity and churning with convective motions that give rise to powerful electrical currents. At Jupiter's equator, the spacecraft measured a field strength of approximately 4.28 Gauss, which may seem an abstract number until we compare it with our own planet, where the magnetic field at the equator measures roughly 0.3 Gauss. This means that Jupiter's equatorial field is approximately 14 times stronger than Earth's, a considerable difference that hints at the scale of everything we shall discuss in this section. This powerful field reaches out from the planet in all directions, carving a cavity in the solar wind, that stream of charged particles flowing constantly outward from the Sun, and within this cavity, Jupiter maintains its own domain of magnetic influence. The shape of this magnetosphere is not a simple sphere, despite what the name might suggest. On the side facing the Sun, the solar wind compresses the magnetic field, pushing the boundary inward to a distance of perhaps 50 to 100 Jupiter radii, depending on the varying pressure of the solar wind at any given time. 1 Jupiter radius is approximately 71,000 kilometers, so even this compressed sunward boundary lies several million kilometers from the cloud tops. But on the side facing away from the Sun, the magnetosphere is stretched and elongated by the solar wind's passage, drawn out into an immense tail that extends far, far into the outer solar system. Galileo's measurements, combined with observations from other spacecraft passing through the region, confirmed that this magnetotail reaches outward for at least 650 million kilometers, and possibly further still, a distance so great that it occasionally brushes against the orbit of Saturn itself when the two planets are appropriately aligned in their journeys around the Sun. Within this vast magnetic realm, Galileo discovered intricate structures and dynamic processes that had only been glimpsed by earlier flyby missions. Perhaps the most striking of these was the plasma torus associated with the moon Io, that volcanically active world whose eruptions we discussed in an earlier section. The volcanoes of Io do not merely reshape the moon's surface, you see, but they also inject material directly into Jupiter's magnetosphere, creating a donut-shaped ring of charged particles that encircles the planet along Io's orbital path. This plasma torus contains primarily sulfur and oxygen ions, the products of Io's sulfur dioxide volcanic gases, which are stripped of their electrons by ultraviolet radiation from the Sun and by collisions with other energetic particles. Galileo passed through this torus on multiple occasions, measuring its density and composition with instruments designed for precisely this purpose, and the spacecraft found it to be a substantial structure, containing perhaps 1,000 kilograms of new material injected by Io's volcanoes every single second. 1,000 kilograms per second may sound like an enormous rate, and indeed it is, amounting to roughly 100,000 tons of material added to the magnetosphere each day. This volcanic output feeds the entire magnetospheric system, providing the raw material that populates Jupiter's radiation belts and contributes to the processes we shall describe shortly. The ions in the plasma torus are not stationary, of course, but are swept along by Jupiter's rapid rotation, for the planet completes one rotation in just under 10 hours, and this rotation drags the magnetic field lines and the charged particles along with it. The torus therefore rotates with Jupiter, and its particles spiral along the magnetic field lines, gradually diffusing both inward toward the planet and outward toward the more distant reaches of the magnetosphere. Galileo also conducted extensive measurements of Jupiter's radiation belts, those regions where charged particles are trapped by the magnetic field and accelerated to tremendous energies. Unlike the plasma torus, which is concentrated near Io's orbit, the radiation belts extend from close to the planet outward to varying distances, with the most intense radiation found in the inner regions. The spacecraft detected electrons and protons with energies exceeding 20 million electron volts, abbreviated as 20 MeV, and in some locations the particle fluxes were so intense that they posed serious hazards to the spacecraft itself. These particles spiral rapidly along the magnetic field lines, bouncing back and forth between the northern and southern hemispheres, trapped in a magnetic bottle from which they cannot easily escape. The inner radiation belt of Jupiter is considerably more intense than Earth's Van Allen belts, and the particles there have energies high enough to penetrate shielding and damage electronic components. This brings us to the considerable challenges that Jupiter's magnetic environment posed for the Galileo mission, a subject we should address before continuing further. The spacecraft had been designed with the Jovian radiation environment in mind, of course, with sensitive electronics housed within a shielded vault intended to protect them from the worst effects of the bombardment. But even with this protection, the cumulative radiation dose accumulated over the years of orbital operations took its toll on various systems. The star scanner, which helped determine the spacecraft's orientation, was particularly affected, occasionally producing spurious signals or missing stars altogether when energetic particles struck its detectors. Other instruments experienced gradual degradation, and the spacecraft's computer memory accumulated errors that the onboard software had to manage and correct. That Galileo continued to function for so many years in this hostile environment is a testament to both its robust engineering and the adaptability of the mission operations team, who learned to work around the various anomalies and degradations as they arose. Returning now to Galileo's scientific findings, the spacecraft made detailed observations of the radio emissions produced by Jupiter's magnetosphere, electromagnetic waves generated by the complex interactions of charged particles and magnetic fields. Jupiter had been known as a radio source since the 1950s, when astronomers using radio telescopes first detected the planet's emissions. But Galileo was able to study these emissions from within the magnetosphere itself, revealing new details about their origin and characteristics. The spacecraft found that certain types of radio emission were strongly correlated with the orbital position of Io, a relationship that had been suspected from ground-based observations but was now confirmed with direct measurements. When Io reaches particular positions in its orbit relative to Earth-based observers, or relative to the spacecraft, the radio emissions intensify in predictable patterns, revealing the Moon's influence on the magnetospheric processes that generate these waves. This correlation between Io and the radio emissions points to one of the most remarkable phenomena in Jupiter's magnetosphere: the flux tube that connects the planet to its volcanic moon. A flux tube is essentially a bundle of magnetic field lines that threads through space between 2 points, and in the case of Jupiter and Io, this flux tube carries an electrical current of staggering proportions. As Io moves through the magnetosphere, plowing through the plasma torus and the magnetic field, it generates an electrical potential across its diameter, much as a wire moving through a magnetic field generates a voltage in a simple electrical generator. This potential drives an electrical current along the magnetic field lines, flowing from Io to Jupiter's ionosphere, then through Jupiter's upper atmosphere, and back to Io along a parallel set of field lines. Galileo's measurements suggested that this circuit carries a current of approximately 1 to 5 million amperes, depending on the conditions, a flow of electrical charge that would be impressive by any terrestrial standard. The flux tube current does not simply flow and dissipate quietly, but rather deposits its energy into Jupiter's atmosphere, contributing to the auroral displays observed at the planet's poles. Just as Earth experiences aurorae, those shimmering curtains of light that appear in polar skies when charged particles from the Sun interact with our atmosphere, Jupiter too displays auroral activity, though on a far grander scale. Galileo observed these aurorae using its ultraviolet spectrometer, detecting emissions from hydrogen molecules and atoms that were excited by the impact of energetic particles. The Jovian aurorae form bright ovals around each magnetic pole, but they also show distinctive bright spots at the locations where the flux tubes connecting to the Galilean moons intersect the atmosphere. The brightest of these spots corresponds to Io's flux tube, but fainter spots were also detected at the magnetic footprints of Europa and Ganymede, indicating that these moons too interact with the magnetosphere and drive currents along field lines to the planet. The auroral power on Jupiter is immense, estimated at several terawatts, which is many times the total electrical generating capacity of human civilization. This energy comes not from the solar wind, as is primarily the case for Earth's aurorae, but from Jupiter's own rotation, which transfers energy through the magnetic field to the plasma in the magnetosphere and ultimately to the auroral regions. The planet's rapid rotation is the engine that drives much of the magnetospheric dynamics, spinning the plasma around and flinging it outward through centrifugal effects, creating a disc-shaped structure in the middle magnetosphere that rotates with the planet. Galileo mapped this structure in detail, revealing how the plasma disk warps and flaps in response to the solar wind's pressure, tilting back and forth as Jupiter rotates because the magnetic axis is tilted roughly 10 degrees from the rotation axis. The Galilean moons, in their steady orbits around Jupiter, do not merely add material to the magnetosphere or generate flux tube currents, but they also modify the magnetic field structure in their immediate vicinity. Ganymede, as we mentioned in an earlier section, possesses its own internal magnetic field, and this field creates a small magnetosphere within Jupiter's larger one, a bubble within a bubble. Galileo discovered this remarkable feature during its close flybys of Ganymede, detecting the characteristic signatures of a magnetopause boundary where Ganymede's field meets Jupiter's. This makes Ganymede the only moon in the solar system known to possess an internally generated magnetic field, and the interactions between its magnetosphere and Jupiter's create complex particle dynamics and field configurations that Galileo worked to untangle over the course of multiple encounters. Europa and Callisto, lacking internal dynamos, nonetheless interact with the magnetosphere in their own ways. Galileo detected signs of induced magnetic fields at both moons, fields generated not by internal processes but by the changing magnetic environment as Jupiter's tilted field sweeps past them. For a conducting layer, such as a subsurface ocean of salty water, to produce such induced fields, and the measurements at Europa were particularly suggestive of such a layer, providing evidence that complemented the geological observations we discussed previously. The magnetospheric interactions thus contributed to our understanding of the Moon's internal structures, demonstrating how the study of invisible magnetic fields can reveal hidden features beneath icy surfaces. Galileo also investigated how the moons absorb energetic particles from the radiation belts, creating shadows or depletions in the particle populations along their orbits. When the spacecraft crossed through the magnetic flux tubes of the various moons, it detected changes in the particle fluxes consistent with the moons sweeping up particles in their path. These observations helped scientists understand how the radiation belts are populated and depleted over time, contributing to models of the overall dynamics of the magnetospheric system. The moons act as sinks for radiation belt particles, removing material that would otherwise accumulate indefinitely, and this loss process must be balanced by the various source mechanisms, including the io-plasma torus and the capture of solar wind particles at the magnetopause. The detailed measurements from Galileo revealed that Jupiter's magnetosphere is not a static structure but a dynamic system constantly adjusting to internal and external influences. The solar wind pressure varies over time, causing the magnetopause to move inward and outward, sometimes quite rapidly. The volcanic output from Io fluctuates as eruptions wax and wane, changing the rate at which new plasma is added to the torus. The rotation of the planet drives continuous circulation and energy transfer throughout the system, and the moons in their orbits create periodic perturbations as they pass through different magnetic and plasma environments. All of these factors combine to produce a magnetosphere that is in constant motion, never quite the same from one moment to the next, yet maintaining its essential character as a vast magnetic domain dominated by the influence of the giant planet at its center. In the outermost reaches of the magnetosphere, where the magnetic field weakens and the solar wind's influence grows stronger, Galileo observed the complex boundary regions where Jupiter's domain meets interplanetary space. The magnetopause, That boundary separating the magnetosphere from the solar wind proved to be a dynamic surface that responds to changes in solar wind pressure over timescales of hours to days. Upstream of the magnetopause, the spacecraft sometimes detected the bow shock, where the supersonic solar wind first encounters the obstacle of Jupiter's magnetic field and abruptly slows and heats, much as a shock wave forms ahead of a supersonic aircraft. These boundary crossings provided valuable data on how the magnetosphere interacts with its environment, exchanging energy and particles with the solar wind in processes that are still being studied and modeled today. As we reflect on Galileo's exploration of Jupiter's magnetic realm, we find ourselves contemplating an invisible empire of staggering proportions, a structure so large that it would appear bigger than the Sun if our eyes could see magnetic fields as they see light. Within this empire, volcanoes on a small moon inject material that spreads throughout the system. Moons with hidden oceans generate induced magnetic fields. Currents of millions of amperes flow along invisible field lines, and auroral displays powered by the planet's own rotation illuminate the polar skies with ultraviolet light. Galileo revealed all of this and more during its years of patient observation, transforming our understanding of planetary magnetospheres and demonstrating that the invisible forces shaping the space environment around a giant planet are just as worthy of study as the clouds and moons we can photograph. And so the spacecraft continued its work, orbit after orbit, measuring the magnetic fields and plasma populations, detecting radio waves and energetic particles, building up a comprehensive picture of Jupiter's magnetosphere that scientists would study for decades to come. The data filled the archives, numbers and measurements that described the invisible realm with the same precision that the images described the visible one. It was quiet work, in a sense, the patient accumulation of measurements from instruments that had no dramatic pictures to return, only the steady flow of numbers that, when properly analyzed, revealed the hidden structure of the giant's invisible empire. And so we turn now to the smaller members of Jupiter's family, those modest companions that orbit the great planet in relative obscurity, their diminutive sizes having kept them largely mysterious until Galileo arrived to study them with patient attention, revealing worlds that, while tiny by planetary standards, offered their own quiet contributions to our understanding of how solar systems arrange themselves and how material moves and settles around giant planets over the long spans of cosmic time. Jupiter, you see, is not merely attended by 4 large moons but by a considerable retinue of smaller bodies, some huddled close to the planet in rapid orbits that carry them through the tenuous ring system, others wandering at tremendous distances in paths that suggest they were not born alongside Jupiter at all, but rather captured later, guests who arrived and stayed, held gently by gravity in orbits that speak to chance encounters long ago. And the Galileo mission, along with ground-based observations conducted during those same years, would come to reveal this population in far greater detail than ever before, adding substantially to the catalogue of known Jovian moons and providing the first close observations of some of the most intriguing small bodies in the system. Among the inner moons, 4 deserve particular mention, and these are Metis, Adraste, Amalthea, and Thebe, arranged here in order of their distance from Jupiter, each one a small and irregularly shaped body that orbits within or near the planet's faint ring system, and each one tied intimately to the dynamics of dust and debris that populate this region of space, their surfaces continually bombarded by micrometeoroids that knock loose particles which then drift into the rings, maintaining those tenuous structures against the forces that would otherwise cause them to dissipate over time. Metis, the innermost of these moons, orbits Jupiter at a distance of roughly 128,000 kilometers from the planet's center, which places it within the main ring itself, a location of some consequence for understanding how that ring is sustained. And while Galileo could not approach Metis closely, the spacecraft did obtain images that revealed a body approximately 40 kilometers across, irregular in shape as one might expect for an object too small for gravity to pull into a sphere, its surface dark and presumably covered with the same reddish material that coats its neighboring moons, though the resolution of the images was not sufficient to reveal surface features in detail, leaving Metis as something of a shadowy presence, known more for its location and its role in the ring system than for its individual characteristics. Asteroid orbits just beyond Metis, at a distance of approximately 129,000 kilometers from Jupiter's center, making it the second innermost known moon, and it is smaller still than Metis, measuring perhaps 20 kilometers across. A tiny body that nonetheless plays its part in the ring dynamics, contributing material to the main ring just as Metis does. The two moons together acting as sources that replenish the ring particles lost to various processes, including the gradual spiraling of dust grains inward toward Jupiter under the influence of electromagnetic forces and the sweeping effects of the ring material itself. And so these two small moons, Metis and Asteroid, while unremarkable in themselves, proved essential to explaining why Jupiter's main ring exists at all, for without such sources of fresh material, the ring would have dispersed long ago, fading into nothing over timescales far shorter than the age of the solar system. Thebe, the outermost of the four inner moons we are considering, orbits at a distance of about 222,000 kilometers from Jupiter, well beyond the main ring but intimately connected to another ring structure known as the Gossamer Ring, a remarkably faint band of material that extends inward from Thebe's orbit, its particles so sparse that they are essentially invisible except when viewed at particular angles with sensitive instruments. And Galileo's observations revealed Thebe to be a body roughly 100 kilometers across, irregular in shape like its companions, with a surface marked by impact craters that spoke to the long history of bombardment that all bodies in the solar system have endured. And the connection between Thebe and the Gossamer Ring became clear as scientists analyzed the data, recognizing that material knocked from Thebe's surface by micrometeoroid impacts drifts inward under the influence of various forces, populating the Gossamer Ring with the fine dust that gives it what little substance it possesses. But it was Amalthea that received the most attention from the Galileo spacecraft, and rightly so, for Amalthea is the largest of Jupiter's inner moons, a body substantial enough to have been discovered from Earth long before the space age, having been spotted in 1892 by the American astronomer Edward Emerson Barnard, who found it while observing Jupiter through the 36-inch refractor at Lick Observatory, and for decades Amalthea remained the only known moon of Jupiter beyond the four Galilean satellites, a solitary small companion whose nature could only be guessed at from Earth-based observations. And so when Galileo arrived at Jupiter, there was considerable interest in studying this moon more closely, an interest that would culminate in one of the mission's most daring encounters. Amalthea's orbit carries it around Jupiter at a distance of approximately 181,000 kilometers from the planet center, placing it between the orbits of Thebe farther out and Asteroid closer in. And this location puts it in the region where the Gossamer Ring begins to form. For just as Thebe contributes material to the outer Gossamer Ring, Amalthea contributes to an inner Gossamer Ring that extends from its orbit inward toward the main ring, the two Gossamer Rings together forming a faint nested structure that Galileo's instruments mapped with care, revealing the gentle gradient of material density that reflected the continuous supply of dust from these two small moons. The Galileo spacecraft made several observations of Amalthea during its years in the Jovian system, gradually building up a picture of this irregular body, but the most significant encounter was saved for near the end of the mission, when the spacecraft was directed to fly past Amalthea at extraordinarily close range, a flyby that took place on the 5th of November 2002. Just a few months before Galileo's planned destruction in Jupiter's atmosphere. And during this encounter, the spacecraft passed within approximately 160 kilometers of Amalthea's surface, a distance so small that it represented the closest approach to any Jovian body during the entire mission, closer even than the daring flybys of the Galilean moons that had yielded such remarkable discoveries. And this proximity was essential for gathering certain types of data that required the spacecraft to pass through Amalthea's immediate gravitational influence. The images and measurements returned from this encounter revealed Amalthea to be a profoundly irregular body, elongated and lumpy in form, with dimensions of approximately 270 kilometers along its longest axis, 166 kilometers along its intermediate axis, and 150 kilometers along its shortest axis, giving it a shape somewhat like a potato or perhaps a slightly flattened ellipsoid, the kind of form that results when a body is too small for its own gravity to overcome the structural strength of its rocky material and pull it into a sphere. And this irregular shape, combined with the Moon's synchronous rotation that keeps its long axis pointed toward Jupiter, means that the gravitational pull felt on Amalthea's surface varies considerably from place to place, a detail of purely academic interest perhaps, but one that speaks to the exotic nature of these small worlds that differ so fundamentally from the planets and large moons with which we are more familiar. The surface of Amalthea proved to be remarkably dark and deeply red in color, a coloration that scientists attributed to contamination by sulfur compounds, material that originates from the volcanic moon Io and spreads throughout the inner Jovian system, coating surfaces with a reddish patina that alters their appearance and spectral properties. And this sulfur connection linked Amalthea to the broader story of material transport in the Jovian environment, where Io's volcanic output creates a torus of ions and neutral atoms that gradually disperses and interacts with other bodies, leaving its chemical signature across the inner moon system, a reminder that these worlds do not exist in isolation but are connected by the movement of matter through shared space. The surface features observed on Amalthea included two notably large impact craters, named Pan and Gaia, each roughly spanning a significant fraction of the Moon's diameter, and these craters spoke to violent events in Amalthea's past, collisions with other bodies that must have come perilously close to shattering the little Moon entirely. And indeed, the images suggested that Amalthea's surface is crossed by grooves and ridges that might represent fractures propagating through the body's interior, evidence of the stresses imparted by those ancient impacts. And this battered appearance reinforced the impression of a body that has survived much abuse over the history of the solar system, enduring in its orbit despite the hazards of its location. But perhaps the most surprising discovery about Amalthea came not from the images but from the gravitational data collected during the close flyby. For by carefully tracking the Doppler shift in Galileo's radio signal as it passed near Amalthea, scientists could measure the tiny acceleration imparted to the spacecraft by the Moon's gravity. And from this acceleration they could calculate Amalthea's mass. And when they combined this mass measurement with the volume estimated from the images, they obtained a figure for Amalthea's density that was startlingly low, less than the density of water, somewhere around 0.86 grams per cubic centimeter, a value that seemed almost impossible for a rocky body until one considered what it might imply about Amalthea's internal structure. For a body made of rock, which typically has a density of 2 to 3 grams per cubic centimeter or more, To have an overall density less than water suggests that the body must contain substantial empty space, voids and gaps that reduce its average density below what solid rock would provide. And this led scientists to propose that Amalthea is not a solid coherent object at all, but rather a rubble pile, an aggregation of fragments loosely held together by gravity, the pieces having originally come from a larger body that was shattered by impact long ago. The debris then gradually reassembling into the irregular mass we observe today. Or perhaps Amalthea was built up from separate pieces that never fully consolidated in the first place, accumulating gently over time without ever being compressed into solid rock. And either interpretation points to an internal structure riddled with cavities and gaps, a body that is more empty space than solid material, held together by the gentlest of gravitational bonds. This rubble pile interpretation has significant implications for understanding the history and dynamics of Jupiter's inner moon system, for it suggests that catastrophic collisions have played an important role in shaping these bodies, breaking them apart and allowing them to reassemble. And it implies that the current population of inner moons may represent just one stage in a long and ongoing process of destruction and reformation, a cycle that may have produced earlier generations of moons that are now lost to us, their remnants perhaps incorporated into the current moons or dispersed into the ring system. And so the quiet orbit of Amalthea around Jupiter becomes a window into violent processes that have shaped this region over billions of years. Beyond these four inner moons, the Galileo era also saw a remarkable expansion in our knowledge of Jupiter's outer satellite population, those distant moons that orbit far from the planet in paths that are often highly eccentric and inclined, moving in directions and orientations that distinguish them sharply from the regular moons closer in. And while Galileo itself did not visit these outer moons, which would have required far more propellant than the spacecraft carried, ground-based observations conducted during the same period took advantage of improving telescope technology and search techniques to discover a wealth of new satellites, revealing Jupiter's moon system to be far more populous than previously known. During the years of the Galileo mission and the period immediately surrounding it, ground-based surveys identified 21 new small outer moons of Jupiter, a dramatic expansion of the known population that transformed our understanding of the Jovian satellite system. And these discoveries were made possible by sensitive CCD detectors and systematic search programs that could detect the faint points of light representing these tiny distant bodies as they moved slowly against the background stars, their motions revealing their gravitational bondage to Jupiter even at distances that might extend tens of millions of kilometers from the planet. And each new discovery added another entry to the catalogue, another data point for understanding how such populations arise and evolve. These outer moons share several characteristics that set them apart from the regular satellites closer to Jupiter, and the most notable of these characteristics is their orbital irregularity. For unlike the inner moons and the Galilean satellites, which orbit Jupiter in nearly circular paths close to the planet's equatorial plane, the outer moons often have highly elliptical orbits tilted at substantial angles, and many of them orbit in the retrograde direction, moving opposite to Jupiter's rotation and to the motion of most other bodies in the system, a configuration that cannot easily be explained by formation in place but instead suggests that these moons originated elsewhere and were captured by Jupiter's gravity at some point in the past. The capture hypothesis proposes that these outer irregular moons were once independent objects, perhaps asteroids or perhaps comets from the outer solar system, that wandered too close to Jupiter and found themselves unable to escape, trapped by gravitational interactions that robbed them of sufficient energy to continue on their way. And such capture events are not straightforward. For an object approaching Jupiter on a hyperbolic trajectory would normally swing past and depart again unless something acts to reduce its energy at the critical moment. And various mechanisms have been proposed to explain how this might occur, including interactions with Jupiter's extended atmosphere or with a disk of gas and debris that may have surrounded the young planet, or perhaps three-body interactions involving multiple objects. And while the details remain subjects of research, the general picture of captured origin has become widely accepted for these irregular outer moons. The orbital characteristics of the newly discovered moons showed interesting patterns, with many of them clustering into groups that share similar orbits, suggesting that these groups may represent the fragments of larger bodies that were captured intact and subsequently broken apart by collisions. Each original captured object giving rise to a family of smaller moons that continue to orbit in roughly similar paths, gradually spreading apart over time but retaining the signature of their common origin. And these groupings, sometimes named after prominent members, provide clues to the history of capture and disruption that has shaped the outer satellite population over the age of the solar system. The composition of these outer moons, while not directly measured by Galileo, can be inferred from their colors and reflective properties as observed from Earth, and these observations suggest that many of them resemble certain types of asteroids and comets, supporting the captured origin hypothesis and indicating that Jupiter's gravity has swept up a diverse collection of primitive material from the outer solar system. Objects that might otherwise have remained in the asteroid belt or the Kuiper belt or the scattered disk. Wanderers that found themselves caught by the giant planet and incorporated into its extensive satellite system. The importance of these observations, both of the inner moons by Galileo and of the outer moons by ground-based telescopes, extends beyond merely cataloguing the Jovian satellites, for they provide essential data for understanding how planetary satellite systems form and evolve more generally, the processes that operate around giant planets to create the diverse configurations we observe, from the regular moons that form in circumplanetary disks alongside their parent planets to the irregular moons that arrive later as captured interlopers, and the recognition that Jupiter's rings are sustained by material from the inner moons ties together the satellite system and the ring system into a unified picture of interacting components, material cycling between moons and rings in a slow dance that continues to the present day. And so as you rest now and your thoughts grow soft and indistinct, perhaps you might hold in mind this image of Jupiter attended by its many companions, the great Galilean moons that we have discussed at length and the smaller bodies that orbit in their shadows. The battered irregular Amalthea with its rubble pile interior and its deep red color. The tiny shepherds Metis and Adraste contributing their material to the faint ring that encircles the planet. Thebe and its gossamer ring spreading inward like a gentle veil. And far out in the darkness the swarm of captured wanderers tracing their eccentric paths. And all of this revealed or refined during the years that Galileo spent in patient study of the Jovian system. The spacecraft gathering data that would occupy scientists for years to come. Each discovery a small piece of a larger understanding that grows slowly and steadily like the accumulation of dust in a planetary ring. Grain by grain. Observation by observation, building toward a picture of how worlds arrange themselves around their central bodies. Jupiter's rings are among the most delicate and understated features of our solar system, a subtle adornment around the largest planet that whispers rather than shouts its presence to those who take the time to look carefully. When the Galileo spacecraft arrived at Jupiter in December of 1995, one of its quieter missions was to study these faint rings in far greater detail than had ever been possible before. Building upon the initial discovery made by Voyager 1 in 1979 and revealing the gentle processes that create and sustain this tenuous system of dust and tiny particles circling the giant planet. The story of Jupiter's rings is not one of grandeur or spectacle in the way that Saturn's magnificent rings capture our immediate attention, but rather a story of subtle beauty and delicate physics, of tiny moons shedding microscopic particles that drift slowly into graceful bands around their parent planet. And the Galileo mission would spend years patiently observing and measuring these faint structures to understand the quiet mechanisms at work. The discovery of Jupiter's rings by Voyager 1 came as something of a surprise to planetary scientists, who had not expected to find such a system around the giant planet, and the initial images showed only a thin, faint band of material that was difficult to see against the brightness of Jupiter itself. Those early observations confirmed that the rings existed but left many questions unanswered about their composition, their structure, and the sources of the material that comprised them, questions that would wait more than 15 years for Galileo to address in its methodical and thorough way. When Galileo began its systematic study of the Jovian ring system, it brought instruments far more sensitive than those aboard the Voyager spacecraft, along with the tremendous advantage of being able to observe the rings repeatedly over many orbits and from many different angles, building up a comprehensive picture that no brief flyby could ever achieve. The ring system of Jupiter, as Galileo confirmed and elaborated, consists of three main components that together form a delicate structure extending outward from the planet's cloud tops. The innermost component is called the halo, a thick torus of material that extends from about 92,000 kilometers from Jupiter's center down to the cloud tops themselves, forming a diffuse cloud of particles that surrounds the planet like a gentle mist. Above the halo lies the main ring, a relatively thin and flat band of material that extends from about 122,000 kilometers to about 129,000 kilometers from the planet center. And this main ring is the brightest and most clearly defined of Jupiter's ring components, though even at its brightest it remains far fainter than the rings we see around Saturn. Beyond the main ring lie the gossamer rings, extremely tenuous bands of material that extend outward to about 220,000 kilometers from Jupiter, named for their gossamer-thin appearance that makes them barely visible even under the best observing conditions. The halo component of Jupiter's ring system has a structure quite different from the flat rings we might expect, extending vertically above and below the ring plane in a thick, toroidal shape that Galileo's observations helped to characterize in detail. This vertical extent of the halo is caused by electromagnetic forces acting on the tiny charged particles that comprise it, as Jupiter's powerful magnetic field interacts with the dust grains and lifts them out of the ring plane into this more diffuse configuration. The particles in the halo are among the smallest in the ring system, predominantly in the micron size range and even smaller, and these tiny grains are particularly susceptible to the electromagnetic forces that give the halo its distinctive puffy appearance. Galileo's instruments measured the distribution of material within the halo and confirmed that it transitions gradually into the main ring above it, with no sharp boundary separating these two components, but rather a continuous change in the concentration and distribution of particles. The main ring of Jupiter, that relatively bright band lying just above the halo, presented Galileo with one of its most interesting discoveries about ring formation and maintenance. Through careful observation of the ring and the tiny moons embedded within it, Galileo's science team determined that the main ring is created and sustained by dust generated from impacts on two small inner moons, Metis and Adraste, which orbit within the ring itself. These two moons, each only a few tens of kilometers across, are continuously bombarded by micrometeoroids, tiny particles of interplanetary debris that strike their surfaces at high velocities and blast small particles of dust into orbit around Jupiter. Because Metis and Adraste have such weak gravitational fields, the dust ejected from their surfaces easily escapes into space rather than falling back to the Moon, and this dust then spreads out along the orbital paths of the moons to form the main ring that Galileo observed so carefully. This process of impact-generated dust production is a gentle one, occurring continuously but slowly over millions of years, and the particles that comprise the main ring have relatively short lifetimes compared to the age of the solar system. The dust grains in the main ring are gradually lost through various processes, including the drag of Jupiter's extended atmosphere on particles in the inner portions of the ring and the effects of solar radiation pressure on the smallest grains. And so the ring must be continuously replenished by new impacts on Metis and Adraste to maintain its current appearance. Galileo's observations helped scientists understand this delicate balance between dust production and dust loss that keeps the main ring in a steady state, neither growing brighter over time nor fading away entirely, but maintaining roughly the same appearance as long as the small moons continue to supply new material. The gossamer rings presented an even more subtle challenge for Galileo's instruments, as these extremely faint structures required careful observation and processing to reveal their full extent and character. Galileo discovered that the gossamer rings are not a single uniform structure but consist of two overlapping components, each associated with a different small moon of Jupiter. The inner gossamer ring extends from the outer edge of the main ring to approximately 181,000 kilometers from Jupiter and is created by dust knocked off the surface of Amalthea, a small irregular moon about 250 kilometers across that orbits at the outer edge of this ring component. The outer gossamer ring extends beyond this to approximately 220,000 kilometers and originates from Thebe, another small moon about 100 kilometers in diameter that marks the outer boundary of this most tenuous portion of Jupiter's ring system. The relationship between these gossamer rings and their source moons was established through Galileo's observations of how each ring component extends inward from the orbit of its parent moon but not significantly outward, a configuration that makes perfect sense once you understand the physics of dust dynamics around Jupiter. When micrometeoroids strike Amalthea or Thebe, the dust particles that are ejected have slightly less orbital energy than the Moon itself, and this means they follow orbits that bring them closer to Jupiter rather than farther away, gradually spreading inward to form the gossamer rings. The particles lose orbital energy through various subtle processes as they drift inward, including interactions with Jupiter's magnetic field and the gentle pressure of sunlight on their tiny surfaces. And this inward drift explains why each gossamer ring extends from its source moon toward Jupiter but not in the opposite direction. One of the most revealing observations that Galileo made of Jupiter's rings came when the spacecraft positioned itself to view the rings backlit by the sun, with Jupiter's bulk blocking the direct sunlight and allowing the rings to be seen in forward-scattered light. This viewing geometry, which astronomers call high-phase angle observation, is particularly valuable for studying rings composed of small dust particles because such particles scatter light very differently depending on the angle between the light source and the observer. When viewed in forward-scattered light, with the sun behind the rings and the observer looking back toward the illumination source, small dust particles appear much brighter than they do when viewed in reflected light with the sun behind the observer. Galileo's high-phase angle observations of Jupiter's rings revealed them to be much brighter than they appeared in other viewing geometries, confirming that the rings are indeed composed primarily of very small particles in the micron size range rather than larger chunks of material. The size distribution of particles in Jupiter's rings, as determined by Galileo's observations at various phase angles and wavelengths, showed that the vast majority of the ring material consists of dust grains between about 1 and 10 microns in diameter, roughly the size of particles in cigarette smoke or fine talcum powder. These tiny particles are far too small to see individually even with powerful telescopes, but collectively they form the faint bands that Galileo observed and measured. The predominance of such small particles in Jupiter's rings contrasts sharply with the composition of Saturn's rings, which contain a wide range of particle sizes from tiny dust grains up to house-sized chunks of ice. And this difference tells us something important about the different processes that create and maintain ring systems around the giant planets. Galileo observed Jupiter's rings repeatedly over the course of its mission, and these multiple observations revealed that the rings exhibit subtle variations in brightness over time. These variations are not dramatic, as Jupiter's rings do not flare or pulse in any obvious way, but careful measurement showed that the distribution and brightness of ring material changes measurably between observations. Some of these variations may be related to the ongoing process of impact-generated dust production, as the rate at which micrometeoroids strike the small moons is not perfectly constant but varies depending on Jupiter's position in its orbit and the flux of interplanetary debris in the Jovian system. Other variations may reflect the complex dynamics of dust particles moving under the combined influences of Jupiter's gravity, its magnetic field, and solar radiation pressure, all of which create a slowly churning system that never quite settles into a perfectly static configuration. The particle dynamics in Jupiter's rings are a gentle ballet of physics, with each tiny grain following its own trajectory under the combined influences of multiple forces. Jupiter's gravity provides the dominant force that keeps the particles in orbit, but the planet's magnetic field exerts electromagnetic forces on particles that carry even small electrical charges, and solar radiation pressure pushes on the sunlit side of each grain in a way that depends on the particle's size and composition. For the smallest particles, those in the submicron range, these non-gravitational forces can be quite significant compared to Jupiter's gravitational pull, and such particles may be quickly swept out of the ring system or pushed into the planet's atmosphere. For slightly larger particles, the balance of forces leads to complex orbital evolution that gradually moves particles inward toward Jupiter while also causing some spreading in the vertical direction perpendicular to the ring plane. Galileo's observations of the ring structure provided constraints on these dynamics, showing how the interplay of forces shapes the ring system over time. The study of Jupiter's faint rings contributes to our broader understanding of ring systems throughout the solar system and beyond, as the processes at work around Jupiter are likely common to many planetary systems. Jupiter's rings demonstrate that ring systems need not be composed of large, icy particles like those in Saturn's prominent rings, but can instead be formed and maintained by the continuous production of fine dust from small moons embedded within the ring system. This impact-generated dust mechanism may operate around many other bodies in the solar system and around exoplanets orbiting distant stars, creating faint rings that are difficult to detect but represent a common outcome of the processes that shape planetary systems. By studying Jupiter's rings in detail, Galileo provided a template for understanding such dusty ring systems wherever they might be found. The contrast between Jupiter's faint, dusty rings and Saturn's bright, icy rings is one of the most striking differences between these two giant planetary systems, and it reveals important information about the different processes that can create ring systems. Saturn's rings contain vast quantities of water ice, with particle sizes ranging from tiny grains up to substantial boulders, and the total mass of Saturn's ring system is roughly comparable to a small icy moon several hundred kilometers in diameter. Jupiter's rings, by contrast, contain so little material that their total mass is estimated to be roughly comparable to a modest asteroid only a few kilometers across, and this material is predominantly rocky dust rather than ice. These differences suggest that the two ring systems have very different origins, with Saturn's rings possibly representing the remnants of a disrupted moon or captured comet, while Jupiter's rings are the steady-state product of ongoing impact processes on small inner moons. The lack of large particles in Jupiter's rings also tells us something about the long-term fate of ring material around the giant planet. If Jupiter once had more substantial rings containing larger particles, those particles would have been lost over time through various processes including orbital decay into the planet's atmosphere and ejection from the system by gravitational perturbations. The fact that only fine dust remains suggests that any larger particles have long since been removed, and that the current ring system represents a balance between the continuous production of new dust and the continuous loss of that dust through atmospheric drag, radiation pressure, and electromagnetic forces. Jupiter's rings are thus not ancient relics but rather a continually renewed feature of the planet, maintained in something like a steady state by the ongoing processes that create and destroy ring particles. Galileo's ring observations also provided context for understanding the small inner moons of Jupiter, those tiny worldlets that orbit within and among the ring structures. Metis and Adraste, the sources of the main ring, are among the smallest moons in the solar system to have been well characterized, and their surfaces must bear the scars of countless micrometeoroid impacts that have generated the dust now spreading through the ring. Amalthea and Thebe, the sources of the Gossamer rings, are somewhat larger and have been observed in more detail, revealing irregular shapes and heavily cratered surfaces consistent with their role as dust producers for the outer ring system. These moons and the rings they produce are linked in an intimate relationship, with the moons slowly eroding to feed the rings while the rings provide visible evidence of the impact processes occurring on the moon surfaces. The gentle observations of Jupiter's ring system by the Galileo spacecraft added another dimension to our understanding of this complex planetary environment, revealing structures so faint that they had gone undetected for centuries of telescopic observation. These rings will never rival Saturn's for visual spectacle, nor will they likely ever become destinations for future exploration in their own right, but they represent an important piece of the puzzle of planetary ring formation and evolution. The lessons learned from Galileo's patient study of Jupiter's dusty rings inform our understanding of how ring systems form, how they are maintained, and how they eventually fade and disappear over the long spans of solar system history. As we continue to observe Jupiter and its rings with newer and more powerful instruments, the foundation laid by Galileo's observations remains essential, providing the baseline measurements against which future changes can be compared. The rings may vary in brightness, the moons may continue to supply new dust, and the delicate balance of forces may shift slightly over time, but the fundamental understanding that Galileo provided will guide our interpretation of these subtle changes. And perhaps in the quiet observation of these faintest of rings, we find a reminder that not all wonders need to be grand or spectacular to be worthy of our attention, that sometimes the most delicate features reveal the most interesting physics, and that patience and careful measurement can unveil beauty that escapes the casual glance. When Galileo completed its primary mission in December of 1997, having accomplished the 2 years of orbital exploration originally planned, the spacecraft remained in good working order, continuing to circle Jupiter in its carefully choreographed dance among the moons, And mission planners at the Jet Propulsion Laboratory found themselves in possession of something rather wonderful, which was a functioning spacecraft with fuel remaining and instruments still operating, and an entire system of moons that had revealed themselves to be far more interesting than anyone had anticipated. And so the decision was made to continue, to extend the mission beyond its original scope. And this extension would eventually become the first of several, each one adding new discoveries and new understanding, each one demonstrating the remarkable durability of a spacecraft that had already overcome tremendous challenges just to reach its destination and begin its work. The first extended mission was given the name Galileo Europa mission, abbreviated to GM, and it was designed to run from December of 1997 through the end of 1999, adding 8 more orbits to the original 11 that had comprised the primary mission. And as the name suggests, this extension focused particular attention on Europa, that ice-covered moon whose surface had revealed such tantalizing hints of an ocean beneath, with its chaotic terrain and its fracture patterns and its remarkable absence of impact craters suggesting a young and active surface. And the scientific community had become increasingly excited about the possibility that Europa might harbor conditions suitable for life, that beneath its frozen shell there might exist a liquid water ocean warmed by tidal heating. And so the decision to focus additional resources on studying this moon reflected both the scientific importance of the questions it raised and the growing public interest in the search for habitable environments beyond Earth. During the Galileo Europa mission, the spacecraft executed close flybys of Europa that brought it nearer to the surface than the primary mission had achieved, passing within hundreds of kilometers of that fractured ice shell, close enough to detect subtle variations in the magnetic field that would provide crucial evidence about what lay beneath. And these magnetic measurements revealed something quite remarkable, which was that Europa appeared to possess an induced magnetic field, a field that varied in response to Jupiter's rotating magnetosphere in exactly the way one would expect if there were a layer of electrically conducting material beneath the surface. And the most plausible explanation for this conducting layer was salt water, an ocean of liquid water containing dissolved salts that allowed it to conduct electricity. And this discovery transformed Europa from an intriguing possibility into a compelling target for future exploration, a place where the ingredients for life as we understand it might come together in ways we had never before observed beyond our own planet. The extended mission also devoted considerable attention to Io, that tortured moon whose volcanoes had so dramatically announced themselves through the discovery of active eruptions during the primary mission. And the Galileo Europa mission included several close approaches to Io that revealed the volcanic activity in greater detail than ever before, capturing images of active lava flows and eruption plumes and calderas that spoke to a level of geological activity unmatched anywhere else in the solar system. And the spacecraft observed changes between flybys, documenting the dynamic nature of Io's surface as new eruptions occurred and lava flows spread across the terrain, creating a record of volcanic activity that would inform our understanding of how heat generated by tidal forces could maintain such extreme geological processes over billions of years. As the Galileo Europa mission drew toward its planned conclusion in late 1999, the spacecraft continued to function remarkably well despite the harsh radiation environment it had been traversing for years. And mission managers faced another decision about whether to continue operations, weighing the scientific potential against the accumulated wear on the spacecraft's systems. And they chose to extend the mission once more, this time under the name Galileo Millennium Mission, a designation that acknowledged both the approaching turn of the century and the ongoing nature of what had become a truly extended exploration. And this second extension would carry Galileo through the end of 2000 and extend further into 2003. adding additional orbits and additional encounters and additional opportunities to study the Jovian system in ways that had never been possible before. The Galileo Millennium mission continued the pattern of close encounters with the Galilean moons while also introducing new scientific objectives and new observations that took advantage of the spacecraft's continued functionality. And one of the most significant events during this period occurred in December of 2000, when the Cassini spacecraft passed through the Jovian system on its way to Saturn, providing a unique opportunity for coordinated observations that had never before been possible, with two spacecraft studying Jupiter simultaneously from different vantage points, and mission planners worked carefully to coordinate the activities of both spacecraft, designing observations that would complement each other and provide scientific insights that neither spacecraft could achieve alone. And this collaboration represented a new approach to planetary exploration, one in which multiple missions could work together to create a more complete picture than any single spacecraft could provide. The joint observations with Cassini during the Jupiter flyby produced measurements of the Jovian magnetosphere from two different locations simultaneously, allowing scientists to distinguish between spatial variations and temporal changes in ways that had never before been possible. Because when you observe a changing system with only one instrument, you cannot easily tell whether the changes you see represent actual variations over time or simply differences between different locations. But with two spacecraft making measurements at the same time from different positions, this ambiguity could be resolved, and the results revealed the dynamic nature of Jupiter's magnetic environment in new detail, showing how the magnetosphere responded to changes in solar wind conditions and how material from Io's volcanoes spread through the system along magnetic field lines. Throughout the extended missions, the spacecraft continued to accumulate damage from the intense radiation environment that surrounded Jupiter, with charged particles gradually degrading the electronic components and affecting the performance of various instruments. And by the end of the mission, this radiation exposure had exceeded the original design limits by a factor of 4, meaning that Galileo had absorbed 4 times as much radiation as it had been built to withstand. And yet the spacecraft continued to function, a testament both to the conservative engineering that had gone into its design and to the creative problem-solving of the operations team, who found ways to work around failures and adapt to changing capabilities as systems degraded over time. The engineers who maintained Galileo during these extended years developed an intimate understanding of the spacecraft's condition and behavior, learning to recognize the subtle signs of radiation damage and to devise workarounds that kept critical systems functioning even as individual components failed. And they developed techniques for managing the spacecraft's memory and processing capabilities that allowed continued scientific operations despite the cumulative effects of years of radiation exposure. And in some cases, they discovered ways to use backup systems or to reconfigure primary systems that extended their useful life beyond what had originally been anticipated. And this ongoing maintenance and adaptation became a kind of partnership between the human engineers on Earth and the robotic spacecraft they had built, a collaboration that spanned the vast distances of the solar system and allowed Galileo to continue its work long after anyone had expected. The antenna malfunction that had plagued the mission from its earliest days in the Jovian system continued to constrain data transmission throughout the extended missions. But the data compression techniques that had been developed during the primary mission were refined and improved over time, allowing increasingly efficient use of the limited bandwidth available through the low-gain antenna. And by the end of the mission, Galileo had returned approximately 14,000 images of Jupiter and its moons, a number that represented only a fraction of what would have been possible with the full high-gain antenna, but that nonetheless constituted an enormous scientific treasure. Each image carefully selected and compressed and transmitted across the vast distances between Jupiter and Earth. each one representing a choice made by scientists about what was most important to capture and preserve from this extraordinary opportunity. The cumulative statistics of the Galileo mission grew impressive over the years of extended operations, with the spacecraft completing 34 orbits of Jupiter over nearly 8 years of exploration in the Jovian system, each orbit bringing new encounters with different moons and new opportunities to study the planet and its environment from different angles and at different times. And the total distance traveled during these years stretched into the billions of kilometers as Galileo looped repeatedly through the complex gravitational environment of Jupiter and its satellites, adjusting its trajectory with each close flyby to set up the next encounter, weaving a path through the system that no spacecraft had ever traced before. As the extended missions progressed and the spacecraft's capabilities gradually degraded, mission planners faced increasingly difficult decisions about which science to prioritize, knowing that each observation consumed limited resources and that the remaining lifetime of the mission could not be predicted with certainty. And these decisions required balancing competing scientific objectives against practical constraints, choosing between different moons to study and different instruments to operate and different types of measurements to make. And the scientists and engineers involved in these decisions worked together to identify the highest priority observations, those that would provide the greatest scientific return given the spacecraft's declining capabilities. And they developed plans that could be adapted as conditions changed, preserving flexibility while focusing on the most important objectives. The magnetic field measurements during the extended missions proved particularly valuable, as repeated flybys of the Galilean moons accumulated evidence about their internal structures that could not have been obtained from single encounters. And over time these measurements revealed something unexpected and wonderful, which was that all 4 of the large Galilean moons appeared to possess conductive layers beneath their surfaces, suggesting that subsurface oceans might be far more common in the outer solar system than anyone had previously supposed. And while Europa remained the most compelling candidate for a potentially habitable ocean world, the evidence for liquid water beneath the surfaces of Ganymede and Callisto added new complexity to our understanding of how such oceans might form and persist. And even Io, despite its volcanic nature, showed magnetic signatures that hinted at a subsurface magma ocean, a layer of partially molten rock that contributed to the generation of its volcanic activity. The discovery of magnetic signatures suggesting ocean presence on all 4 Galilean moons represented one of the most significant scientific achievements of the extended missions, transforming our understanding of where liquid water might exist in the solar system and expanding the potential habitats for life beyond Earth in ways that had profound implications for future exploration. And these findings emerged not from any single dramatic measurement but from the patient accumulation of data over many orbits and many flybys, each passage adding another piece to the puzzle, each measurement contributing to a picture that only became clear when viewed as a whole. And this gradual assembly of understanding exemplified the way that planetary exploration often works, with major discoveries emerging from the careful analysis of many observations rather than from any single moment of revelation. The operations team during the extended missions developed procedures for managing the spacecraft's aging systems that allowed continued function despite the accumulated radiation damage and the wear of years of operation. And they learned to monitor the health of critical components and to take preventive measures when problems appeared imminent. And they became adept at diagnosing anomalies and developing solutions that could be implemented across the vast distance between Earth and Jupiter, where light-speed communication delays meant that any intervention had to be carefully planned and executed without real-time feedback. And this experience informed the design and operation of subsequent missions, contributing to the body of knowledge about how to maintain spacecraft in harsh environments over extended periods. As the spacecraft's propellant reserves dwindled and its systems continued to degrade, mission planners began to consider the eventual end of the mission and what should happen to Galileo when it could no longer be controlled. And this consideration led to decisions about the final phase of the mission that would shape its conclusion. But during the extended operations, the focus remained on continuing science, on gathering as much data as possible while the spacecraft remained capable, on making the most of every remaining orbit and every remaining encounter. And the scientists and engineers who had devoted years of their careers to this mission worked with a kind of quiet dedication to extract every possible bit of scientific value from the aging spacecraft they had tended for so long. The Galileo Europa mission and the Galileo Millennium mission together more than tripled the duration of orbital operations compared to the original 2-year primary mission. And they did so at relatively modest additional cost because the spacecraft was already built and launched and operating. And the investment required to continue operations was small compared to the scientific return. And this pattern of mission extension became a model for later missions, demonstrating the value of designing spacecraft robust enough to operate beyond their primary mission lifetimes and of maintaining the flexibility to take advantage of opportunities as they arose. And Galileo's extended operations contributed to a shift in how mission planners thought about mission duration and about the balance between initial design margins and the potential for extended operations. The 14,000 images returned over the course of the primary and extended missions, despite the antenna malfunction that had limited data transmission so severely, represented not just a collection of pictures but a visual record of a complex and dynamic system, capturing eruptions on Io and ice fractures on Europa and the subtle color variations of Ganymede and the ancient cratered surface of Callisto, and capturing too the cloud patterns of Jupiter itself, the swirling storms and the layered bands and the changing appearance of the Great Red Spot over the years of observation. And each image required careful planning and execution, with the science team selecting targets and designing observations that would maximize the value of the limited data that could be returned. And the resulting collection stands as a testament to both the engineering that made it possible and the scientific judgment that determined what to capture. Throughout the extended missions, Galileo continued to make measurements that no other spacecraft could make, studying Jupiter's atmosphere and magnetosphere from a vantage point within the system, observing the moons at close range and with repeated visits, building a picture of the Jovian system as a dynamic and interconnected environment where the planet and its moons influenced each other in complex ways, where volcanic material from Io spread through the magnetosphere and fell back onto the surfaces of other moons, where tidal forces heated the interiors of the satellites and drove the geological activity that shaped their surfaces, and where the tremendous magnetic field of Jupiter created an environment unlike anything else in the solar system, a miniature realm governed by its own physical processes and its own cycles of activity. The gift that kept giving, as this extended period of exploration might fairly be called, ultimately lasted nearly 3 times as long as the original mission, with Galileo continuing to orbit Jupiter and return valuable scientific data from December of 1995, when it entered orbit, until September of 2003, when the mission finally came to its planned end. And over those nearly 8 years in the Jovian system, the spacecraft transformed our understanding of Jupiter and its moons in ways that continue to shape planetary science today, establishing Europa as a priority target for astrobiological exploration and revealing the volcanic nature of Io and demonstrating the complex geology of Ganymede and Callisto, and providing measurements of Jupiter's atmosphere and magnetosphere that remain fundamental references for researchers studying the outer solar system. The extended missions represented not just additional science but a new way of thinking about planetary exploration. one in which the initial investment in a spacecraft could be leveraged over many years of continued operation, and in which the scientific community could respond to discoveries made during the primary mission by designing extended observations that addressed new questions raised by initial findings, and in which the spacecraft and its human operators could form a kind of partnership that adapted to changing circumstances and evolved over time. And this approach has since become standard practice in planetary exploration, with mission extensions routinely planned and executed for spacecraft that remain capable of productive operations. But Galileo was among the first to demonstrate just how valuable such extensions could be, and the lessons learned during its long years at Jupiter informed the planning and operation of missions that followed. As the year 2003 moved gently toward its autumn months, the Galileo spacecraft found itself in a condition that mission planners had long anticipated, though perhaps had hoped might be delayed just a little while longer. After more than 14 years in space and nearly 8 years orbiting Jupiter, the hardy explorer was beginning to show the inevitable signs of its extended service in one of the most punishing radiation environments in our solar system. Its propellant tanks, which had once held the fuel necessary for the countless orbital adjustments and trajectory corrections that had made its scientific observations possible, were now approaching empty. The gyroscopes that helped maintain its orientation had degraded significantly, and the tape recorder that had proven so essential after the high-gain antenna failure had developed additional problems that limited its usefulness. Most critically, without adequate propellant, the ability to control precisely where Galileo would travel in the Jovian system was diminishing with each passing week, and this reality forced the mission team to confront a decision that was both scientifically responsible and emotionally difficult. The question of how to conclude the Galileo mission had been under consideration for several years, and the answer that emerged reflected a set of ethical principles that had been developing within the space science community for decades. These principles, collectively known as planetary protection protocols, are built upon the recognition that when we send spacecraft to other worlds, we carry with us the microscopic hitchhikers of our own planet, the hardy bacteria and bacterial spores that can survive in remarkable conditions and that might, under certain circumstances, contaminate environments we wish to study. For most of Galileo's mission, this concern had been somewhat abstract, a consideration for future missions rather than an immediate operational constraint. But the spacecraft's own discoveries had transformed this abstract concern into a pressing ethical obligation, because among the most significant findings of the entire mission was the compelling evidence that Europa, that ice-covered moon with its smooth and fractured surface, almost certainly harbored a liquid water ocean beneath its frozen shell. The implications of this discovery were profound and far-reaching. If Europa possessed a global ocean of liquid water, kept warm by the tidal heating generated through its gravitational interactions with Jupiter and the other large moons, then Europa represented one of the most promising locations in our solar system for the possible existence of life beyond Earth. The conditions at the boundary between Europa's rocky core and its ocean floor might bear some resemblance to the hydrothermal vent environments on our own planet's ocean floors, environments that support thriving ecosystems entirely independent of sunlight. The mission team understood that while Galileo had been sterilized before launch according to the protocols of its era, no sterilization process is perfect, and the spacecraft might still carry viable Earth microorganisms that had survived the journey through space. If Galileo were allowed to drift uncontrolled through the Jovian system, there existed a small but non-negligible probability that it might eventually impact Europa, potentially introducing terrestrial biology to an environment that might host its own native life or that might be studied by future missions searching for indigenous organisms. The decision to deliberately destroy Galileo by sending it into Jupiter's atmosphere was therefore not merely a practical solution to the problem of an aging spacecraft, but a conscious act of environmental stewardship on a planetary scale. Jupiter itself, with its crushing pressures, extreme temperatures, and violent atmospheric chemistry, presented no risk of contamination in any meaningful sense. Any Earth microorganisms carried by Galileo would be thoroughly destroyed within moments of entering the Jovian atmosphere, incinerated and dispersed into an environment so hostile that no terrestrial life could possibly survive, let alone reproduce and spread. By guiding Galileo into Jupiter, the mission team could ensure that the spacecraft's remains would be rendered completely sterile while simultaneously protecting Europa and the other potentially habitable moons from any possibility of biological contamination. It was an elegant solution, scientifically sound and ethically responsible, though it required the team to accept that they were bringing their beloved mission to a deliberate and permanent end. In the days leading up to the planned atmospheric entry, the mission team worked to extract every last bit of scientific value from the spacecraft's remaining capabilities. Galileo continued its observations of the Jovian system, recording data about Jupiter's magnetosphere, the behavior of charged particles in the space around the giant planet, and the distant observations of the moons that had revealed so many wonders over the preceding years. The spacecraft's cameras, though limited by the data transmission constraints that had characterized the entire orbital mission, captured final images that would be added to the vast archive of observations that Galileo had compiled. Scientists understood that these would be the last direct measurements from within the Jovian system for many years to come, as no follow-up mission was yet on its way, and so there was a gentle urgency to the final data collection efforts, a desire to gather every possible observation before the opportunity was lost forever. The trajectory that would carry Galileo to its end had been carefully calculated to achieve several objectives simultaneously. The spacecraft would approach Jupiter in a path that took it through regions of scientific interest, allowing for measurements during the final approach while ensuring that the ultimate impact would occur in Jupiter's equatorial region where the spacecraft's entry could be modeled and analyzed. The entry point was selected to avoid any possibility of the spacecraft passing behind Jupiter from Earth's perspective at the critical moment, ensuring that communication would remain possible until the very end. The engineering team had worked out the precise timing of the final maneuvers, using the last of the propellant to adjust Galileo's orbit and set it on its terminal trajectory, knowing that once these maneuvers were complete, the spacecraft's fate would be sealed by the unchangeable laws of orbital mechanics. On September 21, 2003, as afternoon arrived in the eastern United States, the spacecraft that had traveled so far and discovered so much began its final descent into the atmosphere of Jupiter. The entry velocity was approximately 48.2 kilometers per second, a speed so great that it defies easy comprehension, more than 170,000 kilometers per hour, fast enough to cross the entire width of the continental United States in less than 2 minutes. At such velocity, the thin upper atmosphere of Jupiter, which under other circumstances might seem insubstantial, became a wall of resistance that would rapidly heat the spacecraft to temperatures far beyond any material's ability to withstand. The signals from Galileo continued to arrive at the Deep Space Network antennas on Earth, the faint radio whispers crossing the vast distance between Jupiter and our planet, carrying the last telemetry from the spacecraft's final moments of operation. The team members gathered to monitor these final signals understood something that added a poignant dimension to the experience. Because of the immense distance between Jupiter and Earth, which on that day amounted to approximately 780 million kilometers, the radio signals required about 46 minutes to make the journey, traveling at the speed of light but still requiring considerable time to cross such an enormous expanse. This meant that when the team received a signal from Galileo, they were observing something that had already happened 46 minutes earlier. By the time the final transmission arrived at Earth at approximately 3:43 in the afternoon Eastern Daylight Time, Galileo had already been destroyed for the better part of an hour. The spacecraft they were listening to no longer existed, had ceased to exist while they were still receiving its earlier transmissions, and this awareness lent a strange and contemplative quality to the final moments of the mission. They were not watching Galileo die in real time, but rather receiving the last messages from a spacecraft that had already completed its journey, like reading the final letter from a traveler who has already arrived at their destination. The actual process of atmospheric entry and destruction unfolded far more rapidly than any human observation could track. As Galileo descended into increasingly dense layers of Jupiter's atmosphere, the friction of its passage converted its tremendous kinetic energy into heat, causing temperatures on the spacecraft's exterior to rise rapidly into thousands of degrees. The various components of the spacecraft would have failed and disintegrated in a sequence determined by their individual thermal tolerances, with more delicate instruments and structures succumbing first while the denser structural elements persisted slightly longer. Within seconds, perhaps less than a minute after encountering significant atmospheric resistance, Galileo would have been reduced to a shower of fragments, and those fragments would have continued to heat and vaporize as they descended further into the increasingly dense and hot Jovian atmosphere. Eventually, every atom that had once been part of the spacecraft would be dispersed into Jupiter's atmosphere, mixed into the swirling clouds of hydrogen and helium, becoming an infinitesimal addition to the mass of the solar system's largest planet. In a sense, Galileo had become part of Jupiter, the world it had studied for so long. For the men and women who had devoted significant portions of their careers to the Galileo mission, the conclusion of the project brought emotions that were complex and difficult to articulate. Some team members had worked on Galileo for more than 25 years, having joined the project during its initial development phase in the late 1970s and remained through all the challenges, delays, redesigns, and ultimate triumphs that followed. These individuals had spent more time with Galileo than with almost any other undertaking in their professional lives, and the spacecraft had become in some ways an extension of their own efforts, a physical manifestation of their collective knowledge and dedication traveling through the outer solar system. The end of the mission meant the end of a relationship that had defined careers and consumed countless hours of thought, planning, analysis, and problem-solving. There was sadness in this conclusion, certainly, but there was also satisfaction. A recognition that the mission had accomplished far more than its designers had dared to hope and that its scientific legacy would continue to influence planetary science for generations. Claudia Alexander, who served as the final project manager for the Galileo mission, spoke to the mixture of accomplishment and loss that characterized the mission's end. She reflected on the extraordinary journey that Galileo had undertaken, the challenges it had overcome, and the discoveries it had made possible. For Alexander, who had the responsibility of overseeing the mission through its final years and ultimate conclusion, there was a profound awareness of the historical significance of the moment. She understood that Galileo had fundamentally changed humanity's understanding of the outer solar system, revealing Jupiter and its moons to be far more complex, dynamic, and scientifically interesting than previous observations had suggested. The mission had raised new questions even as it answered old ones, and those new questions would drive the next generation of exploration. Alexander recognized that ending the mission was the right decision, the responsible choice given the circumstances. But she also acknowledged the difficulty of deliberately bringing such a successful and beloved endeavor to its close. The legacy of the Galileo mission extends far beyond the data it collected, though that data alone would justify its place in the history of space exploration. The spacecraft's observations transformed our understanding of Jupiter from a distant and somewhat mysterious gas giant into a complex world with intricate atmospheric dynamics, a powerful magnetic field, and a diverse family of moons, each with its own character and scientific interest. The discovery of evidence for subsurface oceans on Europa, and potentially on Ganymede and Callisto as well, opened new avenues of astrobiological speculation that continue to drive mission planning today. The detailed observations of Io's volcanic activity revealed a world more geologically active than any other body in the solar system, challenging previous assumptions about how geological activity relates to planetary size and age. The first direct measurements of Jupiter's atmosphere by the descent probe provided ground truth for models that had previously relied entirely on remote observations. Perhaps equally important was what Galileo taught us about conducting complex missions in challenging environments. The creative solutions developed to work around the high-gain antenna failure demonstrated that skilled and dedicated teams could accomplish remarkable things even when faced with significant setbacks. The careful management of radiation damage, the innovative use of the tape recorder for data storage, and the precise planning of orbital trajectories to maximize scientific return while conserving limited resources all provided lessons that would inform future missions. Galileo proved that long-duration missions in the outer solar system were feasible and scientifically valuable, paving the way for subsequent missions like Cassini-Huygens at Saturn and the Juno mission that would return to Jupiter years later. As the final signals faded and the Deep Space Network antennas turned to other tasks, the Galileo mission passed from active operation into history. The team members who had gathered to mark the occasion gradually returned to other projects, other missions, other challenges, carrying with them the experience and knowledge gained from their years with Galileo. The data collected by the spacecraft continued to be analyzed and published, yielding new insights for years after the mission's end, a testament to the richness of the observations and the continuing interest of the scientific community. In a very real sense, Galileo's mission did not end with its destruction but continues through the ongoing work of scientists who study its data, through the missions it inspired, and through the expanded understanding of our solar system that it made possible. The deliberate destruction of Galileo in Jupiter's atmosphere was a quiet ending to a mission that had achieved so much. There was no explosion visible from Earth, no dramatic imagery of the final moments, simply the fading of radio signals that had traveled across hundreds of millions of kilometers to report on the spacecraft's status. The team knew that by the time they heard those final transmissions, Galileo had already completed its journey, had already become part of Jupiter, had already ensured that Europa's potentially life-bearing ocean would remain uncontaminated by terrestrial microorganisms. It was an act of scientific responsibility, of ethical stewardship, of care for worlds that we were only beginning to understand. And in that quiet, responsible ending, there was a kind of grace, a recognition that the universe is vast and ancient and that our brief visits to other worlds should be conducted with respect for what we might find there, even if what we might find is nothing more than the possibility of life not yet discovered.